air on the valley slopes cools rapidly due to dash radiation, which is supposed to be terrestrial radiation. As we know, at night, the land or the slopes lose heat in a process that is referred to as terrestrial radiation, resulting into the air to become cool, hence it will be able to subside. Number 1.1.3, if the dew point temperature is below freezing point in a valley, water vapor condenses directly into a dash pocket. As we know that whenever cold air subsides to the valley bottom, it will result into the development of frost pocket. 1.1.4, in the mountainous regions of Cape Town, people tend to build their houses on the dash facing slopes, because we know Cape Town is situated in the southern hemisphere, and we know in the southern hemisphere the north facing slopes usually receive more sunlight or direct heat, which makes them to be warmer. Therefore, we say in the mountainous regions of Cape Town, people tend to build their houses on the north facing slopes because they will be warmer. Right, number 1.1.5, 1.1.5, it says a warm layer of air with cold air above and below. A warm layer of air with cold air above and below it, causing an inversion, is known as, that will be the thermal belt. Because we know a thermal belt forms as a result when cold air subsides to the valley bottom, forcing the warm air to rise and will settle in the middle of the valley, forming a thermal belt, whereby below the thermal belt, the air will be cold, and above the thermal belt as well, the air will be cold. That's why they say a warm layer of air with cold air above and below. So that will be the thermal belt. 1.1.6, plants that require more sunlight in winter grow best on the dash facing slopes in the northern hemisphere. Northern hemisphere. The question says plants that require more sunlight in winter grow best on the dash facing slopes in the northern hemisphere. So that will be the south facing slopes, because we know in the northern hemisphere the south facing slopes receive direct heat, which makes them to be warmer, and which is, we know warmer conditions are suitable for the growth of plants, because they will require or they will need that sunlight. In 1.1.7, the area of a valley which receives direct sunlight in winter is known as a zone of incidence, because we know well that we saw the shadow zone doesn't receive direct sunlight, which means that the zone of incidence will hence receive direct sunlight in winter. Right. Let us proceed to question 1.2, which says, just move this one a bit. It says, various options are provided as possible answers to the following questions. Choose the correct, choose the answer and write only letter A to D next to the question. Number the instructions telling us to write the answer or to choose the answer between A, B, C, and D. Right. So this is our synoptic weather map 1.2.1 says the pressure cell labeled A is the dash dash labeled A. This is our pressure cell A here. As you can see, remember, you can see this is the Southern Africa, which means this is the interior, right? So over the interior, we have this pressure cell A, which is a high pressure cell, and definitely that will be the Kalahari high pressure cell or the Kalahari and a cyclone. Because remember, when we say anticyclone, and cyclones are high pressure cells. Right. 1.2.2, the direction of the surface air circulation around pressure cell B. Let's check pressure cell B. Pressure cell B is as well a high pressure cell, as you can see here. Sorry, I move this. This is our pressure cell B, which is considered as H, indicating a high pressure. So they are saying the direction of surface. The concept here is the word surface. Let's wait for technology to get back in order. So the direction of surface air circulation around pressure cell B, because since we know pressure cell B is a high pressure cell, so we need to understand the movement or the saturation of air in high pressure cells. So they will be subsiding. This is the upper atmosphere where there will be convergence. Then on the surface, there will be divergence. All right. So divergence, and as well, since we are in the southern hemisphere, the saturation is going to be anti-clockwise. Right. So if we check our options here, it is clockwise, which is not correct, which makes our anti-clockwise correct. Does not ascend, neither descend, because our focus is on the surface, and on the surface there will be divergence and anti-clockwise rotation. Right. Question 1.2.3, it says the area of elongated high pressure at sea. Remember, to elongate is the same as isobars extending, right? Let's check high pressure cell at sea, right? The area of elongated high pressure cell at sea. This is our high pressure cell, like we know. This is the South Atlantic high pressure cell. So you can see the isobars are raging, or they are stretching, or they are extending towards the land, and that is referred to as raging, which makes our option A to be the correct one. Right. I'll proceed to question 1.2.4, which says weather system D develops because of the impact of the Coriolis force on the air movement between the dash cells. Let us first check what is weather system D. We look for the system D. Yes, this is our weather system D here. And as well, we know that this is it is a mid-latitude cyclone, because we can see the evidence of a cold front and evidence of the warm front, right? So which means if we check again the question, it says weather system D develops because of the impact of the Coriolis force on the air movement between dash cells. Right. Let's check between such cells. We have the polar high pressure cell and the subpolar high low pressure, which is correct because we know what they say. The system develops because of the impact of the Coriolis force between the Coriolis force on the air movement between the polar high pressure cell and the subpolar low pressure, because we know mainly that's where the mid-latitude cyclones can develop. And as well, we can talk about when they say the subpolar low pressure cell and the subtropical high pressure cells. I think option A and B, they are both correct. Because if you check the polar high cell, polar high pressure cell, that is situated between 60 to 90 degrees. In the subpolar low and subtropical high pressure cell is between 30 to 60 degrees, and subpolar low between 60 to 90. So which makes the two options to be viable. Right. In 1.2.5, it says the map shown above is an example of a dash synoptic weather map because of the dash rainfall experienced over Cape Town. Right. So the map above, if you check the map once again, you can notice there is a high pressure cell dominating the interior. And so the codifront, which has approached the land, the high pressure cells are reaching to the land. There's a coastal presence at the coast. There's also pressure gradient between the land and the coast, or between the interior and the coast. And these are all evidences to prove that this is a winter synoptic weather map. So meaning, so far, we know that the map shown is an example of a winter. So we can take option 2, winter weather map, because of the we say here, there is summer. Yes, so we can go with option number 3 because of the frontal rainfall experienced over Cape Town. When we talk about frontal rainfall, because this comes as a result of the different air masses meeting at the polar front. So that's why we say that the map is a winter map, which as well causes frontal rainfall. So, which means option 2 and 3 for this case, which will be number C, right, as our correct answer. Let us proceed to question 1.2.6, which says, weather system D usually brings dash condition to Cape Town in winter. Let's check weather system D once again. So the weather system D is a mid-latitude cyclone. And as you can see, they're saying this is Cape Town already. And you can see there's a cold front already approaching Cape Town there, right? So meaning, if you check our question once again, it says weather system D usually brings all right. So weather system D usually brings, like we mentioned, the system D, let me check again. D is it is a mid-latitude cyclone. So what does it bring over Cape Town? right? So we know it is a mid-latitude cyclone, which could result into let's check rainy conditions, floods. Floods is not a weather conditions. Rainy conditions. We know that the mid-latitude cyclones do cause overcast conditions, which makes this one out. Floods out, clear skies out, windy and floods. And like we know, floods are not weather conditions. If you look at option number D, dry conditions and clear skies, not really. Let's check this question once again. Was there a mistake? Let's say. Let's see. All right. Yes. So I think we're going to go with. Oh, no, I think I was dealing it. Although I was doing a different question. So we are still doing question 1.2.6, which says the system usually brings dash conditions to Cape Town, and as we know, dry and windy. The mid-latitude cyclones usually brings wet conditions, which makes option A to be wrong. Warm and rainy. Not really, because we know a cold front does not cause warmer conditions over Western Cape. Option number C, cold. Yes, this is a condition caused by the cold front conditions, and as well they cause rainfall, which could be correct because option number D talks about dry conditions. So the conditions that would be cold conditions and rainy conditions, right? Then number 1.2.7, let me first remove this because I made a mistake. 1.2.7, it says the weather conditions associated with pressure cell A. Yes, well, that is correct. Let us check pressure cell A. Yes, pressure cell A, it is our cell A. It is our high pressure cell called the Kalahari or the continental high pressure cell. So weather system A, we said that is the Kalahari high pressure cell, and we know high pressure cells are responsible for causing let's check the first option. They don't result into rain, so this is out, which makes the answer to be false. As well, option number B, because high pressure cells will not normally cause rainy conditions, especially since we are dealing with winter season. Number C, windy, which makes now this option to be also out because of floods. Option number D, dry conditions and clear sky, which makes this to be correct because we know the Kalahari will cause dry conditions and clear skies during winter season as a result of the inversion layer being below the escarpment, blocking the warm moist air to reach the interior to condense. Right. Number 8, the pressure at the center of pressure cell E. Let us first check pressure cell E. So pressure cell E, yes, you can see this is our pressure cell E, which is a coastal law, as we know well, because there is a law, there's L here, which means this is a low pressure cell situated along the coast, which makes this to be a coastal law, right? So the question is saying the pressure at the center of pressure cell E is dash dash down 1000 1004 MB and moves from dash dash along the coast, right? Okay, the pressure at the center of pressure cell E, check options. That's gonna be lower because like we mentioned that E is a coastal law, and as well you can see if we check again here, this is 1000. If you look at this isobar, it is 1004 millibars. If you check this one, the next one 1008. So it means next one 1012. It means pressure is decreasing as we move towards the center, which makes it the pressure to be lower, or it is a low pressure, which makes one to be correct. Two is not viable because they're saying pressure does not, the pressure is not high. How they move? We know that low pressure cells, the coastal laws, they move along the coast from the west to the east, which makes option 1 and 4 to be correct, which is 1.2.8, 1 and 4, 1 and 4, 1 and 3, which means number B will be our correct answer. All right. If we proceed to question 1.3, it says, refer to the infographic on tropical cyclone Gombe below. This is our info graph where we have a satellite image and as well the given information. Right. This Cyclone Gombe has killed at least 53 people since the cyclone swept into northern and central areas of the country on Saturday, March 12, 2022. Data showed that the flooding associated with Gombe destroyed a total of 141,854 houses, along with 69 health centers, 21 water systems, 2,764 electricity poles. A total of 2,265 classrooms were damaged, affecting a total of 216 theory pupils and 4,421 teachers. A total of 91,177 hectares of crops were lost, while a total of 1,243 kilometers of roads were severely damaged. Southern Africa has suffered repeated devastating cyclones of the type that used to be relatively rare in the past. Scientists believe climate change is fueling their intensity via the warming of the Indian Ocean. Right. Let's check on the questions. All right. Okay, question 1.3.1. How many tropical cyclones have occurred before tropical cyclone Gombe? Before Gombe, so we go back to, there was A, B, C, D, E, F, and G for Gombe. So before Gombe, how many cyclones have occurred in this area? 1, 2, 3, 4, 5, 6. So there'll be 6 cyclones, right? Number 1.3.2, according to the infographic, what is the scientific evidence fueling intensity of tropical cyclones in the Indian Ocean? Remember, the question is telling us to refer to the infographic to find out what is fueling the intensity, the strength of the cyclone in the Indian Ocean. Now, let us visit the infographic. But I remember while reading, I came across this statement which says, scientists believe climate change is fueling the intensity. So which means, so far, climate change is fueling the intensity via the warming of the Indian Ocean. So we could consider those options, and we say we consider climate change, and as well warming of the Indian Ocean. Warming of the Indian Ocean. Right. 1.3.3 says, provide evidence from the satellite image which suggests that the tropical cyclone Gombe has reached the stage of maturity. Right. Let us check on our satellite images to prove that Gombe reached the mature stage. Right. So our satellite image, as you can notice, we have the eye which has developed at the center of the cyclone, and we know that the eye are more developed in the mature stage. So the evidence could be the presence of the eye, at the center of the tropical cyclone. Number 4, discuss why tropical cyclone Gombe will decrease in intensity once it reaches the coastline of Mozambique. So to describe the saying, question 1.3.4, to describe why tropical cyclone Gombe will decrease in intensity once it reaches the coastline of Mozambique. What will make it to slow down? What will make it to weaken? You see? So they are saying once it reaches the coastline of Mozambique. But if we check on our synoptic map, you can see this is our cyclone Gombe, and somewhere here we have Mozambique, and you know Mozambique is land, right? It's land. Or if you check on the slide image here, so this is Southern Africa, this is Madagascar here, if I'm not mistaken. So if it moves close to this point, it is moving towards land, and we know when cyclone reaches the land, there will be friction. So you could say friction with the land, Friction the land weakens the cyclone. That's one point. Zulu can talk about that less availability of light and heat supply over Mozambique. Since Mozambique is a land, there will be less evaporation, less condensation, resulting into less light and heat. Because we know the more the light and heat, the cyclone becomes more stronger. So the less light and heat availability, the cyclones weakens or its intensity reduces. We'll talk about as well when it moves towards cooler areas. Over Mozambique, it weakens. Because no cyclones do not prefer cooler areas. I want to talk about less availability or less moisture over land of Mozambique which weakens the cyclone, among others, right? But since they were asked for only two, so we only need to give points based on the mark allocation. Right, let's go back to the question. So we've seen what causes the intensity of the cyclone to decrease, right? To decrease. If they say what makes the intensity to increase, then we shall give the opposite. Availability of latent heat, a lot of moisture, less friction of the land, among other factors, right? Question 1.3.5, it says, explain two other elements of tropical cyclone Gombe indicated in the infographic that may have resulted in the damage caused to the infrastructure. Right, so they are asking for the weather elements, right? We're going to talk about weather elements here. We talk about things like wind, rainfall, about thunderstorms, lightnings, talk about things like hail, the overcast conditions. All these are the different weather elements, the strength of the winds and all that, right? However, since the question is telling us to say explain two other elements of Cyclone Gombe indicated in the infographic, so we need to go back to the infographic and try to identify those elements which resulted into damage, right? Let's check. So if you check again our infographic, Cyclone Gombe has killed at least 3 people since the cyclone swept into the northern central half of the country. March 12, 2022. It showed that the flooding associated with Gombe destroyed a total of houses, centers, water systems, and electricity poles. But remember, floods is not a weather element, right? So we need to identify the weather elements. Let's continue. A total of two of that classrooms were damaged, affecting pupils, teachers. Hectares of crops were lost. Roads were severely damaged. Southern Africa has suffered repeated devastating cyclones of that type, to be relatively rare in the past. Science believe climate change for the intensity of the cyclone, right? However, here they don't mention about the other elements, but if we check on this other information, let's say if we look at the satellite image, we can see there's a lot of clouds that have developed, which means there'll be a lot of heavy rainfalls. Heavy rainfalls. Let's check the question again. 135. The question says, explain two other elements of the Cyclone Gombe, indicated in the infograph that may have resulted in the damage caused to the infrastructure, right? Okay, so let's use our blank page to try to explain that question. 135, right? So we can talk about overcast clouds causing heavy rainfalls, which destroyed classes, epistles, etc. That's one. Since we know that there are heavy rainfalls, let's also talk about heavy rainfalls resulted into floods, which damaged crops. We know that tropical cyclones, as well as associated with, they are associated with strong winds, damaging electricity poles, poles. Electricity poles. Let's check something on our question once again. So in the infograph, spoke about the infrastructure, destroying water system, health centers. Okay, so we can as well say that that heavy rainfalls damaged classes. And check another example. Damaged classes, water systems, health centers, right? classes, water systems, health centers, etc. What else can we talk about there? We spoke about the mention about the strong winds, right? Right. Yeah, so they did ask for 2. I think that's enough for our question 1.3.5. Right. Then in question 1.3.6. So 136, it says state to hey, that's about that sound. Sorry about that technology. Okay, 1.3.6, it says suggest 2 precautionary strategies that can be implemented in this area to reduce the possible damage caused to the infrastructure during tropical cyclones by flooding, as mentioned in the article. Right. What measures can be put in place to reduce the possible damage caused to the infrastructure? Because as we know, we cannot control tropical cyclones because these are natural phenomena. However, we can try to put in place strategies or plans to ensure that we reduce on the effects that are caused by these cyclones. Right. So, just going to suggest 2, which means what we can do, such as flooding, if we put coastal defenses are such as sandbags along the coast. This will assist in reducing flooding of the land. Secondly, people to move away from low-lying areas. So this could well reduce the loss of lives, right? As well build with stronger materials to avoid homes being washed away. Also, need to maintain the drainage systems. Maintain and repair the drainage so that they could easily accommodate the overflow of water, right? So we need to ensure that build better infrastructures that are strong enough, etc. So among other strategies, so if you put this in place, this could reduce on the impact of right. Let's proceed. Question 1.4. 1.4 says, study the information below. Warning of severe weather. Cape Town, batten down the hatches. Heavy rain, cold winds, severe flooding, and even light snow are predicted as a battery of cold fronts head to the Western Cape that could bring discomfort and displacement in some areas. The South African Weather Service said this might cause thunderstorms, flooding of roads in both formal and informal settlements, damage to property and infrastructure, loss of livelihoods and livestock, damage to crops, disruption to essential services, and all right. So question 1.4.1 says, identify the weather system shown in the diagram of which the cold front forms part of. So this was a good question or an easy question, which says identify the weather system shown in the diagram. You can see the diagram. You can see the cold front symbol here, and we know this is part of a mid-latitude cyclone. Mid-latitude cyclone, or could as well be referred to as a temperate depression or a frontal depression or extratropical cyclone, right? 1.4.2. Okay, let me write these other names for 1.4.1 just in case for clarity. 1.4.1, we said it is part of the mid-latitude cyclone or a frontal depression. It can as well be called extratropical cyclone or a temperate depression. So all these names mean the same thing. They all refer to a mid-latitude cyclone, right? 1.4.2, it says, what is the main reason why these weather systems are more prevalent or common over Cape Town during winter, as shown in the article? Okay, let's check the article. Anyways, they said, okay. All right, so according to the article, so what is the main reason why these systems are more common over Cape Town during winter? Right. 1.4.2. 4.2. So you could say the mid-latitude cyclone moves northwards. They move northwards. During winter season. Or you could as well say they move in relation to the migration of the sun. Or you could as well say that they follow the latitudinal position of the sun. Latitudinal position of the sun. So this the two are more like the same. However, with the first option, we know that the mid-latitude cyclones, they move northwards in summer. That's why they always try to be close to the land, affecting most of the Cape Town. Right. That was for 1.4.2. We're done. So we continue with question 1.4.3, which says, draw a labeled freehand cross-section through the chord front indicated as A in the diagram. Indicate the other elements preceding the chord front on the cross section. Draw freehand cross-section through the chord front indicated as A in the diagram. Right. So in the diagram, this is A here. It's our chord front. So let us draw a cross-section, let's say from A to B. That's the chord front. Right. And we indicate the other elements preceding the chord front on the cross section. All right. That's for 1.4.3. Okay. So we need to show a steeple pressure gradient. So this would be our chord front. And we know whenever the chord front approaches the home sector, whenever the chord front approaches the home sector, warm air rises. When warm air rises, it's going to condense. And it condenses, the formation of cumulonimbus clouds that are going to result in two heavy rainfalls. Right? So these clouds are referred to as the cumulonimbus. It's a long name. Call them cumulonimbus clouds. Cumulonimbus clouds. So there will be heavy rainfalls. Let us just say heavy rains. Heavy rains. Heavy rains. This would be the direction of air movement. So they move from west to east. So the cold sector, we're going to experience low temperatures. Low temperatures. Just to recap for question 1.4.3. So this is the cross-section of the cold front. As you can see, the steep pressure gradient. That's the cold front, cold sector, warm air rising, forming the cumulonimbus clouds. This is our warm sector, which has resulted into the warm air, where there are cumulonimbus clouds. So of course, there will be heavy rainfalls, and all of that. Right. Let us proceed to question 1.4.5, which says, explain how the weather system identified in question 1.4.1, which is a mid-latitude cyclone, resulted in the development of clouds at B. Right. So we could say, approaching cold front, causes warm air in the warm sector to rise up. The rising warm air condenses forming cumulonimbus clouds. Right. Like we mentioned in our cross section, if you can go back, like what I said, this is the cold front. So our cold front. When the cold front moves towards the warm sector, all the warm air is going to be forced to rise. So when warm air rises, it's going to condense, resulting into the formation of the cumulonimbus clouds. Right. That is for 1.4.5. Okay. Oh. Okay. Question 1.5, it says, refer to the infographic below on urban heat islands. As you can see, they're saying this is the graph or showing the different, also you can call it urban profile, showing the different land use zones where we have the CBD, the commercial area, the suburban residential, the rural areas, urban residential once again, suburban residential, the park, and the rural farmland. Then here, urban areas can sometimes have temperatures up to 15 degrees warmer than nearby rural areas. Cities are filled with more pavements and buildings, while rural areas have more greenery. Right. Now below is a temperature graph, which shows they show us the borderline surface temperatures during the day and air temperature during the day, surface temperature during the night, and air temperature during the night. Right. So you can see here during the night, surface temperatures, they rise, and certainly they rise here. Then the air temperature at night is below the surface temperatures. Okay. Then 1.5.1 says, what is the temperature? What is the temperature over the central business district in the temperature profile? The temperature profile diagram. What is the temperature over the CBD, which is the central business district, in the temperature profile diagram? Let's check. Temperature profile diagram. Okay. The temperature profile diagram, and they're saying it was asking the temperature over the CBD. So the CBD here, as we know, is total buildings. So if we check at the CBD, use a ruler here. Their lines showing this is 20. 21. This is our CBD here, which is 23. CBD is 23 degrees C, right? 23 degrees. Don't forget to indicate the degrees and the Celsius to indicate temperatures. 1.5.2, it says, according to the article, why will an urban heat island develop at A rather than C? Let's check again. The question says, according to the article, why will an urban heat island develop at A rather than at C? Right, let's check. So this is A. They're saying why are we going to experience urban heat island at A instead of C, right? But they're saying according to the article, right? So our article here, it says urban areas can sometimes have temperatures up to 15 degrees warmer than the nearby rural areas. Cities are filled with more pavements and buildings, while low areas have more greenery. Okay, I think we've seen some information there. So we could say 1.52, write it here. 1.52. Why cities? Why urban heat island will develop at A? I think we say because at A, comma, there are more pavements. There are more pavements compared to area C, right? So said at A, comma, there are more buildings than at C. I consider that at C, there are more greenery, yet too. So that's why the Urbanite Island will be more developed at A as compared to C, because we know pavements, they absorb more heat and retain it, which makes the urban area to be much more warmer than area C, where there are a lot of trees. At area A, there are more buildings, because the more the buildings, the more they create a surface area for a heat. Or we can also talk about buildings having a lot of bricks that absorb heat, glasses, metals which absorb heat, a lot of lights which create artificial heat as well. And then at sea, greenery, that means there's a lot of vegetation which includes trees which consume most of the heat in the rural areas, making it not to be warmer like in area C. Okay, so that is, so we done is 151, 152. We proceed to question 153, which says, give one reason for the lower temperatures experienced over the park at area B. Let's check area B. So area B, that is the park. You can see at the park, there are a lot of trees, which could be, for example, a green belt. See, because of the presence of so many of the trees. Anyway, so the saying, question says 153. Give one reason for the lower temperatures experienced over the park at area B. 153. Why area B would experience lower temperatures. So we could say a lot of trees which use the heat in that area to make it having lower temperatures, because most of the heat is being used by the trees or vegetation. As well as said, where there are trees, that means there's less concrete materials to absorb it, right? So that's what we could talk about at 1.5.3, right? 1.5.4, it says, reflect the temperature graph and give the reason why the temperature of the urban heat island is lower at night than during day. Okay. Why temperature of the urban heat island is lower at night than during day. Okay. This is 154. Okay. What the question was asking, why temperature of the urban heat island is lower at night than during day. So you could say lot of activities, from industries, a lot of artificial heat being generated or produced by cars, less during daytime, because we know during day, all of us in the urban area, which results into a lot of heat being produced or generated, and as well there are a lot of lights during daytime, which produces as well more heat during the day. Talk about a lot of activities from industries which could cause pollution, resulting into more heat being trapped by the greenhouse gases. We could as well say less activities at night, such as industrial production, at night the land uses heat, which is referred to as terrestrial radiation, so which could result in the temperatures in that area to lower down. Right. Okay. So 144, then 155, it says, explain in a paragraph how the development of features using natural materials in the cities can be used to reduce the urban heat island. Development of features, we talk about one, have rooftop gardens, on modern buildings, to cool down, or we could say to reduce. We could say to reduce on heat. That's one. It as well say let's check the question once again. It says, explain the paragraph of 8 lines how development of features using natural materials in cities can be used to reduce the urban heat island. I think a rooftop garden that is natural, having plants that are natural, right? As well talk about paint buildings with brighter colors that reflect heat, because we know that dark colors they absorb, but if you use brighter or lighter colors, They reflect the heat, making the area not to be too hot. As well, we can talk about the use of grass, thatched houses, instead of zinc. Also reduces which reduces on heat absorption, because we know the grass will not absorb heat if we compare it with zinc, because zinc, we know it does absorb. But if you use the grass-thatched houses, their rate of absorption is lower as compared to zinc, right? Talk about having more green belts, in cities, to utilize the heat, or to use up the heat, So this will reduce on the amount of heat in the city. Okay, yeah, I think for now, yeah, we can stick to those 4. Okay, so next is geomorphology. And question 2.1 says, various options are provided as possible answers to the following questions. Choose the answer and write only the letter A to D next to the question numbers. .1.1, the feature that develops at B, at the waterfall below, that is going to be a plunge pool, because we know the falling water will result into this area to be eroded, developing a plunge pool. 2.1.2, a natural levee is formed by A is out, because levees do not form by erosion. B, the deposition of sediments within the river channel. No, doesn't form within the river channel, which makes this be false. C, repeated deposition of sediments on the banks, because we know that natural levees forms at the river banks as a result of repeated flooding. It makes option C to be correct. 2.1.3, it says, a floodplain is an area in the dash of a river which experiences flooding during periods of dash discharge. So a floodplain is an area in the lower course. We know that a floodplain forms in the lower course, right? Lower course. This is out, can't form in the upper course during periods of need to be low, periods of high. Let's check. can't be high. It has to be during periods of low discharge, which makes option 1 and 3 to be correct. Wait. 2 and 3. It can't be low. It must be high. So which means this is out. So equals to option 1 and option 4, which makes our option D to be correct. Right. Then 2.1.4, braided streams develops in the river's lower course due to increased deposition, because we know when the river deposits materials in its own channel, the braids on the sand island will develop, creating braided streams. This is 2.1.4. Then we will proceed to 2.1.5. 2.1.5, which says identify the following fluvial feature. 2.1.5, terracing. We don't see things like this nature. With terraces or step-like features, instead we're just seeing horizontal landscape and steep area. This part, the meander, can see there's a feature of a meander, which this could be correct. There's no oxbow lake. It's not a source, because a source is not a fluvial landform, which makes our meander to be correct. As well, a terrace is a feature that forms due to rejuvenation. Right. 2.1.6, they say the following sketch represents the formation of cause 1. You can see they are showing us erosion, narrowing, meander, neck. So eventually, then this part has been cut off, which forms an oxbow lake. 2.17, a delta can be described as delta, a plain that forms at the mouth of a river caused by deposition, which could be correct. Let's check other options. The posts built up on the banks of a river. No, this is wrong. It doesn't form at the banks of the river. A plain that forms at the mouth of a river caused by erosion. No, it comes now because of erosion. The posts eroded from the banks of the river. No, so it makes option A to be correct, because the delta forms at the mouths due to deposition. Right. Next question, 2.2 says, refer to the diagram below, read the following statements and choose the appropriate ones in bracket to make the statements, which will make the statements true. Right. So 2.2.1, it says stream A is the captor stroke, the captured stream. Let's check after capture here. The stream A, so it makes stream A to be our captor stream. Captor stream. Why do you say captor stream? Because you can see it was able to erode through the watershed, as seen in this other diagram. Go all the way, and it was able now to still headwaters of another river. 2.2.2, lateral erosion or headward erosion is dominant at B, that's going to be a headward erosion, because we know this happens when a river erodes backwards through the watershed. It is able to capture another stream. Then 2.2.3, it says River C is identified as the misfit stream because it is too small for its valley, right? So it is a misfit because it is flowing in a large area, or it means that there is less water flowing, which means the river becomes too small for that particular area. 2.2.4, the elbow of capture at D is characterized by the 90 degrees or 45 degrees. It's going to be 90 because if you look at the elbow, it will be an elbow like this. Or as you can see it here, the elbow. Put nicely here, the elbow. So the elbow forms a 90 because if it was 45, it's supposed to be like this, 45. But an elbow forms a 90 degrees, so which makes 90 degrees our correct answer there. 2.2.5, E is known as the wind gap, because that is between the elbow of capture and the misfit. So which makes it to be the wind gap as the correct answer. 2.2.6, the possible cause of river capture is isostatic uplift or reduced discharge. When I say reduced discharge, this is the same as the less water, and we know the lower the water, the weaker the river. However, isostatic uplift will result into the velocity of the river to increase, making it able to erode through the watershed, causing the stronger river to capture the weaker river. So the isostatic uplift will be our correct answer. Number 2.2.7, after river capture, river A will increase its volume, of course, because river A is the capital stream, which means it gained more water volume after capturing the other river. Then 2.2.8, river C will have a larger stroke, smaller drainage basin after capture. It's going to be smaller because it lost its source. So it will be smaller, right? So we proceed to question 2.3. It says, study the following diagrams on the process of river rejuvenation. Right. So that's showing us rivers enters into the sea. This is the sea. This is our river. The meandering pattern. This is the sea. Because of course the sea, it is wider as compared to the river. The saying sea level drops and the river cuts into the flood plain, as you can see here. The sea level has dropped. The river continues cutting backwards. Right. Then 2.3.1, it says, let's check the instructions. So the following diagrams, all right. Choose the correct options in brackets. That is our instructions. River rejuvenation is when the erosive power of a river increases, resulting in an increase in vertical erosion. As we know, when the river gains more energy, it will start cutting downwards, which is the same as vertical erosion. 2.3.2. Determine the cause of river rejuvenation as shown in the diagram above. Okay. I think, as we all know, to be drop in sea level. Sea level. As you can see, here was friction. The moment it was dropping the sea level, the velocity of the river increased, which made it able to start cutting at the river mouth. In 2.3.3, explain how river rejuvenation results in the formation of river terraces. 2.3.3, explain how river rejuvenation results in the formation of river terraces. That is 2.3.3. Okay. So you could say a river gains more energy and erodes downwards, stroke vertically, then the previous floodplain will be left at a higher point, and a new floodplain develops. Forming terraces. Okay. So to question 2.3.4, identify the landform at B associated with river rejuvenation. Landform at B. This is our point B here, which could be waterfalls, rapids, or lake points. 3.4. Talk about waterfalls, rapids, and lake points. Any of those ones, because we know the river is cutting vertically downwards through the landscape, resulting into the formation of waterfalls, rapids, or lake points. 235. Describe how erosion causes landform B to retreat or to move upstream over time. 235. The question says, describe how erosion causes landform B to move upstream over time. Okay, landform B, which is a waterfall, rapids, or lake points. Right. This was our blank page. would say headward erosion with erosion removes the non-resistant layers due to undercutting of the non-resistant layers. Resistant layers will break away due to no support waterfall, then move upstream. So basically, here we are saying, for example, let's use this example here. This is our waterfall. And now the question is asking, why is the waterfall going to extend to this point here? See, because it used to be at point A, but it has now moved upstream to point B. What is causing this? So this happens basically where we have the non-resistant layers of rocks, and we have the resistant layers. So in most cases, the river keeps on eroding away the less resistant layers, and this is going to happen. See, see the resistant layers. Now, after this part being eroded away, this part used to have the less resistant layers, but after them being eroded away, and what happened? They are eroded away. So meaning that the resistant layers of rocks will have no support, and eventually they are going to break. This part breaks off. If it breaks off, it means now the waterfall is going to extend and to be at this point. It used to be at this point, but now it has moved backwards upstream to this particular point. So that's how we could explain that. Also could explain how the landform at B, or how the waterfall moves upstream. Right. Then we got 2.3.6, which says predict how the narrowing of the original floodplain will negatively impact agriculture activities. Okay, could say if the floodplain becomes narrow, that means less farming takes place. When there is less farming, it means also reduces on food production, because food security, challenges to access water from higher grounds. Therefore, we know that when the floodplain narrows, it means most of the area has been undercut vertically, resulting into less land available for farming, and as well it reduces on food production, causing food supposed to be food insecurity, not security, causing food insecurity. And as well challenges to access water from a higher ground, because remember before it used to be a flat land next to the river, but because of vertical erosion, the land has become steeper, meaning in those areas people struggle to access water. Right. Proceed to question 2.4. It says study the diagram below that shows the fluvial course of a river, the fluvial courses of a river, upper course, middle course, and lower course. Right. 2.4.1 says, would the flow in the upper course of the river be characterized as turbulent or laminar? And we know this would be turbulent. So turbulent occurs in the upper course of the river, where the river profile is ungraded due to a lot of temporary base levels of erosion being caused by vertical erosion. So the flow is going to be turbulent. The river does not flow over a smooth concave profile. Right. 2.4.2, provide evidence from the diagram to substantiate your answer to question. Why do we say it is turbulent? Which we just mentioned. Could say river flows over a steeper area. The river channel is not smooth. Not smooth. And as well, we could say there are a lot of temporary base levels of erosion in the upper course. Right. Then 2.4.3 define the term cross profile. In the cross profile, we look at the shapes of rivers at different stages. Profile showing shows shapes of river at different stages. That's why we're able to tell, able to see the V shape, the U shape, or the flat shape. Right. 2.4.4, it says, for the middle course and the lower course, which of the following course profiles represents the middle and the lower course? A middle course to be middle course will be C. This will be middle course, because you can see it is U shape, a bit wider. Then the lower course to be A. You can see it is very wide, less, very wide and shallow for A. So it means A is the lower course, then C is the middle course. Of course, B will be the upper course, because you can see it is very deep, forming a V shape. This will be our upper course. Right. Number B, describe the shape of the river valley in the middle and the lower course. 244B. For B, just a blue color. So describe the shape of the river valley in the middle and the lower course. Middle course would say it has a U shape valley. U shape valley, it has to be a U, not a V. So the U shape. Then the lower course, valley would say the wider U shape or open U shape. Alright, as we saw earlier, the lower course is almost very flat and very wide. The middle course forms a U shape, which is a bit deep. Okay. Then 2.4.5, it says, explain how fluvial processes throughout the river courses result in the formation of the valley shape of the lower course described in question 2.44b. Right. So our 2.44 says, I'll check the question once again. It says, explain how fluvial processes throughout the river course result in the formation of the valley shape of the lower course described in question 2.44.b. Okay. Okay. So let's see how the shape of Fluvial processes throughout the river course results in the formation of the valley shape of the lower course. So that lateral erosion eliminates the lower course, resulting into a wider U shape. Okay, as well, would say more deposition, of the sediments, the lower course causes the channel to be shallow, right? As well as say the speed or velocity decreases due to gentle gradient, causing more deposition. Okay. Or as well as say solid sediments in the upper middle course are deposited in the lower course. Right, just to add on something here, why the lower course has a wider U shape, like we said. This is our shape here, for example. This is our shape. This is the way different from this. This is a U shape. This is a V shape. So they're asking why the lower course has this kind of shape. And we said here, due to lateral erosion, because lateral erosion, when a river erodes its banks or its sideways, making the channel to be wider. So lateral erosion dominates the lower course, cause the lower course are resulting into a wider U shape or more deposition of the sediments in the lower course. In the lower course, in the lower course causes the channel to be shallow. Because you can see that this one is deep. Also, this one is deep. Actually, it was supposed to be like this, the middle course. See, and this one is very, very deep. The upper course. However, since our focus is on this, the lower course, we're going to say more sediments are being deposited in the lower course, causing it to be shallow and not deep. And number 3, the velocity decreases due to gentle gradient, causing more deposition. Because we know the steeper the gradient, the higher the velocity, but due to the gradient, the lower the velocity, so meaning the speed of the water reduces, which causes sediments to be deposited in the lower course. Okay. Proceed to question 2.5. Talks about study the information below on river management. Albanese River Healing Plan, a roadmap for African cities to cope with climate floods. Right. Just to go through the article. Water is the source of life, yet it is also one of the most terrifying forces of nature. This became clear during the recent torrential rains in Durban, when flood waters in 18 local river courses ripped away hundreds of informal houses and dozens of carefully engineered steel and concrete bridges. Instead of allowing the free flow of water, the accumulation of debris can turn bridges into the equivalent of dam walls. When that happens, the power of water is strong enough to smash down obstacles like bridges. Geoff Toll, P.1 senior manager for coastal stormwater and catchment management, estimates that more than 80% of the destructive river blockage in April was due to alien invasions and litter. Itken Mayor Police Kaunda says well-managed catchment areas provide over 4 billion in revenue for services to our city and its residents annually. These waterways are not only responsible for providing water, but they also help regulate the impact of heavy rains and floods if well managed. Right. Our first question says, define the term catchment management. Define the term catchment management. That is 5.1. Could say so I could say catchment management ensuring good use of rivers or drainage basins or proper use of rivers and ensuring that rivers are not mismanaged. Let's continue. Question 1.5.2. Identify the human contribution to the flooding in Durban from the article. Okay. let's check the article. The human contribution to flooding. Okay, so we will identify about litter, which is the same as pollution. Let's check again here. Okay, measure debris. Okay, right. So we talk about things like planting of alien plants, about litter as well. Litter which same as pollution. Then 12.5.3 use evidence from the pie chart graph to explain why the Etiquette municipality has found it challenging to maintain catchment areas. Okay, let's check ownership. So I could say the Etiquette only owns it only owns 23% of the Durban rivers. As you can see the pie chart, only owns 23, the majority is being owned by the private. Then 254. Why is the maintenance of the catchment areas financially important for the Etiquette municipality? I think we saw something here which says the Etiquette police council says well managed the catchment areas provided over 4 billion in revenue. So I could say well managed catchment areas provide well managed catchment area provides 4 billion in revenue. Then 255 in the paragraph the paragraph of 8 line propose 4 ways in which the Etiquette municipality can ensure that residents of Durban can be encouraged to assist in the catchment management. It's 255. Catchment management. So residents should be educated avoid building in or near rivers to create buffer zones. Create buffer zones to reduce encroach on rivers as well. Educate people about river catchment and management. River catchment and management. And as well create programs to ensure that rivers are kept clean and safe. Expansion of wetlands. Okay, etc.
The facing of a valley receive the most sunlight, which will be the north facing side. For this case, answer will be A. 1.1.3. In the southern hemisphere, the dash 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 in a valley is the south facing slope. In the southern hemisphere, once again, so that will be the shadow zone. The shadow zone in the southern hemisphere, the shadow zone in a valley is the south facing slope. What does that mean? It means that the shadow zone is being obstructed or does not receive direct heat. Therefore, it will have shade, or that side will be a bit much more cooler. That is why we say in the southern hemisphere, the valley will be the shadow zone. 1.1.4, katabatic winds occur at night due to terrestrial dash dash from the valley slopes. All of us know that during the night, the land loses heat through a process called terrestrial radiation, where the land loses the heat. This is one of the reasons why at night we do cover ourselves with blankets, because the temperatures seems to drop. When they drop, that means the heat, or sorry, the land is losing the heat through a process referred to as terrestrial radiation. Number 5, a temperature inversion occurs when a layer of cold air develops dash dash a layer of warm air. And all of us know whenever we talk about inversion, so that is a point where temperatures increases with height. Now, when they say a temperature inversion occurs when a layer of cold air develops dash dash a layer of warm air. So this is gonna be beneath. So a layer of cold air develops beneath a layer of warm air. So something like this. This is the cold air. Yeah, this is cold air. Then here we have the warm air. The warm air which forms our inversion. So that's why we say cold air develops beneath the layer of warm air. And number 6, dash dash is stroke are most likely to occur on the valley floor during winter. So on the valley floor during winter, they will form frost pockets in a valley. Like this, we know that whenever cold air subsides in the valley bottom, so it's going to collect at the bottom here, forming our frost pockets. All right, let's continue to question 1.1.7. Radiation fog in a valley is formed by the process of condensation of water vapor. Okay, so this occurs, we know condensation is a process whereby vapor changes into liquid again. So as air subsides to the valley bottom, this air is going to change from being vapor to liquid again, resulting into formation of radiation fog. But the process that results into that will be condensation, a process whereby water changes from gas to liquid. Okay, so that is question 1.1. Let us proceed to question 1.2, which says, study the figure below based on a cross-section of a tropical cyclone in the southern hemisphere. All right, this is our tropical cyclone. As you can see, it's being labeled A, there is C there. I can't see other labels, but we shall see what to do. All right. Question 1.2.1, it says, indicate the season in which this tropical cyclone could occur. And we know that tropical cyclones, they usually develop, we could say, late summer. That is when all the temperatures are way very high. We could say late summer or early autumn. Okay, early autumn. Yeah, this is when temperatures are very high to result into the development of a low pressure. So sometimes we avoid just saying summer because it is just summer. When summer is just starting, at times temperatures are very low. So that is why we prefer saying late summer or early autumn. That is when temperatures are way high to support the development of. Again, 1.2.2, it says, state the minimum ocean temperature required for the formation of this cyclone. And we know the cyclones, they require 26.5 degrees Celsius or 27 degrees Celsius. So those are the minimum temperatures that are required. When we say minimum, it means we can't go below that one. So it is from 26.5 going upwards. All right. 1.2.3, in which general direction would this tropical cyclone move? We know cyclones, they always move from, that's going to be east to west. Or we can as well say westerly direction. And I believe you know the reason for this, because they are driven by easterly winds. Driven by easterly winds. That's why they move from east to west, or they move to the west or westerly direction. Okay. 1.2.4, it says, name the cloud type found at A. This is at A here. This is at A, and you can see these clouds are huge and tall. All right. Now, what is the name of those clouds? And we know clouds are categorized into different. We have the cirrus, we have the nimbus, and all that. So, however, the huge and tall clouds are referred to as the cumulonimbus clouds. Cumulonimbus. The cumulonimbus clouds. Okay. Now, question 1.2.5, it says, state the precipitation likely to occur from cloud type A. Now, we know that the cumulonimbus clouds are associated with heavy rainfalls. I would say heavy rainfalls. Heavy rainfalls. We could say torrential rainfalls. Torrential rainfalls. We could say thunderstorm showers. Thunderstorm showers. Not showers, supposed to be showers. Thunderstorm showers, etc. So basically, we say heavy rainfalls, torrential rainfalls, or stroke thunderstorm showers. Okay. Question 1.2.6, is the air surface pressure at area C low or high? The air surface pressure at C, is it low or is it high? Let's go and look at C. So we are here. This is point C here. They're saying, is the air pressure at this point high or low? I think the first concept, we need to know that at this point, at point C, we see air converging, converging, air moves towards the same point. After converging, then it rises. Now, the mere fact that air rises, it means when air moves away from this point, a low pressure is going to develop. So that is why we say the pressure at C will be low pressure due to air rising or ascending at that particular point after converging. 1.2.7, would the airflow at C be described as diverging or converging? And I think I just explained that one in the previous question. So they're saying, would air flow at sea be described as diverging or converging? So remember, to diverge is when air moves away. It is to diverge, and to converge is when air moves towards the same point. So this is to converge. Now, if we check point C, if we check at point C, you can see that this is our air with black arrows indicating air moving towards this same point C, which means for our answer would be converging for question 1.2.7. All right. 1.2.8, at what stage of development will this tropical cyclone be when it moves over land? And all of us know that whenever cyclones move towards land, over the land, it means they will lose their energy. There will be less latent heat, times cooler conditions, inflow of dry air, which means the cyclone will be in its dissipating stage. We could say dissipating dissipating, or decaying, or degenerating stage. Or degenerating stage. Okay, so this is when they say it moves over the land, it's like the cyclone has reached the land. Whenever it reaches the land, there is friction. That means there will be less light and heat, less evaporation and condensation, which does affect its strength and as well making it to weaken, and eventually it will dissipate. All right, let us proceed to the next question, which says 1.3, for the infographic showing bare wind conditions over South Africa. Okay, so you can see this is our infograph. I see the map of South Africa here. There's this other written information on this other side. We have a graph here. So remember, whenever we talk about infographics, like it is information in form of graphic, which could be maps, charts, articles, and all that. So that is all about when we say infograph. All right. Let us try to look at the first question. They say, which season is being depicted in the diagram? Let's go back to our diagram. Which season? So this is going to be winter season. It's going to be winter season. We shall see, since they are already asking us to give evidence. So this is winter season. Now they say, provide evidence from the infographic to substantiate your answer to question 1.3.1. So we need to provide the evidence from the infograph. So it means whatever we are going to give, it must be gotten from the infograph. All right, let's go to the infograph to try to see or to show why we are saying this is winter season. Okay. Firstly, you can see that the high pressure cell is dominating the interior. You see the learners. So whenever you see this HH, it represents a high pressure, and that means it is dominating the land in winter. So this is typical of winter conditions. So we could say presence of the high pressure, presence of a high pressure dominating the interior. That is one evidence. As well, we can look for other evidences. Look at the position of the mid-latitude cyclone. See how where it is positioned. It means it has moved all the way from the southern and it moved to the northern area. That's why it was able to influence South Africa. So this usually happens in winter. So we see the cold front. I think let us try to use our blank page here. Check here, check here. Okay. All right, we are there. Question, that was question 1.3.2. Yes, so we said there is a high pressure cell over the land or dominating the land. Second, we said the cold front or mid-latitude cyclone has moved further northwards over the land. So let's check again for clarity. So you can see, like we mentioned, The cold front has moved further northwards over the land. Another evidence, we could as well look at the position of the high pressure cell. You see, this high pressure cell that we refer to as the Indian high pressure cell, it has well moved northwards. Normally, these high pressure cells in summer, they are situated a bit further away. Could be somewhere here. The MLC or the mid-latitude cyclone could be somewhere here in summer. Okay. Then in winter, they move in that direction. They move northwards, close or towards the land. So that's why we are saying we're now seeing the mid-latitude cyclone over the land here. We see the South Indian high pressure cell, which has well moved northwards over the land. Okay, so that's why we say, we could as well say the South Indian high pressure cell has moved further north. Okay, let's try to check the other evidences. We could as well talk about the big wind conditions. You can see this. This is a coastal low. This is a high pressure cell. So it means there's a pressure gradient here, meaning winds will be moving from the high pressure cell, the low pressure cell, high pressure over the interior to the low pressure cell over the coast, resulting into a development of the big wind condition. So we know that big winds as well develop during winter. So you could say there are big winds or big wind. Just say wind is fine. Big wind conditions which occur in winter. All right, dear learners. So that is for question 1.3. It's true. Okay. Let us proceed. Okay. So question 1.3.3 says, state two atmospheric conditions evident in the infographic that have resulted in the formation of big winds. Like I think we saw this in the previous question. They're asking what conditions does result in the development of formation of the big winds. All right, like we mentioned before, you can see move it. Okay, so you can see the big winds to develop mainly there must be a high pressure cell over the interior and a low pressure cell over the coast. So with this, there is a pressure gradient. That is why we say one of the conditions, there must be a pressure gradient as our factor, the first one. Pressure gradient. What is pressure gradient? It refers to where one area, or it refers to where the pressure is different between different places. That is, for example, here you see we have a high pressure over the interior and a low pressure over the coast. So this is what we refer to as pressure gradient. So this will hence result in the development of the winds, because we know that always winds, they move from a high pressure going to the low pressure. All right, so That is why we are going to say that there will be formation of big winds as a result of the pressure gradient. Secondly, can as well talk about the high pressure cell, high pressure cell over interior. Okay, as you can see here, this is our high pressure cell, which is the Kalahari high. So you can as well just say this Kalahari high pressure. Okay, or another factor, another condition, we're going to talk about the coastal law. The coastal law pressure cell, which is situated along the coast. So this is our coastal low pressure cell. This one here would be our coastal low. So because of the presence of the high pressure cell, like we've mentioned, the high pressure cell over the interior, the coastal low over the coast, the pressure gradient. So this does result in the development of the big wind conditions. Okay, 1.3.4, with reference to the temperature graph, explain the process of temperature change from 3 to 2 as big winds blow from the interior to the coast. So we need to look at the graph and try to explain what is happening regarding the temperature. So let's do the question once again. It says, with reference to the temperature graph, explain the process of temperature change from 0315 to 1400 as big winds blow from the interior to the coast. All right, let's check the graph here. They said from 0315, and as you can see, this is our temperature graph here. So this is three this line of, let me say this is the vertical line, which would be the longitude for that case. Then this could be, this is 315 somewhere here. Then they said from 315 all the way to 14. But you can see, imagine that it is you are here. It means I am climbing vertically. I keep on climbing. I climb. At this point, then I go down again. See, I continue to go down. You see this. So if it is with temperature, of course, this shows that at 3, the temperature started to rise. They kept on rising. You see, because you can see here, they were somewhere in 20 degrees C. They went to 25 degrees C. They went to 30 degrees C. They went to 35 degrees C. They went to 38. They reached 40 degrees. You see? Then again, at around 10, then they dropped. There's a sharp drop. Then here there was a gradual drop, you see, to 2 o'clock. So we are going to say, with the reference, let's use our blank page. This question 1.3.4. That T14, 15, the temperatures were rising. And this was due to the incoming hot winds. Okay, let's check again. So like we mentioned, Try to remove this. So, not 2, I said at O315, not 2. It's supposed to be O315. Sorry about that. It to be. This is O315, right? O315, temperatures were rising. Well, let's hear the question once again. With reference to temperature graph, explain the process of temperature change. I want us to explain why temperature was able to change from this to this. You see? And that's why here we said temperatures were rising, and this was due to the incoming hot winds, which are the big winds. And as well, we could say the temperatures kept rising. Temperatures kept rising as a result of a diabetic descending wind. So meaning that as winds were subsiding from the interior to the coast, they were warming up and drying up, therefore resulting into temperatures to keep on rising. Then we say somewhere we see the temperatures dropping. So you can see that again, from this is 10, right? From 10 to 14, there was a sharp decrease in the temperatures. So you could say 10 a.m. to 14 p.m. there was a drop in the temperatures. There's a drop in the temperatures. All right. Okay. Let's go back to our page. So now that was question 1.3.4. 1.3.5, they say a weather station located at A has reported clear skies. Account for this current condition. A weather station at A has reported clear skies. Let's look for point A. Okay, point A. So this is our point A here. That along this area there are clear skies. So when they say clear skies, it means there are less few or there are no clouds that are developed along point A. And this could be as well. Let's go to our blank page for question 1.3.5. 1.3.5 could say clear skies due to dry or hot winds resulting into less condensation. Remember, when air is dry, it means it will have low humidity, making or resulting into less condensation to take place, giving us clear skies. And secondly, could say as well subsiding air, subsiding hot dry air at point A results into clear sky. So we know that whenever air subsides, if I can illustrate it here, whenever air is subsiding, it means there will be no condensation here to happen. That means we're going to end up having clear skies. But whenever air rises, like for this case, if air rises, it means there will be condensation resulting into formation of clouds. So where there are big winds, it means there are clear skies as a result of dry hot air or subsiding hot air. See, that's why at point A it will have clear skies. 1.3.6, it says, explain why city A, which is situated on the east coast, will be affected by the release of fire warning. Explain why city A. Let's go check city A. Okay, so city A here, which could be Durban for our case. Durban. So this is Durban here at A. And they're saying, explain why city A, which is situated on the east coast, will be affected by the release of fire warning. Why are they going to issue fire warnings at city A? That is what the question wants us to talk about. Okay, let's go back to our blank page. Okay. Okay. Why are they going to issue fire warnings at city A? One, we could say to alert people at city A to be aware of the fire outbreak. Two, to ensure that people can evacuate away from that area. Another reason why they issue warnings there, to make sure, to ensure that people are not at risk of fire. So could say save lives. So they're going to issue warning to save lives for both people and animals. So to ensure that people do not do bush burning during big winds. As well say to ensure that people stock enough water case of dehydration, among other reasons. So that is why they are issuing warnings at city A, is to ensure all those factors and as well to make sure that people are safe. All right. So that was question 1.3.6. Let's proceed to question 1.4. It says, refer to the infographic below on mid-latitude cyclones. Okay. As you can see, that is somewhere here we can see there are mid-latitude cyclones here. There's some this other side. And see the map of Southern Africa here. You can see Madagascar. See, there's the high pressure cell here. There's another on this other side. See, like these are MLC, of course, there are low pressure cells. These are isobars. You can see in steep pressure gradient here. Okay, so there's a stationary model here. So always try to analyze the infographics and as well you read the information that is indicated. Okay, so let's go straight to the questions. 1.4.1, it says, what climatological evidence indicates that this mid-latitude cyclones is occurring in the southern hemisphere? Okay, what do we look at to ensure that this mid-latitude cyclone is situated or occurring in the southern hemisphere? Right. Firstly, we can look at the date. First, move all this, make it look more clearer. Okay, so you can see the date. Our date here is 9 June. And all of us know that 9 June, this usually happens in winter. See, 9 June in the southern hemisphere, it is winter season. This is when temperatures are very, very low. So one evidence to prove that this mid-latitude cyclone is in the southern hemisphere is by the mere date of winter. So the date showing winter in the southern hemisphere. So that's showing winter in the southern hemisphere because winter in the southern hemisphere that starts somewhere from May towards May, June, July, August. Yeah, that is plus still in winter season. So if we see June and we know that this is winter, you know, and this must be in the southern hemisphere. What other evidence? That was for 1.4.1. 1.4.1, we said that which shows winter in the southern hemisphere. Okay, which other evidence? Let's check. We can as well talk about the position of the mid-latitude cyclone. So you can see that they have moved further northwards. You see, this normally occur in winter. So the position of mid-latitude cyclone further north. See, and this occurs in winter. Let's go back to check again. So like I mentioned, Sorry about that. Erase that, remove all this. Like I mentioned, in winter season, the mid-latitude cyclone is always situated further northwards. See, they are moving further northwards, which is typical of winter, but in the southern hemisphere. Okay. Because we know that in the southern hemisphere, mid-latitude cyclones will be situated further northwards. So what other evidence can we give to prove that this is southern hemisphere? Remember, we need to be very careful with this question. It talks about climatological. Okay, wait for my pen to react. Okay. It's technology sometimes. So just to recap, we said 1.4.3, the stage was the mature stage. 1.4.4, the cross section, like we showed it here. This is the cold front, this is the cold sector, this is the warm sector. Then for 1.4.5, a group of tourists want to attempt the hiking trek to the top of the Table Mountain ahead of the cold front. And they're saying in a paragraph, approximately 8 lines, advise the organizers of the hike why the event should be postponed by explaining the expected conditions and possible impacts thereof. Okay, 1.4.5. So we need to look at the possible conditions and the impacts thereof. All right. Let's do like this. Sorry. Okay. So ahead of the cold front, we're going to say, because there will be overcast clouds. Starting into poor visibility. When it's too dark, it means the tourists might not be able to see properly. As well say the cold front lowers temperatures, making the area too cold and unbearable. Because whenever there is a cold front, temperatures will drop. You need to be very, very cold. And as well say tourists might catch flu or cold due to very low temperatures. The area experience resulting into poor visibility, as well say there will be heavy rainfalls. There will be heavy rainfalls which could trigger landslides or mudslides as well. Heavy rainfalls could result into floods, which might impact on tourists. I can as well say transport and communication. Will be disrupted, which could result into tourists getting lost. So among other factors. So just to recap, we said there will be overcast clouds resulting into poor visibility. The cold front makes temperatures to be very low and unbearable. Tourists might catch flu or cold due to very low temperatures or due to cold snaps. And the area will experience snow resulting into poor visibility as well. There will be heavy rainfalls, which could trigger landslides or mudslides. Heavy rainfalls could result into floods, which might affect on tourists. Transport and communication will be disrupted, which could result into tourists getting lost, among other factors. All right. So that is for that question. Let us proceed to question 1.5. 1.5. Okay. Refer to figure 1.5 below, showing a pollution dome. Excuse me. So they say define the term a pollution dome. So you could say a mass of polluted air, above the city. That's a pollution dome. As you can see here, this is the city. So you can see pollution taking place here. So all this now is a dome which has formed as a result of trapped pollutants in the warm or in the heat island, resulting into a pollution dome. So that is why we define it as a mass or a lot of polluted air above the city. Okay. 1.5.2, they say at night, the pollution dome is lower in elevation than during the day. Explain why this occurs. At night, the pollution dome is lower in elevation than during daytime. So explain why this occurs. Okay, so we're going to look at, let us try to use the blank page to illustrate the two. So this is a pollution dome at night. This is our step, for example. It's our city with tall buildings. This could be the CBD in the center. Then during day, so you can see the elevation at this one. During daytime, the pollution dome is way above the city, you see? But at night, it is way close to the city, you see? So what causes this? Why is it that during day, the pollution dome is way far away from the city, then at night is much more closer to the city? What could be the cause of this? Okay, so that's what we need to answer. Okay, let's look at the answers here. We could say that at night, due to terrestrial radiation, this is when the land loses the heat. Due to terrestrial radiation, the dome subsides close to the city. So at night, we know temperatures are low. Therefore, the dome cannot expand upwards. Instead, it will be contracting, moving towards the city or towards the surface as a result of cooler conditions. Secondly, at night, there is less convection currents. Less convection currents resulting into the dome to move close to the city. Okay. At night, we could as well say at night, there is a lot of pollution. Trapped in the air. Okay. So, so far, those are some of the reasons. Okay. As well say at night, there is a lot of subsiding air, pushing the dome downwards. Okay. Let's go to question 1.5.3. They say, state the environmental problem that results from a pollution dome which develops close to the surface in a city. Environmental problem. As well we know, there might be acid as the rain would form. Rain could form, and as well talk about the heat island, poor air quality. Okay, so there could be a formation of as the rain, development of heat islands, or poor air quality. Okay. 154. Describe how the environmental problem identified in the above question develops. Let's go to 154. Let's use our blank page. 154. About as the rain could form due to the reaction of water, gases, and pollutants above the city. So when those mix up, the chances of experiencing acid rain will be high. Then poor air quality will be due to pollutants trapped above the city. Then heat islands, their temperatures are rising due to heat being trapped above the city. So all this could result into those factors mentioned. Okay. 1.5.5, air pollution reduces the amount of a city's clean air at night. Explain this statement. 155. I could say that at night, there is less air blowing into the city to clean up pollutants. To clean up the pollutants. So we would as well say that at night there is too much pollution taking place. Also, you could say the pollution dome is situated close to the city. Is situated close to the city, among other factors. Okay, 1.5.6 provided two sustainable strategies that can be implemented that can be implemented in cities to minimize the effects of industries on pollution dome. Okay, to minimize, I think we have space here. We could say put fines to industries that do not respect regulations on pollution. So I could say to also to carry out decentralization or industrial decentralization. Industrial decentralization, so that industries are moved away to other areas. Again, okay, technology. Excuse me. Install filters in chimneys. To reduce on pollutants as well. Could say enforce programs regarding dangers of pollution. As well say advise industries to set up green belts so that they can consume most of the pollution. Also promote greener energy sources. So among others, so this could help in minimizing the effects of industries on pollution dome. Let us proceed to question 2, which is geomorphology, by either saying, they say refer to read the following statements and choose the appropriate words in the bracket that will make the statement true. Okay. An increase in rainfall in the middle course of the river valley will result in increased, because we know in the middle course of the river valley, usually there is more of lateral erosion. So I could say there will be more lateral erosion. But as well, even vertical erosion could as well be a correct answer, because we know the more the rainfall, the stronger the river, increasing its vertical and lateral erosion. So both options could be correct. 2.1.2, the amount of load that a river can carry is determined by its gradient. But the gradient refer to the steepness or the gentleness. So the steeper the gradient, for example, like this, so the river will be able to carry lots of sediment from upper coast down to the lower coast due to the steepness of the gradient. So 2.1.3, the volume stroke velocity of water is higher in the upper coast than in the middle coast. So I think we are going to say that the volume, that is the amount of water, and we know it is less in the upper coast. So this goes with velocity or the speed. So the velocity of water is higher in the upper coast than in the middle coast. Like, because we know that the upper coast, that's why it is very steep. So if water is flowing over a steeper gradient, its velocity is very high, meaning water will be flowing so fast. 2.1.4, the V-shaped valley in the upper course of a river is a result of vertical erosion, because we know when they say the V-shape, they are referring to this. See, and this is caused when the river is eroding, going downwards. When it goes downwards or vertically downwards, so it's going to result into the V shape. So that's why we say that will be due to vertical erosion. 2.1.5, at the mouth of a river, there is more deposition, which results in the formation of a delta. So what is a delta? Delta is a landform which develops due to deposition at the river's mouth. Okay. 2.1.6, lateral stroke vertical erosion in the middle course results in the migration of a meander downstream. We know that meanders cannot form because of vertical erosion. So instead, they'll form as a result of lateral erosion, because it means the river is winding side to side. 2.1.7, rejuvenation closer to the source of the river will result in more erosion stroke deposition in the lower course. So remember, rejuvenation is all about the river gaining energy. Therefore, there will be more erosion in the lower course. So it means it will start eroding the channel vertically after gaining strength due to more water, or due to gaining more energy. Okay, let's proceed to question 2.2, which says, below and refer to figure below and choose the correct letter that matches the description. Okay, so 2.2.1, it says drainage pattern that formed from rivers flowing into a depression or a lake. Okay, that's going to be F. As you can see, the streams are all flowing to one central point. Okay, we need to be careful between this one and this one here. With this one here, they are showing us, you can see the streams are flowing out. Look at this tributary joining, then it continues like that. Then here you can see tributaries are joining like this, and the river, they continue. They come, they join, then continue. They come, they join, then it flows. So they are flowing to the one central point. That's why 2.2.1 will be F. A drainage pattern formed from rocks of uniform resistance. We know that's going to be dendritic, which could be typical of A, because it looks like dendritic. Even I think it's not dendritic. Take A, as well take C. So, but the most appropriate one will be A. Okay. Two point 2.3, drainage pattern commonly found in melting ice regions. I think that is typical of G. which is the drenched, because you can see with drenched forms in glacial areas where streams do not have a clear pattern of flow. They are haphazard, you see. Then 2.2.4, a drench pattern that occurs on common slope down a linear mountain. That will be C. That will be C. That will be C. Okay, 2.2.4, a pattern that occurs on a common slope down a linear pattern. Then actually, if you look at 2.2.4, let's see. Sorry, 2.2.5, a drainage pattern that develops on alternate layers of hard and soft rocks. It has to be trellis, which is B. So 2.5, that would be B. Then 2.2.6, a drainage pattern that commonly forms on areas of volcanic mountains. That would be D. Areas of volcanic mountains, that would be D. Then 2.2.7, a drainage pattern formed where prominent ridges like lie parallel to one another. It has to be trellis, which is B, because with trellis, it looks like dendritic, though we look at the tributaries that are too short and they join the main, you see, too short. So with trellis, the tributaries are too short, which is going to be B. Oh, 2 point drainage pattern formed where prominent ridges lie parallel to one another. Let's check this question once again. Sorry about that. This technology. Okay. A pattern found where prominent ridges lie parallel to one another. That's gonna be C, which is a parallel pattern, right? Then 2.2.8, a pattern in which the main streams and their tributaries display many right angle bends. That has to be rectangular, which is E. Okay. 2.3, figure below shows a meandering river. You can see this is our meander. This is a feature here, the feature here. Okay. So what is a meander scar? So all of us know meander scar. A featured fluvial landform. Fluvial landform that forms when Oxbow Lake dries up. Okay. 2.3.2, in which stage of the river can a meander loop and a meander scar develop? I think they are more developed in the lower course. But as well, they could also give the middle course. The middle course. 2.3.3, name the slopes that will develop at X and Y of the meander loop. X and Y, so it's a bit dark. but this side is x, and this side is y. So at x will be the undercut slope. That's where the water flows so fast. So I could say x, the undercut, sometimes we call it the scarp slope. Then y, where the river deposits materials, that would be the slip of slope. 2.3.4, at which slope x or y will there be more deposition than erosion? Because we know the slip off, that's where the river deposits more. Okay, so it means to be it should be slope y, which is the slip off slope. So that is where there will be more deposition than erosion at slope y, due to slow movement of water. So the river can no longer erode, instead it will be depositing more materials at that point. Oh, this is a given reason for your answer. Would say there is low velocity the slope is shallow. So we talk about gradient. So all this will result into the river to deposit more materials than to erode. 2.3.6, explain how a meander scar is formed. I think when I use this space here, I would say, before we look at the meander scar, we need to understand Oxbow Lake. We say a river erodes the outer bank and deposits in the inner bank. Okay, then we say the meander neck is narrowed due to erosion which eventually breaks, is cut off, forming the Oxbow Lake. The Oxbow Lake eventually dries out, forming a meander scar. All right, let's proceed to question 2.4, which says start the figure 2.4 below on river capture. So they say define the term headward erosion. So we could define it, and we say depends when I'm gonna write it on top here. a river erodes backwards towards its source, lengthening its channel. That is headward erosion. Two 2.4.2, name one possible factor from figure 2.4 that could have resulted in river A capturing river B. River A, so that means that river A, this was our captor river, which was more stronger. So they are asking us to give one factor. So you could say, so that river A, I think let me use our blank page so that I have enough space. This is for question 2.4.2. So I could say that river A was flowing on less resistant enabling it to erode easily. Or you could say river A was flowing on steeper gradient making it more energetic. Or river A had a higher velocity and strength. Or river A had more water to make it more stronger. So these are some of the factors that could have resulted in river A to capture the other river. Okay. Question 2.4.3, explain how the process of headward erosion contributes to river capture. So 2.4.3. So you could say a river erodes backwards towards its source. The river is able to erode through the watershed and will steal the other area. So that's how you can explain how headward erosion could contribute to river capture. Okay. The next question, which is 2.4.4, give the geographical terms of features D and E, which develops from river capture. Features D and E. So you can see this is our feature D here after capturing. That's feature D there, which is curving. And all of us know a feature which curves, that you refer to it as the elbow of capture. Feature D, elbow of capture, where capturing took place. And feature E, you can see this area which has been left dry. You can see the river continues the other side, but then this area has been left dry, and we refer to it as a dry pen or a wind gap. So feature E is going to be our wind gap or a dry pen. 2.4.5, discuss 3 physical changes that will occur in River A as a result of river rejuvenation. So what's going to happen to River A? Would say its erosive power. Its erosive power will increase. Its energy and velocity will increase. It will erode more vertically. It will have more volume of water. More volume of water. It will develop various landforms such as rapids, to see, among others. Right. Question 2.5 below, which is an infographic on just K River catchment area. K River catchment area. Okay. Okay. So 2.5.1, they say define the concept river catchment area. So a catchment area, but as well define it area that supplies technology. Sorry about that. Okay, so I could say area I write it here at the bottom. Area that supplies a river with water. So 2.5.2 of which river is the Jaskai River a tributary? Let's go check through. So of which river is the Jaskai River a tributary? Okay, first. Okay. Of which river is Jaskai River a tributary? Okay, let's see. This is the dam on top there. There is a dam here. So this is Jaskai here. So this is an area. Chalami. So it comes, is flowing into which other river? So here they mentioned the Crocodile River. This is Crocodile River. So which means that this tributary, the Jaskai River tributary is flowing into the Crocodile River. That's why we say the Crocodile River. Okay. 2.5.3. The water quality of Jaskai River is deteriorating. Substantiate the statement by referring to the infographic. Why is it deteriorating? Okay, let's check here. One of Hautenge's largest rivers, the Jaskai, flows northwards, meandering through bed flowing into hydrotrophic spot dam. It's roughly 50 kilometers course through the city, inexorably marks it as a casualty of Johannesburg massive urbanization. Its ready waterways, a repository for the city's torrent of sewage, stormwater, litter, industrial waste, building rubble. For water expert Dr. Anthony, not only is the Jaskai one of the country's most polluted rivers, it is also one of the saddest. Its demise, he believes, is a metaphor for all what is wrong in our city. All right. So they say the quality of the Jaskai River is deteriorating. Substantiate the statement by referring to the infographic. Okay. I think we can focus on this point here, on this statement here. Let's talk about, so all the little points here. Why is water quality deteriorating? 253. Got it here. Three. Okay. Check. Testing one, two. All right, it's back. So 2.5.3. The water quality of Jaskai is deteriorating. Substantial statement by referring to the infographic. Okay, let's go back to 5.3. So remember, we had identified, they said, the torrent of sewage. So talk about sewage. sewage from industries, and homes that pollute the Jaskai River. Okay, that's one. Also identified also this other part here about urbanization. Check. So, excuse me. Urbanization, which has also resulted into high pollution of the Jaskai River, because we know when most people are running away from rural areas to come stay in cities, so at times this also increases pollution, which does affect most of the rivers. So talk about litter, another reason. Say the Jaskai River has been affected due to too much litter affecting its quality, affecting its water quality. Okay, what else could we talk about here? Okay. So among other factors, let's try to check if there's some other points here. Okay. So in a paragraph 2.5.4, in a paragraph of 8 lines, suggest possible strategies that can be implemented to deal with the problems identified in question 2.5.3. What can be done? 2.5.3. We'll say buffer around, buffer around river to prevent people strict laws and regulations regarding pollution of rivers, as we'll talk about environmental campaigns. Excuse me. Environmental campaigns to educate people, get people on importance of rivers. So rivers. So I'll talk about clinic campaigns to ensure that rivers excuse me, rivers are still safe and fix sewage pipes to avoid leakage into rivers. Also, okay, that is among others. First, take a glass of water, then I'll shower. Okay. Question 3: Geographical skills and techniques. Background. The coordinates. This was Howick is a town located in KwaZulu-Natal. The town is 1,050 meters above sea level, with warm summers and cool dry winters. Snapperjaw descends upon Howick when snow falls on the nearby Drakensberg. The town is located along the N3 freeway, connecting it with the rest of South Africa. The town is the location of Howick Falls, which is the large waterfalls that occurs when the Omgen River falls 95 meters over the Rarite cliffs on its way to the Indian Ocean. All right. Excuse me. So they say the first question, 3.1.1, in the topographical map index 2930SC, the 29 and 30 indicate. Let's check on our Howick map. Let's try to zoom in a little bit. Okay. So this is our 2930. And as you can see, 29 shows, 29 shows a latitude and 30 shows a longitude. I know the latitudes are numbered south, longitudes increases to the east. So which means answer for this case will be 29 latitudes and the 30 longitude, which is B. Howick Waterfalls is located in which province? Remember, as we read, Howick is a town in KwaZulu-Natal, which is supposed to be A. So always for such information, do not forget always to read through those given infos or infographics. Sometimes learners miss out on such easy questions. Okay, 3.1.3. What is the difference in height between spot height 1030 in block 3 and spot height 784? So for this case, the difference, just gonna subtract, and we say 784 subtracted from 1030. Then we get our calculator here, and we send our calculator. We say 1030 minus 7. Put it here, minus 784. So our answer will be Our answer will be 246 meters. 246 meters. Then 3.1.4, calculate the distance in meters between spot height 1030 and spot height 784 in block D4 on topographic map. So let's go in block E3 and block D4. The block E3, this is E1, E2, E3. So we are here. This is our spot height, which is 1030. And the D4, is it D4 or D5? Let's check. Yes, D4, which is 784 here. So which means we're going to measure from this spot height to this spot height. So what you do, you get your ruler and you measure in centimeters from the given spot to the other spot. But for this case, let us assume that we measured and let's say we got 6.2 centimeters as our distance. What do? We come here and we say 6.2 centimeters. We need to convert it to because this is the distance in meters to the scale, which will be 500 since we are using a topographic map. So 6.2 times 500. Go back to our scale. 6.2 times 500. Going to get 3,100 meters. Okay. Then 3.1.5, they say use the answers in equation 3.1.3. So 3.1.3, our answer is 246 meters. And 3.1.4, our answer is 3 meters. To calculate the average gradient in meters between the two spot heights. So what we do there, since we already have the distance, this was the distance here, then this was the difference in height. Okay. Difference in height. So what we do here, as our formula states, vertical interval over horizontal equivalent. So meaning our vertical interval, that is the difference in height, which is 246 meters over the horizontal equivalent, which is the distance in meters. Okay. So when you have everything in meters, then the figure on top divides by itself, divided by 246. And what you do on top, you as well do it at the bottom here, divided by 246. Then you say 246 divided into 246, that will be 1. Don't forget that our answer for gradient must be in a ratio. So it's going to be 1. Then 3,100 divided into 246 divided by 246. So our answer is 12.6 as our gradient. Okay. Then we proceed to 3.1.6. Choose the correct answer from the option provided below. Write only the letter A to the next to the question number. A cross-section of the slope between spot height 1030 in block E3 and spot height block D4 on topographical map is a cross-section. So let's go again to those blocks. Spot height 1030 in E3 and D4. E3 and D4. So you can see that at E3, 20 spot height, this area is gradual, is gentle. That's why there's been farming. But as you go to the other side, look at the contour lines there. The contour lines at this particular point, they are too close to each other, which shows a steeper gradient, right? Which means it could be something like this. Gentle, then becomes steep. Okay, let's check on our options here. So when you look at option B, you can see it is gentle, then it becomes steep. You see? That's why we're going to take number B as our correct answer. Give a reason, then you could say at E3, shows a gentle gradient and steeper at D4. Okay. Then 3.2, 3.2, refer to the valley at G in block B2 on topographic map. The valley at G in block B2. Let's check. Sorry about that. Block B2. Okay. The valley at G. So this is where we are at G. Block B2. All right. Choose the correct answer from those given below. Write only the letter to the number. The nocturnal or nighttime wind that develops during the night in this area is called, that will be katabatic winds, because we know that katabatic winds develop in the valley at night. Explain how wind promotes the formation of dense fog at G. So let's go back to our blank page. So you could say at night, cold air subsides at the valley bottom, forming frost. The cold air at valley bottom condenses below freezing point, forming the fog. Forming a fog. Okay, so that is how the winds, that is katabatic, will result in the formation of dense fog at G. Then question C, how development of fog in this area impact early morning traffic on the secondary road? Well, so consider this is our secondary road here, secondary road. And then they're saying that this is developed already. There's a lot of fog in this area. So how will it impact on the early morning traffic. So when there's too much fog, it reduces visibility, causing traffic to move very slow. Okay, go to question 3.2.2. Refer to the Umgen River in the south of the topographic map. South of topographic map. Let's go south. With Umgen River. Here, this is our Umgen River here. We got it. All right, so it moves all the way. This is Umgen River there. Somehow it falls there. All of this is Umgen River. Another tributary joining it there. Right. Okay. So I erase this for more visibility. Okay, so let's go back to the question. It says, in what general direction does the Umgen River flow? Let's check. So you can see that this side it is too steep, right? Too steep. And we know that rivers, they originate in steeper or from steeper areas, and they flow towards gentle places. So it means that this river was flowing, if we put our compass like this, our compass, it was coming from the northeast, going to the southwest. Why do we say southwest for this case? As I mentioned before, so the river do originate from higher areas. So this is visible by looking at the contour lines. I think you can see our contour lines are too congested here or close to each other, indicating steeper gradient. Again, the other side. But as we pass the Howick waterfalls here, as it continues this other side, you can see that the gradient becomes gentle. And also, you can see that now the meanders are more developed in this other side, which means that the river was flowing from the northeast towards the southwest. Okay. Okay. So that's why we say, that this river is flowing to the southwest direction. Write it down here. Southwest direction. Give evidence from the map to support your answer. Let's say gentle gradient in the southwest. So that is 132B. Gradient southwest. So steeper gradient in the northeast as well. You could see meanders in the southwest, flood plains in the southwest. Let's try to check those ones for clarity. You can see we have flood plains around this other area next to the river. Remember, flood plain is a flat land or a level area across the river, and in most cases that area is used for farming. So there's a flood plain. The other side, there are meanders that are more developed also in the southwest. Then the gradient is gentle again around this other area. That's why you can even see there are a lot of buildings, farming taking place instead of this other side. Then this other side you can see the gradient is too steep as a result of these contour lines. We still have very steep here. The evidence of waterfalls that are more common in the upper coast. So which means that it can't be flowing to this other side. So it is flowing like this, going to the other direction. All right. So that is for that question. Let's proceed to question 3.2.3. Identify the stream order at H in block F4 on topographic map. Block F4. F4. So this is at H here. Let's try to zoom it. Okay, so you can see at this point, this is H here. If we draw this stream nicely, you can see the other stream, this other stream, right? It means there is 1 and 1, which will give us a 2-order stream at H. Right to back. So meaning the order would be a 2-order stream. 3.2.4, landform 8 on the orthophoto map. Let's go to the orthophoto map. Okay, landform 8 on the orthophoto map. Let's check orthophoto map. Landform 8. Okay, landform 8, you can see contour lines steep on either sides. The second option is here, which could be either a spur, so it could be a spur or it could be a saddle. Identify the Fluvial feature at the base of the Howick waterfalls on the orthophoto map. Orthophoto map is at 9. Yeah, that looks like a pool, because they say under the question talks about the feature at the base of the Howick waterfalls. So we know that would be a plunge pool that develops when the falls erode downwards. 3 to 6. Refer the Fluvial form, of which the cross section above is illustration. So this would be a meander. Name the Fluvial process taking place at 10 and 11. So at 10, it will be deposition, because that is the slip off. Then at 11, it will be erosion, because that is an undercut. In 331, GIS, refer to block B1. Vector data is data that consists of points, lines, and polygons. Identify the following vector data in block B1 that relates to conservation. A point feature, block B1, that relates to conservation. This is B1 here. So we need to identify a point feature in block B1 that relates to, okay, let's see. Our map, is that clear? Let's try to zoom in and see. In B1, what do we see here? What feature? Yeah, based on our map here, I think because of the resolution, you can't easily see the lookout, can't identify a point feature there. But let's try a polygon. So polygon, so polygon that could be woodland. See, full of woodland, that is in block B1, which is woodland. Then refer to the Howick waterfalls in block E2. So they say the location of the Howick Falls at F in block E2 on topographic map is an example. The location that is going to be spatial data, because we know spatial data deals with the location of objects. So since they spoke about the location of the Howick Falls, that would be spatial data. Then 3.3, refer to Imgen River, which runs through the town of Kwamevena in block E1. Define the term buffering. This is drawing rings around a feature, or demarcating a zone around a feature. Demarcating a zone around a feature, that is buffering. So number B, do you think buffering was applied in the development of the town in block E1? Let's go and check. Block E1. Do you think buffering was applied in development? That's the question. Development of the town in block E1. Do you think buffering was applied here? We could say so, because at least the river is still being preserved. Otherwise, there will be no river there. Okay. But as well, I think let's go with a no, because let's say no, buffering was not applied. Give a reason. The town encroaches encroaches on the river. town encroaches on a river.
Hello, good day learners. Godfrey here to continue with the section that we left hanging, and that is the section for map work. Okay. And last time I was busy teaching or telling you regarding the interpretation of maps, calculations, application of geomorphology topic, and now today I want to look at other related concepts to the application. Now, when you're given a map extract, please learners first understand that the map will be having this kind of things. There is what you call reference. Reference is a key. It's the key that you're using to try to interpret what is on the map. And if you look at it clearly, one side is Afrikaans, another side is English. So for those ones who are understanding Afrikaans, you can use the other side, this side here. For those ones who are understanding English, you can use this side. But now I realize that some learners are struggling to understand what the key or the reference tries to refer to. Please listen, learners. It is very important to understand what the different symbols or conventional signs mean. A case in point, we have got this part here, this part here. We have got this part here known as the national road. And if you want to see what the national road shows this first part, which is blue in color. Okay. Then this other national route, it shows this other part, which is red in color. So when you're interpreting, you must know that this one, the first one is for the first line. The second one is for a second line. We have the arterial route. You can see that arterial route, there is one word. And if it's one word, you can see that it's completely one word. It's all red color with R in between, which means it's the arterial road. The main road, you can see it, same color. When you look at the secondary road, I want you to see the secondary road simply means this road that is having this kind of color. But now there is a benchmark. The benchmark is this symbol here that you see. Okay. Other roads, this one, and the bridge is that sign that is just on the other roads. Tracking and trail, you can see track and hiking trail, railway station, and the high railway station or siding. You can even see this black color here. So this is this symbol here, or this conventional sign is for a station. Embankment, you can see this is embankment here, and then you have the cutting, which is this other side. Okay, the power line. In other words, you can be in position to interpret these symbols. I want you to look here. Somewhere here we have got a post office. Okay, there is a police station and there's a store. Post office is P, police station is PS, and store is W. That is its conventional sign. A place of worship, school, and hotel. This is a place of worship K, school is S, and hotel is H. Now that is how you need to know to interpret the symbols. So the reference is basically assisting us to understand what is supposed to be on the map. So in this case, if there is anything that you do not understand and you just look at it, please don't just look at this reference as just given information just there. It's not irrelevant. It's very, very, very relevant for you to be in position to pass or to understand what the map means. So we must understand what each one imply about the mapped area. It's not only those symbols you see there. There are some other symbols. You can see these ones here. I know when you look at the kind of maps you have, in most cases, you will find that some symbols are missing. But in case you have been doing with these other maps, you see that a lot of symbols are existing. But now other symbols, you must be knowing them in your head, such that you can be in a position to interpret them nicely. Take an example. The national boundary and the beacon. See that? The national boundary, this kind of line here, and then the beacon, that other kind of line. Then there is a provincial boundary that looks like that. It's a bit different from this one. You see, these are 2 dots. These are 3 dots. You see that? So you don't take things for granted. Take everything very relevant. Take everything very important, such that you can be in a position work with it. We have here a water tower, a reservoir, and a water point. So this is a water tower, okay? A reservoir, this is a reservoir here, and then a water point. Water point is abbreviated with F. Then we have a coastal rock. So this symbol is for the coastal rock, and so on and so forth. So in other words, I wanted you to understand that in map work, every symbol, everything you see has got value. Okay, so you must be in position to interpret. So before you proceed with understanding both the geomorphology, the climatology, how settlement is applied, how economic geography is applied, please start by understanding what the reference means on the mapped area, such that you can know that this is this one is this one, this one is this one, and that will assist us to be in position to interpret what we have on the map. Okay. Like I told you that it is interpretation. All right, learners? It is interpretation. With interpretation, we must make sure that we apply all the theory that we have learned so that it can be seen on the map. Take an example. We have looked at the aspect, valley winds, climate, slopes, landforms, settlements, land use, and all that. So we must be in position to interpret all those aspects on the map. Okay, so I want you to look at this. What do you see here? Here, you can see the issue of aspect, valley winds, climate. You can all apply it here, and settlement by just mere looking at what each part is meaning. Take an example. Okay, that when you look at this kind of map, and when you check somewhere here, you can see that the contour lines here are depicting that this part here is steeper than these other areas, which is basically a slope, a steeper slope here compared to what is happening this other side. Okay, then here is a protected area, natural protected environment that can be a game park, a game reserve, and so on and so forth. So you must be in position to interpret that. When you look at this one, what do we see in terms of drainage? You can see that this is a high-lying area. So these rivers are all draining outwards, which forms a kind of a pattern drainage in geomorphology that we call the dendritic drainage pattern. And when you check somewhere outwards here, it's lower than what is happening here. Okay. Now, you can see this part here. I want us to be in position to interpret the economic activities. What do we see? When you see this, this is showing the cultivated land. Okay. And if they talk about the cultivated land, what do you expect? You expect activities like agriculture, you expect activities like farming, and so on that is likely to take place in that area. And to make it easy to understand, you can easily interpret that this cultivated land is basically located close to the dams, near the rivers and the furrows, meaning that they can easily have access from the dams to these farms, and they use it while practicing agriculture. Okay. Besides that, there are some other activities that we can look at here that we can think of. Take an example. If you see here, this is an excavation. Okay, that means there's some kind of mining taking place. In that case, okay, then you can also look at this place. That this place has got mining being practiced. Take an example. We have what we call the Western Platinum. Okay, Western Platinum mines, meaning that there is mining taking place in this area. In other words, this one can help us to interpret the economic activities that are taking place in this locality. Okay. Now, we go ahead and look at the aspects. All these ones are applications or interpretation of theory or map work with the different topics that we look at in geography. So, like I told you that all aspects we look at are applicable. Landforms, microclimate, farming, recreation, conservation, and so on and so forth. So when you check here, what do we mean by conservation? This is the basically the using of the protection of the environment or preserving of the environment for future use. When you take this area here, Maharisberg protected natural environment. So Maharisberg protected natural environment is basically a conserved area, meaning that conservation is taking place here. Okay. When you see the cultivated land, what does that mean? Maybe there is farming taking place here. And when you see that this is a little bit steeper, what do we look at? We can think of the slope aspects. Okay, we can also think of a microclimate, that the climate that is affecting very small areas. So in other words, all those ones are trying to assist us understand the interpretation of maps using the different topics. Okay, so learners understand that anytime, any day when you're writing your geography papers, you're going to find out that those topics are going to come your way. You must be in position to apply what you have looked at in theory. It is going to be very difficult for you to understand the concepts when you have not applied the theory, or when you lack knowledge in the theory. Take an example. When you look at this slope aspect and you check this side, there is a lot of green compared to what is happening this other side. Remember, when you talk about slope aspect, you look at where the sun is facing in relation to where the slope is facing in relation to the sun. Meaning that on the shadow zone, we said that that place is cooler. Okay, so if you're in the southern hemisphere, the south-facing slope is much more cooler than the north-facing slope. What does that mean? The south-facing slope can easily favor activities, can easily favor activities like the growing of forests because it's cool. Remember, trees need a cool environment. And when you check this other side, there's a lot of green this other side, and there's a lot of cultivated land this other side compared to what is happening on this other side. So I want you to be in position to apply. That is application. Okay, be in a position to apply. All right. Now, we can also apply other topics. Both settlement. Here we have what we call the shapes of settlement, landforms, land use, and topography. When you check around here on the maps, what do we see? We talk about the shapes of settlement. How many shapes do we have? We've got a lot of shapes. For example, the linear shape. Okay, that is when the settlement is along a line. A line like what? Like a road. A line like what? Like a railway line. A line like what? Like a river. So in this case, if you see a road like this, and there are settlements along the road, which settlement shape is more likely to be formed if it's along a line of a road? Okay, the line feature that would be there will be a road. And if you see this road, that means you will know that the kind of settlement shape is a linear settlement that is taking place. Okay, so besides linear, we have got what we call the star shape. Beside the star, we have got another shape like that is a circular shape. That is, for example, when the settlement is around the circular features like mountain, like lakes, and I understand. We have also what we call the semicircular shape. For example, at the coast, ocean side, you'll find that kind of settlement. Okay, so if they ask about the settlement pattern, what do you expect? Settlement pattern, I will look at the layout of settlements in an area, and you find out that it's either nucleated pattern or sparsed. Okay, nucleated or sparsed. If it's nucleated, simply means when the settlements are within one area. If it's sparsed, when the settlements are spread. So what will you see? You'll find out that there are some areas where you'll see a lot of settlement. Actually, you must know that these are settlements here. So if it is concentrated in one place, it's nucleated. If it is dispersed, or if it is they're spread away from each other, it is dispersed. Okay. Now, besides that, learners, we have also the interpretation in relation to the settlement types. Okay, we say the settlement types, that is rural or urban settlement. Then besides that, we have the settlement pattern, which we said that it is either nucleated pattern or nucleated, which is the same as clustered, or dispersed, which is the same as spread pattern. Then you have the street patterns. When we talk about street patterns, what do we see? We're looking at the way the streets are being arranged. Okay, and in this case, what do we see? Look at this, learners. We know that in our settlement, you must have looked at what they call, okay, in terms of settlement pattern, said we have nucleated, Okay, then you have what you call dispersed. And we'll talk about nucleated settlements close to each other. Then here is settlement far away from each other. Okay, so if you check on the map, do you see anywhere where the settlements are so close to each other in one area like that? So that one is going to form a nucleated settlement pattern. What about dispersed? Dispersed is going to form something like this when they are spread from each other. Okay, that is settlement pattern. Then the street pattern. Street pattern, we have basically there is grid. Okay, we have planned, but planned, we have planned regular and planned irregular. Okay, then in this case, if it's gridion, it forms kind of grids, squares, straight, and normally it is one way. So when you check around here, what do you see? You can start list here where they form a grid pattern. See that? Okay, and see maybe around here forms a grid pattern. Okay, then these other ones like this one is planned irregular. Then you have that one that is not having a proper shape, where the settlements are just spread. The roads are just put anyway. So that one is irregular. But when you check there, you'll see that there is one which is planned, there is one which is grid, and the one which is irregular or planned irregular and planned irregular. Check here. This is a very good example of grid street pattern. This is a very good example of grid street pattern. It's a very good example of planned regular. But if it is irregular, it simply means it is not making a proper shape. Take an example. This is unplanned street pattern, because the way they appear, streets are joined anyway, the way they want them to be. So that is interpretation of settlement. You are applying the concepts of settlement. And that settlement concept, remember, it is coming in paper 1, in paper 2, and the economic geography is also coming in paper 2. So climatology and geomorphology is the application that is coming in paper 1. So learners, get ready for those aspects. Be in position to interpret them, and then life moves on. So you need to pass as we expect. Okay, now, like I've been telling you that we have a lot of things to apply. We have those areas that are flat. We have those areas that are steep. And how are they applicable? How are they important? If you look here, learners, we have fields here. We have canals. We have rivers. What do they all do? They all provide water for the farmers. Okay? The dams, they also do the same. They store water that is used during the dry season. Okay, so please, I'm trying to show you some of the aspects. Now, we can also apply another concept somewhere here. I want you to look here. This place here, because of the nature of the contour lines, it simply means that it's a bit gentler. And that means a gentle slope encourages the development of transport routes for easy accessibility. Now, check here. There are a lot of roads that are running around or running along this area because it's a bit flat. I want you to look at what is happening this other side. Because of the nature of the contour line, somewhere here, it is very steep. Therefore, because it is very steep, it discourages the growing, the construction of roads. And the same thing that applies here. Okay, that's why you see there are many roads here. If you check the only road that is here, it is passing where it's a bit gentler. In other words, between the two high-lying areas. You see this is a mountain here, it's a mountain. So this one we shall call it a pass, okay, or a gap where the roads are passing. Okay. Now you can see that this road, maybe it would have a chance to just come direct through here if it wants to proceed, but it couldn't. Why? Because of the existence of the steep area. Therefore, the road tries to pass around so that it can connect to other areas, because those steep areas are very difficult to construct roads onto. So hope learners, you understand. Okay, we are still looking at interpretation. Whatever that I see that is really important for interpretation, I will please try to explain. Okay, there is another aspect that I also want to talk about that is related to interpretation, that is the direction of the rivers and the direction of the rivers. Okay, let me start from the direction of the rivers. Direction of the rivers, I want to use this river here. They can ask, what is the direction of this river here? Okay, I might not be having a name for it on this map, but maybe it will have a name. Now, let us use this as our example. Where does the river flow to? Do you think this river flows from the north to the south, or it flows from the south to the north? Who would have thought? But in real sense, this river is flowing from the south to the north. Why? Because of the dam wall. It's not having tributaries. Look at the dam wall. The dam wall is this side, and this is where the dam is, meaning that the water is flowing from here, then through the dam wall, it goes north. That is number one. Number two, which other evidence do you have to show that this river is flowing in a northerly direction? Is because of the nature of the contour lines or the gradient. Check here, learners. You see here is steeper, here is flatter, meaning that the river flow from a higher lying area to lying area. So this river cannot be flowing from this way, entering where it is mountainous. It can only flow from the side that is a little bit mountainous, going downwards. Because remember, a river is a flow of, or is water that swiftly flows from the source to the mouth under the influence of gravity. Okay, so this river cannot climb the mountain, and the river flows from a higher lying area to down or to downer areas. Now, besides this, there is something that I want us to apply still. Look at this other part here. When you check that part, which stage of river do you think? Which stage of the river do you think this river is called what? Schwarzkopf's river flowing to? Where does it flow to? And then the next question can be, which stage of this river? And then they can also ask some related aspects of river buffering, the buffering or the buffer zones. But before we reach there, let us start from here. When you look at this river here, look at the way the shape, the pattern is forming. It's forming this meandering pattern. And besides that, we look at the nature of the contour lines. It's not that so steep. And it is not that so flat. So when you look at this area, we understand that this river is in its last section. It's in the last course. So if it's in the last course, this is what we call meandering. Okay? And remember, in the meandering sections, there are some aspects we looked at. If it comes to meandering, remember, we looked at aspects like what? We looked at aspects of meandering. Then we looked at issues of the slip off. Then we looked at another issue of the undercut. And we know that if we talk about the undercut, what are we referring to? We are referring to the area that is experiencing erosion. When we talk about the slip off, we are referring to areas that are experiencing what? Deposition. Meaning that the slip off is what we refer to the outer, to the inner bend. Inner bend. And the undercut is what we refer to as the outer bend. Let us check on this river that we are having. If you look at this river that is flowing like this, meaning that as it keeps on curving and bending, we have the inside part, which we said is the inner bend. Therefore, this one is formed by deposition, and the outside bend, which is formed by erosion. So outside is erosion, inside is deposition. And you know, when you talk about erosion, what do we expect? We refer to the fast flowing water, Then we talk about dominant activity is erosion. Okay, we talk about the gradient being a bit steeper. Okay, and then the velocity, high velocity of water. Then when we talk about the inner bend, what do we expect? Gentle gradient. Here, we expect a gentle gradient. Okay, you expect aspects of deposition, slow flowing water, and then less velocity. Meaning that the inside bend, expect slip off as a slope, and therefore there is slow flowing water, more deposition. Okay, and the outer bend, which we said it's an undercut, that's where we have water flowing faster, and we expect the erosion to take place. The area is a bit steeper, that's why water is flowing faster, and that fast flowing determines also the velocity. Okay, so that is what we refer to as meandering or a meander. So a meander is a landform. Meandering is a process through which that landform of a meander is formed. Okay, so when we check somewhere here, we can still see another feature. Which feature is this one here? The feature that we are seeing here in this area is what we call a braided stream. What is a braided stream? This is a depositional feature. It's a depositional feature that forms when the materials are deposited in the river channel. Okay, meaning that since the river is in its last stage, it means it has got less power to erode, Okay, so if it has got less power to erode, that means it dodges the material and later reconnects. That's why you see this river is flowing like this. So this one rejoins, this one rejoins, and then the river keep on flowing to another destination. Okay, now that is what you call a braided stream. So the area that is adjacent to the river, this part here, is what you call a flood plain. Okay, is what you call a flood plain. So learners, you can be in position to interpret those aspects. You can see that somewhere here is flat. That's why you see the area has got even the marsh and fay, because the area is flat. It's having a lot of water that is sitting in that area. Okay. Remember, learners, don't forget, we are still looking at interpretation. And I am trying to put all the topics in the geography syllabus all together so that we can see how can each concept or how can the concepts be applied on what? On the map. Okay. If you see anything that you're not understanding, please feel free to ask questions or to leave a comment. I'll be in position to answer you. Okay, but in preparation for exams, please take note of everything and let us try to pass. Okay, now besides this, there are some other interpretation concepts that can be applied. Take an example. There is this area here that is a bit far away from the residential areas. Okay, this area has got very big buildings. It has got even the silos. What do silos do? Those are the ones they use to store agricultural products or food. Okay, now when you check here, you will find out that they are very big settlements here. They are very big buildings here. Okay, these buildings we can term them as industrial areas. And we can, what do we remember when we're talking about the industrial areas? First of all, industrial areas are meant to be far away from the settlements because of the noise. Okay. Industrial areas are meant to be in areas where the land is cheap and available, like large areas where those industries can be established. Okay, it is established close to the roads or communication lines. Okay, which you can see that there is a road here that is going, there's a road, and so on. Meaning that this industrial area is basically, an industrial area according to the interpretation of the diagram. Okay, now I want us to proceed and keep looking at other aspects. We are still looking at interpretation, learners. I told you today, at least I want to see the interpretation part. There's another time where I handled the calculations, and I know that I finished all those calculations. If there's anything that is remaining, please let me know. I'll re-handle it. But if there's nothing, we are still moving forward, and apparently I want us to look at interpretation. And as far as interpretation is concerned, we are almost done, because we have looked at all the possible ways in which questions can be asked in relation to the different topics that we have looked at. Okay, now here we go. We look at another area here on the map. What do we see? Do you see somewhere here? These are industrial areas. Okay, those are industrial areas. What do we remember? Like we mentioned above, that all those industrialized areas will be built, first of all, next to the major communication lines. Take an example here. There's a road here, 102. There's another one here. There is a railway line there. Actually, a lot of railway lines there. Okay, so these are industrial built-up areas, meaning that such industries discourage people to settle close to them because of the noise they make, the noise pollution. So people are staying basically far away from those industries. The reason why they are close to the main road is mainly because they need to transport, easy transportation of.
Please use the link below to get the notes, questions, and other videos. Don't forget to subscribe, like, and share to others for our daily new videos.
In microclimate, we said it means climate of a small region. And the small region is like what? Like valleys. So the valleys are experiencing a different climate. In this case, we're going to look at slope aspect and temperature inversion or inversion rupture rate. Okay, let us proceed and see what happens. Valley climate or the slope aspect, we're looking at the direction in which the slope is facing in relation to the sun. That is what we refer to as slope aspect, the direction in which the slope is facing the sun. So if you are in the southern hemisphere, what happens? I want you to look at this diagram. When you look at this diagram, you will find out that one side here is completely dry. On the other side, there is some kind of green. Why? Those are the aspects we need to ask. Why is it that it is experiencing such aspects? Remember, this diagram here that we have is from the southern hemisphere. And if this is the southern hemisphere, we have this side which is the north, and we have this side which is the south. Okay, so in this case, if the sun is overhead here, it is striking directly at right angles on this slope, which is facing the north. So this slope here, we call it the north-facing slope because it is facing the north altogether. So we have another slope here, which is facing the south. So on this slope that is facing the north, what do you see? The slope that is facing the north, you find out that it becomes warmer because it is experiencing direct sun rays. or direct sun insolation, which will not be the same if this sun strikes at this angle. You will find that this slope here is getting the sun late or at angles that are less than 60 degrees. Okay, so meaning that this slope will be cooler, and therefore we shall find out that this one is going to be warmer, but the slope that is not experiencing direct sun will be in the shadow zone. So because it is in the shadow zone, what will happen? It will be cold. Okay, it will be cold. Under slope aspects, we have many things that we're supposed to look at. For example, how is this influencing human activities? Okay, how is it influencing human activities like plantation or planting of trees or growing of crops or settlement itself? How will it influence it? I want you to understand, learners, that please don't forget, please remember this. We are saying that in the southern hemisphere, the slope that is facing the north is warmer than the slope that is facing the south. This slope here we see is facing the south. The slope here we see is facing the north. So the slope that is facing the north is warmer. Why? Because it is experiencing direct sun rays from direct sun insolation. Okay, which we say it is perpendicular. Perpendicular means right angles. And somewhere here, we see that this one is having it at is experiencing slanting angles of the sun. Therefore, it will be experiencing less sun, and which will make it lie in the shadow zone. Eventually, it will be cooler. Okay, we go ahead, and I want us to understand more of the slope aspect. So, when we understand the slope aspect, like I've explained here, what happens in the north and the south. In case you ask further questions like, how is this influencing human activities? We shall find out that in reality, if this place experiences more sun, there will be more evaporation on this other side. There will be more evaporation. So there will be that evaporation taking place here, which means there will be condensation, having more rainfall on this other side. So if we have more rainfall here, how is this important? This will assist basically for the farmers or people who are growing crops. They will grow their crops here, number one. Number two, those crops that do love a lot of sun, they will also be grown along this slope, which is north facing what? North facing slope, because it will be experiencing direct sun and it will be warmer. So even in human settlement, if you want to really settle on such areas, you cannot settle in the shadow zone. Why? Because the shadow zone is colder. No one would like to settle in the shadow zone because it is very, very cold. Everyone would love to stay where it is warmer, at least in this aspect of the land. If you are to grow crops, you are going to use this other side for only those crops that will have more of the sun. But if you're to grow crops that at least will have can persist or can survive in the conditions, even if they are cold, then they will be grown around here. However, the main activity that is likely to take place here is the plantation of trees. So trees love cool environment, moist environment, and also those crops that love a lot of moisture will be grown on this other side. But now this side will discourage human settlement because no one will want to stay where it is cold. That is how it is impacting on human activity. Now, there's something here that I want you learners to understand. The issue of inversion or temperature inversion. Inversion is coming from the word invert. Okay? Inversion is coming from the word invert. This is what is going to happen. I want you to look at these two aspects. We have what happens during the day when there is direct sun. We also have what happens during the night. I want you to look at this. One diagram will lead us to the other. During the day, there is direct sun insolation. This word insolation simply means incoming solar radiation from incoming solar radiation. Solar means sun. That means the heat that is coming from the sun. In this case of this valley, what happens is that the sun hits directly the valley slopes. So that the valley slopes get warmer, they absorb that heat during the day. Do you understand? The sun hits the valley slopes, and the valley slopes absorb the heat during the day. And when they absorb the heat during the day, meaning that the slopes are going to be hot. And when the slopes are hot, it simply means that we shall have a region of low pressure. But somewhere at the very bottom, we shall have cold conditions. Therefore, it's going to be high pressure. So winds move from high pressure to low pressure. That's why you're going to have winds moving up. But that is going to come when you're looking at the kind of anabatic and katabatic winds. In this case, I want you to understand what happens, the scenario that occurs during the day. So the scenario that occurs during the day is that when the sun hits the slopes get heated, they absorb the heat during the day. That is the land. What happens at night? At night, the land that absorbs the heat is now losing it through what we call the terrestrial radiation faster than what it could happen on the water bodies. So radiation takes faster if there's no clouds formation. So what will happen in the night surface? So when this heat is lost at night, what will happen? The slopes here are now getting colder. Why? Because they have lost the heat. So on losing the heat, the slopes are becoming colder, meaning that even the winds that are going to blow off these slopes are also going to get what? To get colder. Remember, we're talking about the rates at which the slopes are losing the heat. The sides of the slopes here are losing heat faster than the valley bottom, meaning that here heat is going to be lost at a faster rate, making it colder than what it will happen in the valley bottom. Therefore, we shall have some cold conditions here and we shall have a bit of warm conditions in the valley bottom. And what will happen? So if the winds that are blowing off the slopes are very cold, they become dense and heavy. Therefore, they will have to slope down the valley because they are too heavy. Remember, heavy winds slope down. So as they descend down the valley bottom, they are going to displace the warm air that was within the valley bottom. But remember, this scenario is now occurring at what? At night. So when this warm air rises, it is rising now from the valley bottom. But above here, there is descending cold air. It's a bit colder. And down here, because there is continuous descending of cold winds, it simply means that even the valley bottom is going to be colder. Therefore, the warm air is going to be trapped halfway the valley bottom. This line you see here. So the warm air is going to be trapped within here. And if this warm air is trapped within here, we are going to have a zone here of warm air. That is what we refer to as a thermal belt. But within this zone, temperature is going to increase with increase in height. Therefore, we shall refer to it as temperature inversion or valley inversion or negative Raps rate. So that is the occurrence of that is the scenario that is explaining the formation of inversion layers. Hope we are together, learners. If there is anything that you don't understand, please don't hesitate posing any question. We shall be in position to assist you at any time. Okay, when we log in. We also see another aspect. So we're done with that aspect. We also see another aspect which we call the valley winds. So this is what I wanted to explain last time, but I knew that we're going to find it somewhere in the front. So when you talk about the valley winds, we have basically two. The first one is the anabatic, and the second one is the katabatic winds. So when you try to refer to anabatic winds, this is basically occurring during the day. I want you to understand that anabatic are occurring during the day. So this happens. How is this happening? It's happening because the valley slopes are getting heated, and therefore, when they get heated, the slopes, because they are receiving direct sun insolation, they get heated. So it is a region of low pressure. As they get heated, they become warm. So when they become warm, in terms of pressure, it's a low pressure, and the valley bottom is not heated at the same rate like what happens on the valley slopes. Eventually, we shall have a pressure difference whereby we shall have a low pressure and high pressure. In that case, winds will move from high pressure to low pressure, making those winds rise up. Okay, so we say anabatic winds occur during the day as warm air rises, becoming as the day warm rising air becomes the valley slopes are heated by the insolation, and therefore the energy is coming from where? From the sun, like I explained prior. So I want you to understand that anabatic is day, but katabatic is night. Like I explained before, how does it form? When the valley slope is heated, it becomes warm, that is during the day, And when it becomes warm, suddenly it's a region of low pressure. But the valley bottom is not heated at the same pace or the same rate like the valley slope. Okay, therefore, in terms of pressure difference, at the valley bottom it will be high pressure and the valley slope will be low pressure. Apply pressure gradient, winds move from high pressure to low pressure. That's why they move upwards during the day. And what happens at night? At night, what happens is that when the slope cools, it loses the heat that it had absorbed during the day. So meaning that the slopes of the valleys are also going to get colder. And when they get colder, even the wind that is blowing off the cold region are also going to get colder. And we know that cold winds are heavy and dense. Therefore, they descend down the valley slope. As so happens, what will happen? We shall have the winds during the night descending towards the very bottom. And then further, it explains the formation of the inversion layer, frosty pockets as well. But we are going to explain that. Okay. So, how do we experience the thermal belt? What happens is that at night, cold air descends on the sides of the slopes and displaces or it pushes the warm air that had accumulated during the day. So cold air descends in the middle of the valley, cold air descending in the middle of the valley traps the warm air in the middle of the valley, creating a warm thermal belt. So only on nights when there is no wind to mix the cold air and warm air. Okay, so what will happen is that the inversion layer traps. The importance of the anabatic winds is basically it drives or it clears all the pollutants that were within the valley. It pushes it up. So what happens? Air closer to the ground is cooler than the air above it. And therefore, what happens on the calm nights? The upper slopes cool rapidly. So cold air sinks down the valley slope. The colder air is trapped under the warm air. So the temperature increases with altitude in a valley. Therefore, polluted air gets trapped and it cannot rise again. So it will be trapped within that area of the inversion. What happens again? There is another concept that I want to learn and to understand. It is here what we call the frosty pockets. Frosty pockets. Frost form when the temperatures go below the freezing point. They form when temperatures go below the freezing point. What happens in this case? Like I explained, what happens at night, when this cold air descends, the warm air in the valley bottom is also going to be displaced. So when the warm air is displaced, where does it go? It cannot surpass the cold air that is above. So it's going to be trapped halfway. But there is continuous descendance of cold air on the valley slopes. So the continuous descendance of cold air on the valley slope simply means that the valley bottom will only be occupied by cold air. So the valley bottom, as it is occupied by cold air, in that case, we are going to have frost forming because there is continuous descendance of cold air, and this descending of cold air will mean that the valley bottom, the temperatures will have to drop below the freezing point. Eventually, it will form frosts. Okay, so meaning that as this happens, there is this descending air, there is this descending air here. So the warm air that was at the very bottom is going to be displaced, moving up, but halfway of the valley, it will be trapped here. Remember, somewhere here, it's at night, we have got some descending cold air, we have the scenario of cold air. So somewhere here, this is where we have the temperature inversion. Therefore, what happens is that the warm air that was escaping or that was pushed out from the very bottom here is all going to be trapped within here. So within this zone here, temperature is going to increase with increase in height. So the continuous descending cold air in the valley bottom is going to result into the valley bottom having temperatures going below zero. And when they go below zero, frosts start forming. That is during the cold nights or during the winter period. Okay, the formation of frosts. We talked about the formation of frosts, and now after the frosts are formed in the valley bottom, the question is, you might want, or people might want to use the valley bottom for any other reasons. Okay, like planting of crops or settlement and so on and so forth. What will happen in the valley bottom? You will have to only plant crops that are resistant to frosts. And those crops are the ones that will be thriving very well in the valley bottoms. Because crops are sensitive to frosts, are planted on the higher slopes where it is a bit warm. Okay, so the scenario that I wanted to explain, that is explained in Canabatic and version layer, are these ones. So we have the descending air, which is cold and dense, displacing the warm air. The warm air can't surpass this sinking cold air, therefore it is trapped halfway the very bottom. So at least, as you understand here, this diagram explain this very well. You can see that in this case, you can see that there is heat that is lost on the valley slopes here. So when heat is lost on the valley slopes here, it means the valley slope is becoming cold. Therefore, the valley slope becomes the region of high pressure in terms of pressure. The valley bottom is not losing heat at the same rate like the slopes. Therefore, it will be a bit warmer here in the valley slope, meaning that we shall have low pressure here, shall have high pressure here. Pressure gradient will move from high pressure to low pressure. So when the warm air is displaced, that is what happens. Okay. So how do we utilize these slopes? In this case, the slope aspect. We said slope aspect is the direction in which the slope faces in relation to the sun. So if you are from the southern hemisphere, what will happen? The north facing slope will be warmer. So it will be used for you or for a farmer to plant crops and then for settlement. So what happens? In that case, houses will be built on those north facing slope in the southern hemisphere or in the middle of the valley because it is warm. Number two, you plant crops that are non-frost resistant in the middle of the valley or on the slope that is warm. Okay. What happens again? We also see that people in the valley can suffer from respiratory problems as pollution is trapped and it cannot escape. I think that is understandable. Look at this. When the pollution, if it is trapped here, and let me say, take an instance that you are staying on the valley slopes somewhere here, so you can easily suffer from respiratory problems, breathing problems, because of the fact that the pollutants can't escape. They are all trapped there. So you inhale them and that will cause diseases. Working conditions can be difficult in factories at night at the bottom of the valley. Why? Because the valley is extremely, extremely cold. Okay. Another thing is that at the bottom, you will plant only crops that will survive the conditions of frost. When it is very cold, you can plant only those crops that can survive the cold conditions. Okay, that is if you want to survive there. So solutions to the pollution problem. What do? You plant more trees to absorb pollutants, find the factories that are really polluting the environment, give incentives to those factories that have at least tried to manage or to solve or to control the pollution. Okay. Also introduce what we call the carbon tax. This carbon tax is like a tax that is given to maybe cars or owners of the cars or factories that are really contributing to pollution. So they pay a tax for that. Have torocumulus above the inversion layer that takes the pollutants out. Also rooftop gardens, that is basically planting the trees on the rooftop, and also use of clean fuels like unloaded petrol that will assist. Okay. So in this case, this is what we have been focusing on. This is another view of these aspects. Okay, another view of these aspects. So there are a number of difficulties. There are a number of different winds that blow in the very bottom. Like we talked about the anabatic, I would say these occur during the day, and then they are driven by heating of the slope, and therefore they go down the escarpment. So of these two diagrams, learners, I think you can identify. We said anabatic, it occurs during the day. Clearly, on the day you don't expect the moon. During the day, you expect the sun. So by seeing the sun even here, and you see the moon here, we said day is anabatic, night is katabatic. Another thing that you can look at to say day or night is look at the arrows. These arrows are pointing upwards. Okay, they are pointing upwards. That means upward movement or upward slope winds. These ones are pointing downwards from the slopes coming down. You can see that during the day when the sun hits the slopes became warmer. So when the slopes become warmer, there is evaporation, which is out into condensation, forming clouds. You can see in the diagram. Okay, and then this is the temperature inversion, like I explained last time, that temperature inversion, the ground gets cooler, they cool not at the same rate with the valley slope. So there will be warm air here in the valley slope. But in the valley slope, this warm air is supposed to do what? To rise up. Being trapped halfway the valley slope, that will result into the inversion there. Okay. Hope you understand, learners. Don't mix concepts. The difference between dew and frosts. Okay. So that is basically what I wanted you to understand. So in this case, we were looking at the valley slopes, or the northern hemisphere and the southern hemisphere. This is another version of the diagram. You can see that in this diagram, if this is this slope here is facing this north with south facing slope. You see, this slope here is in this case the north. This one is the south. Because they said this diagram is in the southern hemisphere, there is here direct sun insolation. You can see that here it's direct than here. The angle is not the same. What does that mean? This simply means, this simply means that if this is southern hemisphere and this slope by arrows is showing that it is receiving direct sun, which slope in the southern hemisphere receives direct sun? Is the north facing slope. Therefore, this slope here is facing the north, just like you hear the word north facing slope. The slope must be facing the north. So that simply means this is north, this is south. The slope is facing the north. So this slope is warmer. This slope here is facing the south. This slope here is facing here. So it simply means that this slope here is south. This slope here is north. So this slope is facing here. That is where the name comes from. So this slope, let me say this slope is X and this slope is Y. So slope X is facing the south. So this slope X, we call it south facing slope. This slope Y, we call it north facing slope because Y is facing the north. And we say that in the southern hemisphere, the north facing slope is warmer. Therefore, this Y, we call it north facing. Okay. Please don't mind about my pencil. My pen, I'm already a little bit struggling with this pen. So this slope here is X. So X is facing the south. Therefore, the name of this slope X will be south facing slope. And what I was talking about, that this south facing slope, this is where you can plant trees or forests. Why? Because it is cool and cool environment. It's cool, moist. You can favor the growth of trees. So here, this land use can be used for growing crops because crops love sunlight so much. Another thing, the slope will be warmer, therefore it will be good for settlement and all other human activities. Hope you understand, learners. Okay. We continue and look at the next slide. Slope aspect. In this case, I want you to look at this diagram. What do you see? We're saying south-facing slope hosts a thinner regolith cover. So the result of this shear erosion with somewhat less gill development than on the north-facing slope. Why? Because north facing slope is warmer. Therefore, you use it for activities like farming. And when you look at this grazing, most grazing posts are located on the warm slopes. So this is where you keep your animals. So there is evidence of increased vegetation reduction. Okay. And then we shall have the development, the gully development on this slope, surrounding this slope. So the result of this rapid concentration flows leading to gully erosion. So in this case, we are trying to explain the aspect in real reality. So no one will have to settle on the side that is cold. Everyone will have to settle on the side that is what? That is warm. Hope you understand, learners. Please let me also handle another aspect here. The second aspect that I want, or the third aspect that I want to look at, is what we call urban climates. Urban climates. So when you look at, in this case, we're looking at the climate that is experienced in urban areas. Okay, so under this, we're going to look at the characteristics. We'll look at the heat urban island, which I'll look at also other aspects as we proceed. So under this line, what do we get? We're trying to look at the instances or the aspects that are existing. In this case, when we look at urban heat island, what is the meaning? When you look at urban climate, what do we understand? We are understanding the climate that is existing in urban areas. Please, learners, and I hope you have seen this, that urban areas don't experience the same climatic conditions like it is in rural areas. Why? Because of a lot of reasons that are happening in urban areas than what happens in rural areas. Okay, so let's see. How do you see? And another thing, that how do you get the difference between rural areas and urban areas? Just in simple understanding, rural areas, what do you see there? You will see that rural areas have got a lot of farms, open land, trees, the houses are too small. You understand? Basically, that is explaining rural areas. When you go to urban areas, you will find that urban areas have got very tall buildings. Besides the buildings being tall, they are too congested, density, very many activities, cars, and so on and so forth. That is really existing in urban areas. So in this case, when you're looking at this urban climate, we are going to look at basically the scenarios or the instances that are occurring in urban areas, and we look at all elements that really define climate in urban areas. In this case, we're looking at temperatures, we're looking at rainfall, we're looking at humidity, we're looking at cloud cover, we're looking at speed of wind, and all those aspects will be analyzed. Okay, but before we reach there, heat urban island or urban heat island, what does it mean? Urban heat island is the situation whereby rural areas are cooler than urban areas, or urban areas are warmer than rural areas. Okay, so under this case, we are going to find out that urban areas are warmer. Why? That is the most important question. Why do we say that urban areas are warmer? There are a lot of reasons that we look at. For example, urban areas are warmer because number one, the artificial surfaces. Number two, urban areas are so busy. You understand? They have got a lot of activities, meaning that we shall have a lot of pollutants that absorb heat in urban areas. Limited water surfaces in urban areas. We also see that urban areas have got limited vegetation. Therefore, whatever pollutants that are raised in the atmosphere, there will be increased carbon emissions. And remember, plants are very important because they take in carbon dioxide and they release oxygen that helps to regulate the temperatures. No water sources in urban areas, that will all result into the increasing heat in urban areas. Look at this graph here that we have, that is explaining heat urban island. Here we have temperatures. Here we have the structure of the city on the Earth's surface. Down here, or somewhere here, we have the city, the central business district. As you move out, you have the rural areas, suburb areas, and so on and so forth. So what happens here? The main focus is this and the rural areas. You can see here, no vegetation. Here there is vegetation. No vegetation. Oh, if it's there, it is limited. No water sources. You can find water sources here. Okay. So in this case, the CBD here, or the towns or the cities, have got temperatures. Look at the readings, 33 or 34 degrees. But look at the rural areas. It is somewhere here in 30, somewhere here in 30, meaning that it's warmer in urban areas, it's cooler in rural areas. The question is, what I wanted us to understand is that why do we say rural areas are warm, urban areas are warmer, and rural areas are what? Are cooler. Number one, more pollutants. Like we said that urban areas are very busy. Cars, industries, we have other businesses, all those ones are polluting the environment. So wherever there is more pollution, that pollution in the atmosphere will result into increase in heat. And that increase in heat will make cities warmer, and which is not the same in rural areas because there are less activities. Another thing is that cities have got more industries. You know, more industries have got pollution passing out of waste pollutants, especially when they are producing goods. So those ones are all set into the atmosphere that will increase the heat, and there is few or little or no industries in rural areas. Another one is lack of vegetation. If you find vegetation in rural area, in urban areas, it's going to be in smaller areas. For example, a park, okay, or some trees that are planted along the roadside, which is not the same scenario in rural areas. Rural areas have got dense vegetation. You can find trees everywhere, vegetation everywhere. So that will mean that it will help to regulate the temperature as the trees take in carbon dioxide, which are greenhouse gases that could trap the heat in the atmosphere to increase the temperature. That's why rural areas are cooler and urban areas are warmer. Okay, lots of people, many cars that are passing out carbon monoxide, all increasing the heat or through the burning of fossils. Large dark surface areas. Remember, everywhere you go, tarmac roads, it's cemented pavings and so on. All those ones are trapping heat. We also have what we call the artificial surfaces. Artificial surfaces that are going to trap heat in urban areas. Besides that, I always add on the use of artificial surfaces like air conditioners in order to regulate the heat. They use air conditioners, but even air conditioners regulate increased heat. Number two, in urban areas, you find that their lights are ever on because they are down there in the basements or in buildings. They put on the lights that increase or that generate heat, making those areas warmer. Okay, we shall look at this city climate in details when we are looking at other aspects. So, in this case, I want us to look at what we call urban heat island. But now I feel we have a lot of things that we have not discussed. City climate, like for example, rainfall. We have only discussed at length the temperatures, but I want to discuss something that is related to rainfall. Remember, I told you that I want at length, you need to look at all the elements that are affecting temperature. That are affecting climate and weather in urban areas. So this one is only focusing on temperatures because we are looking at warmer alongside cooler rural areas. So in case, another aspect that I want us to look at before we go there, besides temperatures, there is rainfall. Okay, rainfall. We know that urban areas receive more rainfall than rural areas. Urban areas receive more rainfall than rural areas. Why? The question is why. The question is why. So how do we answer why? The why part of why urban areas are getting more rainfall is because of what we call hygroscopic nuclei. Those hygroscopic nuclei absorb the moisture that is now rising up in urban areas because of that insolation. So the hygroscopic nuclei absorbing moisture, they collect together at the condensation point, they form clouds, forming rainfall in urban areas. Remember, cities are very busy. there are a lot of particles that are raised in the atmosphere. So those particles are acting as hygroscopic nuclei that are collecting clouds, forming rainfall. So urban areas receive more rainfall than rural areas. Another thing that also we need to look at is pressure. In terms of pressure, urban areas have got low pressure than what? Than rural areas. Why? We have just said that urban areas are warmer. We know that when the temperatures are warm, okay, or hot, the pressure is low. So urban areas have got low pressure. That is number one, because of the high temperatures. Number two, because of the rising warm air. So the rising warm air leaves a low pressure on the ground. That's why urban areas have got low pressure, rural areas have got high pressure. So when you apply pressure gradient, winds blow from high pressure to low pressure. That means if urban areas have got low pressure somewhere here, and somewhere here we have got a high pressure. So what will mean that winds will move from high pressure to low pressure, meaning that as they reach low pressure, they are warmed up and they rise up in the sky or in the atmosphere, forming clouds to form rainfall. So as they move from, that means in terms of direction, winds move from high pressure to low pressure. In other words, they move from rural areas to urban areas. That is in terms of even wind direction is explained. But now when you explain the speed of wind, we shall find out that rural areas will have a high speed of wind. Why? Because rural areas have got open spaces, so wind can go anywhere. In urban areas, the speed of wind is a bit low. Why? Because the buildings that are too tall and too many act as obstructions and friction to the speed of wind. However, the wind is channeled within the buildings. That explains that the wind, the speed of wind within the building corridors is going to be very high, as it is all channeled in one area. The speed is going to be high within the channel of the buildings. But generally, urban areas have got low speed of winds. So in this case, I've explained temperatures, I've explained the rainfall, I've explained the pressure, I've explained the direction of wind, I've explained the wind speed, and I've explained the rainfall. Most aspects, even moisture. You can talk about moisture. As warm air rises, it has got a lot of moisture. Therefore, we have got high humidity in urban areas and low humidity in rural areas. So you can look at those aspects and try to apply all the aspects very well. That is basically what we refer to as city climate. Okay, the next aspect that I want us to look at is what we call heat urban island. So I prefer to start this heat urban island in our next lesson that we shall be having. Therefore, I will stop here for now. But in case of any questions, learners, please don't hesitate asking questions. You'll be assisted there and then, and you handle the questions. But basically, one day I'll come here and I'll see how we can answer questions, especially paragraph questions, and then we see how we can, because learners lose a lot of marks when they tell them to answer paragraph questions.
Learners, once again, so today we'll be looking at preparatory examination 2022 geography paper 1, which includes climate and weather and geomorphology. Our question today, we are starting with question 1, which is climate and weather, and below other questions. All right, so question 1.1.1, the slope dash is the angle at which the sun's rays strike a slope. So for this, it's supposed to be option number B, which is the aspect. Because as we know, the side which a slope faces, that side receives direct or receives more heat compared to the other side which doesn't receive the direct heat. So therefore, the slope aspect is the angle at which the sun's rays strike a slope. Right. 1.1.2, in the southern hemisphere, the dash facing slope of a valley receives the most sunlight? We are in the southern hemisphere. If I try to do this one quickly here, this is, sorry, that's a sketch. This is the southern hemisphere here. This is our slope. We have the north, we have the south. And we know this is the sun, which gives direct heat. So they say direct heat. That's why this side is going to be more warmer. The north facing side will be warmer and the south facing will be cooler. So we go back to the question. The southern hemisphere, the facing slope of a valley receives the most sunlight, which will be the north facing side. For this case, our answer will be A. 1.1.3. In the southern hemisphere, the dash 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 in a valley is the south facing slope. In the southern hemisphere, once again, so that will be the shadow zone. The shadow zone in the southern hemisphere, the shadow zone in a valley is the south facing slope. What does that mean? It means that the shadow zone is being obstructed or does not receive direct heat. Therefore, it will have shade, or that side will be a bit much more cooler. That is why we say in the southern hemisphere, the valley will be the shadow zone. 1.1.4, katabatic winds occur at night due to terrestrial dash dash from the valley slopes. All of us know that during the night, the land loses heat through a process called terrestrial radiation, where the land loses the heat. This is one of the reasons why at night we do cover ourselves with blankets, because the temperatures seems to drop. When they drop, that means the heat, or sorry, the land is losing the heat through a process referred to as terrestrial radiation. Number 5, a temperature inversion occurs when a layer of cold air develops dash dash a layer of warm air. And all of us know whenever we talk about inversion, so that is a point where temperatures increases with height. Now, when they say a temperature inversion occurs when a layer of cold air develops dash dash a layer of warm air. So this is gonna be beneath. So a layer of cold air develops beneath a layer of warm air. So something like this. This is the cold air. Yeah, this is cold air. Then here we have the warm air. The warm air which forms our inversion. So that's why we say cold air develops beneath the layer of warm air. Number 6, dash dash is stroke are most likely to occur on the valley floor during winter. So on the valley floor during winter, they will form frost pockets in a valley. Like this, we know that whenever cold air subsides in the valley bottom, so it's going to collect at the bottom here, forming our frost pockets. All right, let's continue to question 1.1.7. Radiation fog in a valley is formed by the process of condensation of water vapor. Okay, so this occurs, we know condensation is a process whereby vapor changes into liquid again. So as air subsides to the valley bottom, this air is going to change from being vapor to liquid again, resulting into formation of radiation fog. But the process that will result into that will be condensation. a process whereby water changes from gas to liquid. Okay, so that is question 1.1. Let us proceed to question 1.2, which says, study the figure below based on a cross-section of a tropical cyclone in the southern hemisphere. All right, this is our tropical cyclone. As you can see, it's being labeled A, there is C there. I can't see other labels, but we shall see what to do. All right. Question 1.2.1, it says, indicate the season in which this tropical cyclone could occur. And we know that tropical cyclones, they usually develop, we could say, late summer. That is when all the temperatures are way very high. We could say late summer or early autumn. Okay, early autumn. Yeah, this is when temperatures are very high to result into the development of a low pressure. So sometimes we avoid just saying summer because it is just summer. When summer is just starting, at times temperatures are very low. So that is why we prefer saying late summer or early autumn. That is when temperatures are way high to support the development of a tropical cyclone. Again, 1.2.2, it says, state the minimum ocean temperature required for the formation of this cyclone. And we know the cyclones, they require 26.5 degrees Celsius or 27 degrees Celsius. So those are the minimum temperatures that are required. When we say minimum, it means we can't go below that one. So it is from 26.5 going upwards. All right. 1.2.3, in which general direction would this tropical cyclone move? We know cyclones, they always move from, it's going to be east to west. Or we can as well say westerly direction. And I believe you know the reason for this, because they are driven by easterly winds. That's why they move from east to west, or they move to the west or westerly direction. Okay. 1.2.4, it says, name the cloud type found at A. This is at A here. This is at A. And you can see these clouds are huge and tall. All right. Now, what is the name of those clouds? And we know clouds are categorized into different. We have the cirrus, we have the nimbus, and all that. So, however, the huge and tall clouds are referred to as the cumulonimbus clouds. Cumulonimbus. The cumulonimbus clouds. Okay. Now, question 1.2.5, it says, state the precipitation likely to occur from cloud type A. Now, we know that the cumulonimbus clouds are associated with heavy rainfalls. I would say heavy rainfalls. Heavy rainfalls. We could say torrential rainfalls. Torrential rainfalls. We could say thunderstorm showers. Thunderstorm showers. Not showers, supposed to be showers. Thunderstorm showers, etc. So basically, We say heavy rainfalls, torrential rainfalls, or stroke thunderstorm showers. Okay. Question 1.2.6, is the air surface pressure at area C low or high? The air surface pressure at C, is it low or is it high? Let's go and look at C. So we are here. This is point C here. They're saying, is the air pressure at this point high or low? I think the first concept, we need to know that at this point, at point C, we see air converging, converging, air moves towards the same point. After converging, then it rises. Now, the mere fact that air rises, it means when air moves away from this point, a low pressure is going to develop. So that is why we say the pressure at C will be low pressure due to air rising or ascending at that particular point after converging. 1.2.7, would the airflow at C be described as diverging or converging? And I think I just explained that one in the previous question. So they're saying, would air flow at sea be described as diverging or converging? So remember, to diverge is when air moves away. It is to diverge, and to converge is when air moves towards the same point. So this is to converge. Now, if we check point C, if we check at point C, you can see that this is our air with black arrows indicating air moving towards this same point C, which means for our answer would be converging for question 1.2.7. All right. 1.2.8, at what stage of development will this tropical cyclone be when it moves over land? And all of us know that whenever cyclones move towards land, over the land, it means they will lose their energy. There will be less latent heat, times cooler conditions, inflow of dry air, which means the cyclone will be in its dissipating stage. You could say dissipating, or decaying, or degenerating stage, Okay, so this is when they say it moves over the land, it's like the cyclone has reached the land. Whenever it reaches the land, there is friction. That means there will be less light and heat, less evaporation and condensation, which does affect its strength and as well making it to weaken, and eventually it will dissipate. All right, let us proceed to the next question, which says 1.3, for the infographic showing bare wind conditions over South Africa. Okay, so you can see this is our infograph. And see the map of South Africa here. This other written information on this other side. We have a graph here. So remember, whenever we talk about infographs, like it is information in form of graphic, which could be maps, charts, articles, and all that. So that is all about when we say infograph. All right. Let us try to look at the first question. They say, which season is being depicted in the diagram? Let's go back to our diagram. Which season? So this is going to be winter season. It's going to be winter season. We shall see, since they are already asking us to give evidence. So this is winter season. Now they say, provide evidence from the infographic to substantiate your answer to question 1.3.1. So we need to provide the evidence from the infograph. So it means whatever we are going to give it must be gotten from the infograph. All right, let's go to the infograph to try to see or to show why we are saying this is winter season. Okay. Firstly, you can see that the high pressure cell is dominating the interior. You see, the learners. So whenever you see this HH, it represents a high pressure, and that means it is dominating the land in winter. So this is typical of winter conditions. So we could say presence of the high pressure, presence of a high pressure dominating the interior. That is one evidence. As well, we can look for other evidences. Look at the position of the mid-latitude cyclone. See where it is positioned. It means it has moved all the way from the southern and it moved to the northern area. That's why it was able to influence South Africa. So this usually happens in winter. So we see the cold front. I think let us try to use our blank page here. Check here, check here. Okay. All right, we are there. Question, that was question 1.3.2. Yes, so we said there is a high pressure cell over the land or dominating the land. Second, we said the cold front or mid-latitude cyclone has moved further northwards over the land. So let's check again for clarity. So you can see, like we mentioned, the cold front has moved further northwards over the land. Another evidence, we could as well look at the position of the high pressure cell. You see, this high pressure cell that we refer to as the Indian high pressure cell, it has well moved northwards. Normally, these high pressure cells in summer, they are situated a bit further away. Could be somewhere here. The MLC or the mid-latitude cyclone could be somewhere here in summer. Okay. Then in winter they move in that direction. They move northwards, close or towards the land. So that's why we are saying we're now seeing the mid-latitude cyclone over the land here. We see the South Indian high pressure cell, which as well moved northwards over the land. Okay, so that's why we say, we could as well say the South Indian high pressure cell has moved further north. Okay, let's try to check the other evidences. We could as well talk about the big wind conditions. You can see this. This is a coastal low. This is a high pressure cell. So it means there's a pressure gradient here, meaning winds will be moving from the high pressure cell, the low pressure cell, high pressure over the interior to the low pressure cell over the coast, resulting into a development of the big wind condition. So we know that big winds as well develop during winter. So you could say there are big winds, or big wind. Just a wind is fine. Big wind conditions. Which occur in winter. All right, dear learners. So that is for question 1.3. It's true. Okay. Let us proceed. Okay. So question 1.3.3 says, state two atmospheric conditions evident in the infographic that have resulted in the formation of big winds. Like I think we saw this in the previous question. They're asking what conditions does result in the development of formation of the big winds. All right, like we mentioned before, you can see remove it. Okay, so you can see the big winds to develop mainly they must be a high pressure cell over the interior and a low pressure cell over the coast. So with this, there is a pressure gradient. That is why we say one of the conditions, there must be a pressure gradient as our factor, the first one. Pressure gradient. What is pressure gradient? It refers to where one area, or it refers to where the pressure is different between different places. That is, for example, here you see we have a high pressure over the interior and a low pressure over the coast. So this is what we refer to as pressure gradient. So this will hence result in the development of the winds, because we know that always winds, they move from a high pressure going to the low pressure. All right, so that is why we are going to say that there will be formation of big winds as a result of the pressure gradient. Secondly, can as well talk about the high pressure cell over interior. Okay, as you can see here, this is our high pressure cell, which is the Kalahari high. So you can as well just say this Kalahari high pressure. Okay, or another factor, another condition, we're going to talk about the coastal low. The coastal low pressure cell, which is situated along the coast. So this is our coastal low pressure cell. This one here would be our coastal low. So because of the presence of the high pressure cell, like we've mentioned, the high pressure cell over the interior, the coastal low over the coast, the pressure gradient. So this does result in the development of the big wind conditions. Okay, 1.3.4, with reference to the temperature graph, explain the process of temperature change from 3 to 2 as big winds blow from the interior to the coast. So we need to look at the graph and try to explain what is happening regarding the temperature. So let's do the question once again. It says, with reference to the temperature graph, explain the process of temperature change from 0315 to 1400 as big winds blow from the interior to the coast. All right, let's check the graph here. They said from 0315, and as you can see, this is our temperature graph here. So this is three this line of, let me say this is the vertical line, which could be the longitude for that case. Then this could be, this is 315 somewhere here. Then they said from 315 all the way to 14. But you can see, imagine that it is you are here. It means I am climbing vertically. I keep on climbing. I climb. At this point, then I go down again. See, I continue to go down. You see this. So if it is with temperature, of course, this shows that at 3, the temperature started to rise. They kept on rising. You see, because you can see here, they were somewhere in 20 degrees C. They went to 25 degrees C. They went to 30 degrees C. They went to 35 degrees C. They went to 38. They reached 40 degrees. You see? Then again, at around 10, then they dropped. There's a sharp drop. Then here there was a gradual drop, you see, to 2 o'clock. So we are going to say, with the reference, let's use our blank page. It is question 1.3.4. That T14, 15, the temperatures were rising. And this was due to the incoming hot winds. Okay, let's check again. So like we mentioned, try to remove this. So we said at the 0315, not 2. It's supposed to be 0315. Sorry about that. It would be, this is 0315, right? 0315, temperatures were rising. Well, let's hear the question once again. With reference to temperature graph, explain the process of temperature change. I want us to explain why temperature was able to change from this to this. You see? And that's why here we said temperatures were rising, and this was due to the incoming hot winds, which are the big winds. And that's what we could say. The temperatures kept rising. Temperatures kept rising as a result of a diabetic descending wind. So meaning that as winds were subsiding from the interior to the coast, they were warming up and drying up, therefore resulting into temperatures to keep on rising. Then we say somewhere we see the temperatures dropping. So you can see that again, from this is 10, right? From 10 to 14, there was a sharp decrease in the temperatures. So I could say 10 a.m. to 14 p.m. there was a drop in the temperatures. There's a drop in the temperatures. All right. Okay. Let's go back to our page. So now that was question 1.3.4. 1.3.5, they say a weather station located at A has reported clear skies. Account for this current condition. A weather station at A has reported clear skies. Let's look for point A. Okay, point A. So this is our point A here. That along this area there are clear skies. So when they say clear skies, it means there are less few or there are no clouds that are developed along point A. And this could be as well. Let's go to our blank page for question 1.3.5. 1.3.5 could say clear skies due to dry or hot winds resulting into less condensation. Remember, when air is dry, it means it will have low humidity, making or resulting into less condensation to take place, giving us clear skies. And secondly, could say as well subsiding air, subsiding hot dry air at point A results into clear sky. So we know that whenever air subsides, if I can illustrate it here, whenever air is subsiding, it means there will be no condensation here to happen. That means we're going to end up having clear skies. But whenever air rises, like for this case, if air rises, it means there will be condensation resulting into formation of clouds. So where there are big winds, it means there are clear skies as a result of dry hot air or subsiding hot air. See, that's why at point A it will have clear skies. 1.3.6, it says explain why city A, which is situated on the east coast, will be affected by the release of fire warning. Explain why city A. Let's go check city A. Okay, so city A here, which could be Durban for our case. Durban. So this is Durban here at A. And they're saying explain why city A, which is situated on the east coast, will be affected by the release of fire warning. Why are they going to issue fire warnings at city A? That is what the question wants us to talk about. Okay, let's go back to our blank page. Okay. Okay. Why are they going to issue fire warnings at city A? One, we could say to alert people at city A to be aware of the fire outbreak. Two, to ensure that people can evacuate away from that area. Another reason why they issue warnings there, to make sure, to ensure that people are not at risk of fire. So could say save lives. So they're going to issue warning to save lives for both people and animals. So to ensure that people do not do bush burning during big winds. As well say to ensure that people stock enough water in case of dehydration, among other reasons. So that is why they are issuing warnings at city A, is to ensure all those factors and as well to make sure that people are safe. All right. So that was question 1.3.6. Let's proceed to question 1.4. It says, refer to the infographic below on mid-latitude cyclones. Okay. As you can see, that is somewhere here we can see the mid-latitude cyclones here. There's some this other side. You can see the map of Southern Africa here. You can see Madagascar. See, there's the high pressure cell here. There's another on this other side. See, like these are MLC, of course, they are low pressure cells. These are isobars. You can see in steep pressure gradient here. Okay, so there's a stationary model here. So always try to analyze the infographics and as well you read the information that is indicated. Okay, so let's go straight to the questions. 1.4.1, it says, what climatological evidence indicates that this mid-latitude cyclones is occurring in the southern hemisphere? Okay, what do we look at to ensure that this mid-latitude cyclone is situated or occurring in the southern hemisphere? Right. Firstly, we can look at the date. First, move all this, make it look more clearer. Okay, so you can see the date. Our date here is 9 June. And all of us know that 9 June, this usually happens in winter. See, 9 June in the southern hemisphere, it is winter season. This is when temperatures are very, very low. So one evidence to prove that this mid-latitude cyclone is in the southern hemisphere is by the mere date of winter. So the date showing winter in the southern hemisphere. So that's showing winter in the southern hemisphere because winter in the southern hemisphere that starts somewhere from May towards May, June, July, August. Yeah, that is still in winter season. So if we see June and we know that this is winter, you know, and this must be in the southern hemisphere. What other evidence? That was for 1.4.1. 1.4.1, we said that which shows winter in the southern hemisphere. Okay, which other evidence? Let's check. We can as well talk about the position of the mid-latitude cyclone. So you can see that they have moved further northwards. You see, this normally occur in winter. So the position of mid-latitude cyclone further north. See, and this occurs in winter. Let's go back to check again. So like I mentioned, sorry about that. Erase that, remove all this. Like I mentioned, in winter season, the mid-latitude cyclone is always situated further northwards. See, they are moving further northwards, which is typical of winter, but in the southern hemisphere. Okay. Because we know that in the southern hemisphere, mid-latitude cyclones will be situated further northwards. So what other evidence can we give to prove that this is southern hemisphere? Remember, we need to be very careful with this question. It talks about climatological. Okay, wait for my pen to react. Okay. It's technology sometimes. So just to recap, we said 1.4.3, the stage was the mature stage. 1.4.4, the cross section, like we showed it here. This is the cold front, this is the cold sector, this is the warm sector. Then for 1.4.5, A group of tourists want to attempt the hiking trek to the top of the Table Mountain ahead of the cold front, and they're saying in a paragraph, approximately 8 lines, advise the organizers of the hike why the event should be postponed by explaining the expected conditions and possible impacts thereof. Okay, 1.4.5. So we need to look at the possible conditions and the impacts thereof. All right. Let's do like this. Sorry. Okay. So ahead of the cold front, we're going to say, because there will be overcast clouds starting into poor visibility. When it's too dark, it means the tourists might not be able to see properly. As well say the cold front lowers temperatures making the area too cold and unbearable. Because whenever there is a cold front, temperatures will drop. You need to be very, very cold. And as well say tourists might catch flu or cold due to very low temperatures. The area will experience snow, resulting into poor visibility. As well say there will be heavy rainfalls. There will be heavy rainfalls which could trigger landslides or mudslides. As well, heavy rainfalls could result into floods, which might impact on tourists. I can as well say transport and communication. Transport and communication will be disrupted, which could result into tourists getting lost. So among other factors. So just to recap, we said there will be overcast clouds resulting into poor visibility. The cold front makes temperatures to be very low and unbearable. Tourists might catch flu or cold due to very low temperatures or due to cold snaps. And the area will experience snow resulting into poor visibility as well. There will be heavy rainfalls, which could trigger landslides or mudslides. Heavy rainfalls could result into floods, which might affect on tourists. Transport and communication will be disrupted, which could result into tourists getting lost, among other factors. All right. So that is for that question. Let's proceed to question 1.5. 1.5. Okay. Refer to figure 1.5 below, showing a pollution dome. Excuse me. So they say define the term a pollution dome. So you could say a mass of polluted air, above the city. That's a pollution dome. As you can see here, this is the city. The city. So you can see pollution taking place here. So all this now is a dome which has formed as a result of trapped pollutants in the warm or in the heat island, resulting into a pollution dome. So that is why we define it as a mass or a lot of polluted air above the city. Okay. 1.5.2, they say at night, the pollution dome is lower in elevation than during the day. Explain why this occurs. At night, the pollution dome is lower in elevation than during daytime. So explain why this occurs. Okay. So we're going to look at, let us try to use the blank page to illustrate the two. So this is a pollution dome at night. This is our step, for example. It's our city with tall buildings. This could be the CBD in the center. Then during day, so you can see the elevation at this one. During daytime, the pollution dome is way above the city, you see? But at night, it is way close to the city, you see? So what causes this? Why is it that during day, the pollution dome is way far away from the city, then at night is much more closer to the city? What could be the cause of this? Okay, so that's what we need to answer. Okay, let's look at the answers here. We could say that at night, due to terrestrial radiation, this is when the land loses the heat. Due to terrestrial radiation, the dome subsides close to the city. So at night, we know temperatures are low. Therefore, the dome cannot expand upwards. Instead, it will be contracting, moving towards the city or towards the surface as a result of cooler conditions. Secondly, at night, there is less convection currents. Less convection currents. Resulting resulting into the dome to move close to the city. Okay. At night, we could as well say at night, there is a lot of pollution. Trapped in the air. Okay. So so far, those are some of the reasons. Okay. As well say at night there is a lot of subsiding air. Pushing the dome downwards. Okay. Let's go to question 1.5.3. They say, state the environmental problem that results from a pollution dome which develops close to the surface in a city. Environmental problem. As well we know, there might be acid as the rain would form. As the rain could form, and as well we'll talk about the heat island, poor air quality. Okay, so there could be a formation of as the rain, development of heat islands, or poor air quality. Okay. 154. Describe how the environmental problem identified in the above question develops. Let's go to 154. Let's use our blank page. 154. About as the rain could form due to the reaction of water, gases, and pollutants above the city. So when those mix up, the chances of experiencing as the rain will be high. Then poor air quality will be due to pollutants trapped above the city. Then heat islands, their temperatures temperatures are rising due to heat being trapped above the city. So all this could result into those factors mentioned. Okay. 1.5.5, air pollution reduces the amount of a city's clean air at night. Explain this statement. 155. I could say that at night, tonight, there is less air blowing into the city to clean up pollutants. To clean up the pollutants. So we would as well say that at night there is too much pollution taking place. Also, you could say the pollution dome is situated close to the city. Is situated close to the city, among other factors. Okay, 1.5.6 provided two sustainable strategies that can be implemented in cities to minimize the effects of industries on pollution dome. Okay, to minimize, I think we have space here. We could say put fines to industries that do not respect regulations on pollution. So I could say to carry out decentralization or industrial decentralization. Industrial decentralization, so that industries are moved away to other areas. Again, okay, technology. Excuse me. Install filters in chimneys. To reduce on pollutants. as well, could say. Enforce programs. Regarding dangers of pollution. As well say, advise industries to set up green belts so they can consume most of the pollution. Also, promote greener energy sources. So, among others, so this could help in minimizing the effects of industries on pollution down. Let us proceed to question 2, which is geomorphology, by either saying, they say refer to read the following statements and choose the appropriate words in the bracket that will make the statement true. Okay. An increase in rainfall in the middle course of the river valley will result in increased, because we know in the middle course of the river valley, usually there is more of lateral erosion. So I could say there will be more lateral erosion. But as well, even vertical erosion could as well be a correct answer, because we know the more the rainfall, the stronger the river, increasing its vertical and lateral erosion. So both options could be correct. 2.1.2, the amount of load that a river can carry is determined by its gradient. But the gradient refer to the steepness or the gentleness. So the steeper the gradient, for example, like this, so the river will be able to carry lots of sediment from upper course down to the lower course due to the steepness of the gradient. So 2.1.3, the volume stroke velocity of water is higher in the upper course than in the middle course. So I think we are going to say that the volume that is the amount of water, and we know it is less in the upper course. So this goes with velocity or the speed. So the velocity of water is higher in the upper course than in the middle course. Like, because we know that the upper course, that's why it is very steep. So if water is flowing over a steeper gradient, its velocity is very high, meaning water will be flowing so fast. 2.1.4, the V-shaped valley in the upper course of a river is a result of vertical erosion, because we know when they say the V-shape, they're referring to this. See, and this is caused when the river is eroding, going downwards. When it goes downwards or vertically downwards, so it's going to result into the V shape. So that's why we say that will be due to vertical erosion. 2.1.5, at the mouth of a river, there is more deposition, which results in the formation of a delta. So what is a delta? Delta is a landform which develops due to deposition at the river's mouth. Okay. 2.1.6, lateral stroke vertical erosion in the middle course results in the migration of a meander downstream. We know that meanders cannot form because of vertical erosion. So instead, they'll form as a result of lateral erosion, because it means the river is winding side to side. 2.1.7, rejuvenation closer to the source of the river will result in more erosion stroke deposition in the lower course. So remember, rejuvenation is all about the river gaining energy. Therefore, there will be more erosion in the lower course. So it means it will start eroding the channel vertically after gaining strength due to more water or due to gaining more energy. Okay, let's proceed to question 2.2, which says below and refer to figure below and choose the correct letter that matches the description. Okay, so 2.2.1, it says drainage pattern that formed from rivers flowing into a depression or a lake. Okay, that's going to be F. As you can see, the streams are all flowing to one central point. Okay, we need to be careful between this one and this one here. With this one here, they are showing us, you can see the streams are flowing out. Look at this tributary joining, then it continues like that. Then here you can see tributaries are joining like this, and the river, they continue. They come, they join, then continue. They come, they join, then it flows. So they are flowing to the one central point. That's why 2.2.1 will be F. A drainage pattern formed from rocks of uniform resistance. We know that's going to be dendritic, which could be typical of A, because it looks like dendritic. Even I think it's not dendritic. Take A, as well take C. So, but the most appropriate one will be A. Okay. Two point 2.3, drainage pattern commonly found in melting ice regions. I think that is typical of G, which is the drenched, because you can see with drenched forms in glacial areas where streams do not have a clear pattern of flow. They are haphazard, you see. Then 2.2.4, a drainage pattern that occurs on common slope down a linear mountain. That will be C. That will be C. That will be C. Okay, 2.2.4, a pattern that occurs on a common slope down a linear pattern. Then actually, if you look at 2.2.4, let's see. So the 2.2.5, a drainage pattern that develops on alternate layers of hard and soft rocks. It has to be trellis, which is B. 2.5, that would be B. Then 2.2.6, a drainage pattern that commonly forms on areas of volcanic mountains. That would be D. Areas of volcanic mountains, that would be D. Then 2.2.7, a drainage pattern formed where prominent ridges like lie parallel to one another. That's to be trellis, which is B, because with trellis, it looks like dendritic, though we look at the tributaries that are too short and they join the main, you see, too short. So with trellis, the tributaries are too short, which is going to be B. 2 point drainage pattern formed where prominent ridges lie parallel to one another. Let's check this question once again. Sorry about that. This technology. Okay. A pattern found where prominent ridges lie parallel to one another. That's gonna be C, which is a parallel pattern, right? Then 2.2.8, a pattern in which the main streams and their tributaries display many right angle bends. That has to be rectangular, which is E. Okay. 2.3, figure below shows a meandering river. You can see this is our meander. This is a feature here, the feature here. Okay. So what is a meander scar? So all of us know meander scar. A featured fluvial landform. Fluvial landform that forms when Oxbow Lake dries up. Okay. 2.3.2, in which stage of the river can a meander loop and a meander scar develop? I think they are more developed in the lower course. But as well, they could also give the middle course. The middle course. 2.3.3, name the slopes that will develop at X and Y of the meander loop. X and Y, so it's a bit dark, but this side is X and this side is Y. So at X will be the undercut slope. That's where the water flows so fast. So I could say X. The undercut, sometimes we call it the scarp slope. Then Y, where the river deposits materials, that would be the slip of slope. 2.3.4, at which slope X or Y will there be more deposition than erosion? Because we know the slip off, that's where the river deposits more. Okay, so it means to be it should be slope Y, which is the slip off slope. So that is where there will be more deposition than erosion at slope Y due to slow movement of water. So the river can no longer erode. Instead, it will be depositing more materials at that point. Oh, this is a given reason for your answer. Would say there is low velocity. Low velocity. The slope is shallow. So we talk about gradient. So all this will result into the river to deposit more materials than to erode. 2.3.6, explain how a meander scar is formed. I think here, when I use this space here, I would say, before we look at the meander scar, we need to understand Oxbow Lake. We say a river towards the outer bank and deposits in the inner bank. Okay, then we say the meander neck is narrowed due to erosion which eventually breaks, is cut off, forming the oxbow lake. The oxbow lake eventually dries out, forming a meander scar. All right, let's proceed to question 2.4, which says start the figure 2.4 below on river capture. So they say define the term headward erosion. So we could define it, and we say depends when I'm gonna write it on top here. A river erodes backwards towards its source, lengthening its channel. That is headward erosion. Two 2.4.2, name one possible factor from figure 2.4 that could have resulted in river A capturing river B. River A, so that means that river A, this was our captor river, which was more stronger. So they are asking us to give one factor. So you could say that river A, I think let me use our blank page so that I have enough space. This is for question 2.4.2. So I could say that river A was flowing on less resistant enabling it to erode easily. Or I could say river A was flowing on steeper gradient making it more energetic. Or river A at a higher velocity and strength. Or river A had more water to make it more stronger. So these are some of the factors that could have resulted in river A to capture the other river. Okay. Question 2.4.3. Explain how the process of headward erosion contributes to river capture. So 2.4.3. So you could say a river erodes backwards towards its source. The river is able to erode through the watershed and will still the other area. So that's how you can explain how headward erosion could contribute to river capture. Okay. The next question, which is 2.4.4, give the geographical terms of features D and E, which develops from river capture. Features D and E. So you can see this is our feature D here after capturing. That's feature D there, which is curving, and all of us know a feature which curves, that you refer to it as the elbow of capture. Feature D, elbow of capture, where capturing took place. And feature E, you can see this area which has been left dry. You can see the river continues the other side, but then this area has been left dry, and we refer to it as a dry pen or a wind gap. So feature E is going to be our wind gap or a dry pen. 2.4.5. Discuss 3 physical changes that will occur in river A as a result of river rejuvenation. So what's going to happen to river A? Would say its erosive power. Will increase. Its energy and velocity will increase. It will erode more vertically. It will have more volume of water. volume of water. It will develop various landforms. As rapids, to see, among others. Right. Question 2.5 below, which is an infographic on Jaskei River catchment area. Jaskei River catchment area. Okay. Okay, so 2.5.1, they say define the concept river catchment area. So a catchment area, but as well define it area that supplies technology. Sorry about that. Okay, so I could say area. I write it here at the bottom. Area that supplies a river with water. So 2.5.2, of which river is the Jaskei River a tributary? Let's go check through. So of which river is the Jaskei River a tributary? Okay, first. Okay. Of which river is Jaskei River a tributary? Okay, let's see. This is the dam on top there. There is a dam here. So this is Jaskei here. So this is an area, Chalami. So it comes, it's flowing into which other river? So here they mentioned the Crocodile River. This is Crocodile River. So which means that this tributary, the Jaskei River tributary is flowing into the Crocodile River. That's why we say the Crocodile River. Okay. 2.5.3, the water quality of Jaskei River is deteriorating. Substantiate the statement by referring to the infographic. Why is it deteriorating? Okay, let's check here. One of Hautenge's largest rivers, the Jaskei, flows northwards, meandering through bed flowing into hydrotrophic spot dam. It's roughly 50 kilometers course through the city inexorably marks it as a casualty of Johannesburg massive urbanization. Its red waterways, a repository for the city's torrent of sewage, stormwater, litter, industrial waste, building rubble. For water expert Dr. Anthony, not only is the Jaskei one of the country's most polluted rivers, it is also one of the saddest. Its demise, he believes, is a metaphor for all what is wrong in our city. All right. So they say the quality of the Jaskei River is deteriorating. Substantiate the statement by referring to the infographic. Okay. I think we can focus on this point here, on this statement here. Let's talk about, so all the lot of points here. Why is water quality deteriorating? 253. Got it here. Three. Okay. Check. Testing one, two. All right, it's back. So 2.5.3. The water quality of Jaskei is deteriorating. Substantial statement by referring to the infographic. Okay, let's go back to 5.3. So remember, we had identified, they said, the torrent of sewage. So talk about sewage from industries and homes that pollute the Jaskei River. Okay, that's one. Also identified also this other part here about urbanization. Check. So, excuse me, urbanization, which has also resulted into high pollution of the Jaskei River, because we know when most people are running away from rural areas to come stay in cities, so at times this also increases pollution, which does affect most of the rivers. So talk about litter. Another reason, say the Jaskei River has been affected due to too much litter affecting its quality, affecting its water quality. Okay, what else could we talk about here? Okay. So among other factors, let's try to check if there's some other points here. Okay. So in a paragraph 2.5.4, in a paragraph of 8 lines, suggest possible strategies that can be implemented to deal with the problems identified in question 2.5.3. What can be done? 2.5.3. We'll say buffer around, buffer around river to prevent people strict laws and regulations regarding pollution of rivers, as we'll talk about environmental campaigns, environmental campaigns to educate people, get people on importance of rivers. Also, rivers. So talk about cleaning campaigns to ensure that rivers rivers are still safe fix sewage pipes to avoid leakage into rivers. Also, okay, that is among others. First, take a glass of water, then I'll shower. Okay. Question 3: geographical skills and techniques. Background, the coordinates. This was Howick is a town located in KwaZulu-Natal. The town is 1,050 meters above sea level, with warm summers and cool dry winters. Snapperjaw descends upon Howick when snow falls on the nearby Drakensberg. The town is located along the N3 freeway, connecting it with the rest of South Africa. The town is the location of Howick Falls, which is the large waterfalls that occurs when the Omgen River falls 95 meters over the Rarite cliffs on its way to the Indian Ocean. All right. Excuse me. So they say the first question, 3.1.1, in the topographical map index 2930SC, the 29 and 30 indicate. Let's check on our Howick map. Let's try to zoom in a little bit. Okay, So this is our 2930. And as you can see, 29 shows, 29 shows a latitude and 30 shows a longitude. And all the latitudes are numbered south, longitudes increases to the east. So which means our answer for this case will be 29 latitudes and the 30 longitude, which is B. Howick Waterfalls is located in which province? Remember, as we read, Howick is a town in KwaZulu-Natal, which is supposed to be A. So always for such information, do not forget always to read through those given infos or infographics. Sometimes learners miss out on such easy questions. Okay, 3.1.3. What is the difference in height between spot height 1030 in block E3 and spot height 784? So for this case, the difference, just gonna subtract, and we say 784 subtracted from 1030. Then we get our calculator here, and we send our calculator. We say 1030 minus 7. Put it here, minus 784. So our answer will be 246 meters. 246 meters. Then 3.1.4, calculate the distance in meters between spot height 1030 and spot height 784 in block D4 on topographic map. So let's go in block E3 and block D4. The block E3, this is E1, E2, E3. So we are here. This is our spot height, which is 1030. And the D4, is it D4 or D5? Let's check. Yes, D4, which is 784 here. So which means we're going to measure from this spot height to this spot height. So what you do, you get your ruler and you measure in centimeters from the given spot to the other spot. But for this case, let us assume that we measured, and let's say we got 6.2 centimeters as our distance. What do? We come here and we say 6.2 centimeters. We need to convert it to because this is the distance in meters to the scale, which will be 500 since we are using a topographic map. So 6.2 times 500. Go back to our scale. 6.2 times 500. Going to get 3,100 meters. Okay. Then 3.1.5, they say use the answers in equation 3.1.3. So 3.1.3, our answer is 246 meters. And 3.1.4, our answer is 3 meters. To calculate the average gradient in meters between the two spot heights. So what we do there, since we already have the distance, So this was the distance here. Then this was the difference in height. Okay. Difference in height. So what we do here, as our formula states, vertical interval over horizontal equivalent. So meaning our vertical interval, that is the difference in height, which is 246 meters over the horizontal equivalent, which is the distance in meters. Okay. So when you have everything in meters, then the figure on top divides by itself, divided by 246. And what you do on top, you as well do it at the bottom here, divided by 246. Then you say 246 divided into 246, that will be 1. Don't forget that our answer for gradient must be in a ratio. So it's going to be 1. Then 3,100 divided into 246 divided by 246. So our answer is 12,6. That's our gradient. Okay. Then we proceed to 3.1.6. Choose the correct answer from the option provided below. Write only the letter A to the next to the question number. A cross-section of the slope between spot height 1030 in block E3 and spot height block D4 on topographical map is a cross-section. So let's go again to those blocks. Spot height 1030 in E3 and D4. E3 and D4. So you can see that at E3, between the spot height, this area is gradual, is gentle. That's why there's been farming. But as you go to the other side, look at the contour lines here. The contour lines at this particular point, they are too close to each other, which shows a steeper gradient, right? Which means it could be something like this. Gentle, then becomes steep. Okay, let's check on our options here. So when you look at option B, you can see it is gentle, then it becomes steep. You see? That's why we're going to take number B as our correct answer. Give a reason, then you could say at E3 shows a gentle gradient and steeper at D4. Okay. Then 3.2 refer to the valley at G in block B2 on topographic map. The valley at G in block B2. Let's check. Sorry about that. Block B2. Okay. The valley at G. So this is where we are at G. Block B2. All right. Choose the correct answer from those given below. Write only the letter to the number. The nocturnal or nighttime wind that develops during the night in this area is called That will be katabatic winds, because we know that katabatic winds develop in the valley at night. Explain how wind promotes the formation of dense fog at G. So let's go back to our blank page. So you could say at night, cold air subsides at the valley bottom, forming frost. The cold air at valley bottom condenses below freezing point, forming the fog. Forming a fog. Okay, so that is how the winds, that is katabatic, will result in the formation of dense fog at G. Then question C, how development of fog in this area impact early morning traffic on the secondary road? Consider this is our secondary road here, secondary road. And then they're saying that this is developed already. There's a lot of fog in this area. So how will it impact on the early morning traffic? So when there's too much fog, it reduces visibility, causing traffic to move very slow. Okay, let's go to question 3.2.2. Refer to the Umgen River in the south of the topographic map. South of topographic map. Let's go south. With Umgen River. Here, this is our Umgen River here. We got it. All right, so it moves all the way. This is Umgen River there. Somehow it falls there. All of this is Umgen River. Even as a tributary joining it there. Right. Okay. So I erase this for more visibility. Okay, so let's go back to the question. It says, in what general direction does the Umgen River flow? Let's check. So you can see that this side it is too steep, right? Too steep. And we know that rivers, they originate in steeper or from steeper areas, and they flow towards gentle places. So it means that this river was flowing, if we put our compass like this, our compass, it was coming from the northeast, going to the southwest. Why do we say southwest for this case? As I mentioned before, so that the river do originate from higher areas. So this is visible by looking at the contour lines. I think you can see how contour lines are too congested here or close to each other, indicating steeper gradient. Again, the other side. But as we pass the Howick waterfalls here, as it continues this other side, you can see that the gradient becomes gentle. And also, you can see that now the meanders are more developed in this other side, which means that the river was flowing from the northeast towards the southwest. Okay. Okay. So that's why we say that this river is flowing to the southwest direction. Write it down here. Southwest direction. Give evidence from the map to support your answer. Let's say gentle gradient in the southwest. So that is 132B. Gradient southwest. So steeper gradient in the northeast as well. You could see meanders in the southwest. Flood plains in the southwest. Let's try to check those ones for clarity. You can see we have flood plains around this other area next to the river. Remember, flood plain is a flat land or a level area across the river, and in most cases that area is used for farming. So there's a flood plain. This other side, there are meanders that are more developed also in the southwest. Then the gradient is gentle again around this other area. That's why you can even see there are a lot of buildings, farming taking place instead of this other side. Then this other side, you can see the gradient is too steep as a result of these contour lines. We still have very steep here. The evidence of waterfalls that are more common in the upper coast. So which means that it can't be flowing to this other side. So it is flowing like this, going to the other direction. All right. So that is for that question. Let's proceed to question 3.2.3. Identify the stream order at H in block F4 on topographic map. Block F4. So this is at H here. Let's try to zoom it. Okay, so you can see at this point, this is H here. If we draw this stream nicely, you can see the other stream, this other stream, right? means there is 1 and 1, which will give us a 2-order stream at H. Right to back. So meaning the order would be a 2-order stream. 3.2.4, landform 8 on the orthophoto map. Let's go to the orthophoto map. Okay, landform 8 on the orthophoto map. Let's check orthophoto map. Landform 8. Okay, landform 8, you can see point valence, steep on either sides. The second option is here, which could be either a spur, so it could be a spur or it could be a saddle. Identify the Fluvial feature at the base of the Howick waterfalls on the orthophoto map. Orthophoto map is at 9. Yeah, that looks like a pool, because they say under the question talks about the feature at the base of the Howick waterfalls. So we know that would be a plunge pool that develops when the falls erode downwards. 3 to 6. Refer the Fluvial form, of which the cross section above is illustration. So this would be a meander. Name the Fluvial process taking place at 10 and 11. So at 10, it will be deposition, because that is the slip off. Then at 11, it will be erosion, because that is an undercut. In 331, GIS, refer to block B1. Vector data is data that consists of points, lines, and polygons. Identify the following vector data in block B1 that relates to conservation. A point feature, block B1, that relates to conservation. This is B1 here. So I need to identify a point feature in block B1 that relates to. Okay, let's see. Our map. Is that clear? Let's try to zoom in and see. In B1, what do we see here? What feature? Based on our map here, I think because of the resolution, you can't easily see the lookout, identify a point feature there. But let's try a polygon. So polygon, it's a polygon that could be woodland. See, all of woodland that is in block B1, which is woodland. Then refer to the Howick waterfalls in block E2. So they say the location of the Howick falls at F in block E2 on topographic map is an example. The location that's going to be spatial data, because we know spatial data deals with the location of objects. So since they spoke about the location of the Howick Falls, that would be spatial data. Then 3.3, refer to Mgen River, which runs through the town of Kwa Mevena in block E1. Define the term buffering. This is drawing rings around a feature or demarcating a zone around a feature. Demarcating a zone around a feature. That is buffering. So number B, do you think buffering was applied in the development of the town in block E1? Let's go and check. Block E1. Do you think buffering was applied in development? That's the question. Development of the town in block E1. Do you think buffering was applied here? We could say so, because at least the river is still being preserved. Otherwise, there will be no river there. Okay. But as well, I think let's go with a no, because let's say no, buffering was not applied. Give a reason. The town encroaches on the river. Town encroaches on a river.
In this question here, we have question number 1.1, which talks about the stable weather conditions over the interior of South Africa are due to the well-developed high pressure cell. Right, for us to realize stable weather conditions over the interior of South Africa, we understand that stable weather conditions are realized when we have the dominance of sinking air. When we have a sinking air, that is where we have fine weather, we have stable weather, which is an anti-cyclonic system. So in this instance here over the interior, when we are having stable weather conditions, we are having the dominance of the Kalahari high pressure cell. So for that question there, our correct response would be the item number D, which is the Kalahari high pressure cell. It's the one that contributes towards fine weather conditions over the interior. Right, we move on to the second question. Right, the dew point temperature at weather station A. If we check weather station A, you tend to find that weather station A is located here, there over the interior to the extreme west, close to the extreme west coast. So the dew point temperature, we are talking of the presentation of temperature on the synoptic weather map. We have two temperature readings, the one on top and the one at the bottom, meaning to say we have the air temperature, which is the maximum temperature, and the dew point temperature, which is the minimum temperature. So we take the least one, the smaller between the two, which means that is the negative 8 degrees Celsius. That becomes our minimum temperature, or our dew point temperature for that weather station. So our correct response in that question becomes response number item B, which is negative 8. Right, we move on to the next question, which is question number 1.13, which says the atmospheric air pressure at weather station B is dash hectopascals. Right, we try to check again on our synoptic map. We are seeing that station B is located here, and for us to figure out the pressure for this particular weather station here, it's not indicated for us. We need to use map interpretation skills. Right, we check the isobars closer to that station. Right, if we check our isobar here, we have an isobar with a reading of 1016 hectopascals, and we have our station B as we go to the north eastern direction. We also see that we have another isobar which crosses via this path here, which has got a reading of 1020. So if we check here our isobaric interval, it represents that it has a 4 hectopascal interval from 1016 to 1020, 1016 to 1020. That is a difference of 4 hectopascals. So if we can try to estimate before we even check on the responses, our response definitely has to lie within the range of 1016 and 1020. It should be between the values of 1016 and 1020, which will mean that it can only be 1017, 1018, 1019. Those are the possible responses for that particular station. So if we try to check on our responses here, definitely there's no response which coincide, or which is there are no two responses which definitely fall within the range of our responses expected. So the correct answer for that question comes as response number C, which is 1018 hectopascals for that question. Then we move on to the next question, which is question number 1.14, right, which talks about the low pressure cell at C is known as a dash low. Right. We go to our synoptic map and try to identify C. Our C is here. Right. If we see the location of our pressure cell there, we can actually see that the pressure cell is located along the coast, is along the coastline. And if you check on this extreme western side, we are over the Atlantic Ocean, and as we get to the eastern side, we are getting inland. So this low pressure cell is along the coast, is along the coastline here. So low pressure cells that we tend to find along the coast, we call them the coastal low pressure cells. So we check on our responses, and on our responses, the correct response there becomes a coastal low for that question, which means our item number D becomes the correct response. Right, we move on to number 115, which says the type of precipitation found at town D is dash. Right, we go back to our map and try to identify where town D is. Right, we check there. Our D is there, indicated by this letter, and is pointing to that symbol there. Right, what does that symbol mean? What is the type of precipitation indicated by that symbol? You can see D is pointing at a dot. Right, we have several symbols that are used in synoptic weather maps. We have symbols for different types of precipitation. We have symbols for fog, symbols for mist, symbols for hail, drizzle, rain, whatever form of precipitation, snow. They have different ways of presentation on the synoptic map. So for this one, for this dot here, the correct response is rain. That is the type of precipitation that is represented by that symbol on the synoptic map. So we check the response of rain. Right, we go to the next question. Right, the type of precipitation, to answer question number 1.15 is caused by, right, what causes the rain is, we want to look for the first item of the type of winds which will cause that type of precipitation. Definitely in that instance, when we talk of offshore and onshore winds, we are looking at offshore, we are looking at winds which are coming from land going over the water body or going over the ocean. And onshore, we are looking at winds which come from the ocean over the land. So definitely for us to have rain conditions, we need to have onshore winds. So we pick our item number 2. Then we look at the conditions of the winds which are onshore, conditions which are likely to cause rainfall. For us to have effective condensation taking place, we need to have warm and moist air. Cold and dry air has no capacity here to cause condensation, because if the air is dry, it means it doesn't have moisture. So we cannot have effective cloud formation and we cannot have rain formation. So in this instance, our item number 116, the correct response you are picking the response for onshore, and you are also picking the response for warm and moist, which gives us a combination at D with item number 2 for onshore and item number 4 for warm and moist, which gives us the response item D for that response for question number 1.16. Then we proceed to question number 1.17. Right, the evidence of backwinds, backwind conditions at weather station E is dash and dash. We need 2 conditions that suggest that there was a backwind on that particular weather station at E. Let's try to figure out from the station E. If you try to figure out a station E, you can see that the conditions there is clear skies. If you check there is no shading to indicate cloud cover on that station. And also if you check, the wind direction is a north-westerly wind. And if you also check the temperatures, the maximum temperature is 27, the minimum temperature is -9. So if you try to figure out on these conditions here, you want to figure out conditions that relate to the prevalence of backwind conditions on that weather station. We have noted that there is clear sky, there is no cloud cover here, and we have also noted that the maximum and minimum temperature is 27 and -9, and also the wind direction is a north-easterly or northwesterly wind and at 30 knots. Right, so if we go to our responses, we want to try and figure out the conditions that are most likely to have caused the wind, the conditions to be having backwinds. Right. Clear skies, we have noted that the weather station is resembling clear skies. There's no shade which represents any form of cloud cover. It's a valid response. General winds, we cannot talk of general winds. We have seen that the wind speed was at 30 knots. Which is not general in that instance, which means the response item number 2, we are phasing it out. Then we also talk of a large temperature range. If you see the temperature range on that weather station, we had a minimum of -9 and a maximum of +27, which resembles that there was a very big temperature range. There was a very wide temperature range of 36 degrees Celsius. And the implication is such that the conditions before the coming of the backwinds, it was extremely cold with a temperature of a minimum of -9, and then with the coming of the backwinds, the temperatures rose from that minimum until they got to a higher temperature of 27 degrees. So a large temperature range is a possible response. Then southeasterly winds. The wind direction, we've seen that is not even a southeasterly wind, so we are phasing out the last response. So the remaining response is clear skies and a large temperature range, which gives us a combination of item number 1 and item number 3. The combination falls at option number A, which is the correct response for that question number 117. It gives us the response at A. Right. That was question number 1 1.1. Then we proceed to item number 1.2. Basically, it's a question which is based on urban climates. Right. And before you figure out the questions, we need to familiarize with the concepts of urban climates and how the climate conditions are modified by the urban environment. Because you remember, an urban climate is a micro climate, which means it's a unique climate for a particular geographical region, for a particular smaller geographical space, which is an urban setting. So there are different factors that shape and that determine the climatic conditions that are realized in an urban settlement. Right, now let's look at the questions. We got question number 121. Slopes in a valley facing the equator are warmer because the area covered by insolation is dash, with the responses Y and Z being smaller and greater. Right, here we are looking at, for the perspective of the southern hemisphere, we are saying we are referring to the north-facing slope or the southern slope. The north-facing slope in the southern hemisphere is the one which is facing towards the equator. And if you are looking from the northern hemisphere's perspective, we are saying we are looking at south-facing slopes or the northern slopes in the northern hemisphere. Those are the ones which are facing the equator. So we tend to find that they have warmer temperatures, or they are warmer generally, because the area covered by insolation is greater. There is greater coverage of that slope by insolation because they face towards the direction of the sun. North-facing slopes in the southern hemisphere, they face towards the sun, and south-facing slopes in the northern hemisphere, they also face towards the sun. So basically, the area that receives insolation in those slopes, the area is larger. So our correct response qualifies to be Z for that response, for that question, which is Z for number 121. We go to number 122. Anabatic winds are dash winds. Right, you need to distinguish between anabatic and katabatic. Right, we know those are typical valley winds. It's also a microclimatic environment. When we talk of anabatic, we are looking at the day winds, which are upslope winds. Anabatic winds, they happen during the day. They blow from the valley floor going to the valley sides. And the opposite is true with the katabatic winds. They are night winds that flow towards the valley floor from the valley sides at night. So in this instance, we have defined what anabatic winds are, and we can figure out the correct response from the explanation and the definition of the two types of winds. Anabatic winds are upslope winds. That is the correct response for that one. They are upslope, which is Z. Then we move on to number 123. Anabatic winds are dash pollutants found in the valley. Right, when you talk of an upslope winds and you're talking of pollutants being concentrated in a valley, when there is an upslope winds, it means it takes with itself the pollutants within the valley as it goes up the valley sides. So it means it disperses the pollutants from the valley, which implies that the correct response for number 123 is letter Y. Right, we move on to number 124. The type of precipitation found in a valley when dew point temperature is above 0 degrees Celsius. We are saying the minimum temperature is above 0 degrees Celsius. In that instance, what type of precipitation forms in a valley? Right, the correct response there qualifies to be fog. Why we are not saying frost? Because frost only forms when the temperatures fall to freezing point, which is 0 and below 0, which means we can only have the formation of frost in the valley at temperatures maximum 0 to minimum of negative temperatures. So that qualifies fog to be the correct response in that instance. We move on to the next question, number 125. Right, number 125, winds at A will be dash than winds at B in the sketch below. Let's try to analyze the sketch. We are seeing those are winds blowing in an urban environment. And where we see our B is falling on an open space just by the sides of the taller buildings, and our A is falling in within the taller buildings. So will the winds at A and B comparably, which ones will be weaker or stronger? If we check on B here, there is open space and there is free flow of air, and wind flows freely across area B, which will imply that the winds will be less stronger compared to the winds which will blow along channels at A. A is more of a channelized winds which are forced to blow in a given direction because of the barricade or the blockade which is caused by the buildings. So the winds will become stronger as they get concentrated and they get to be channelized towards a given direction. So they become stronger. So in that instance, our correct response is item Z for stronger. Right, we move on to the next question, which is question number 1.2.6. The main factor contributing to the heat island effect in the sketch below. Right, if we check the sketch below here, we can see these arrows which are from one building to the other and back, and to the other building and back. What might be causing the heat island? And remember, when we're talking of a heat island, we are talking of an urban area with a higher temperature compared to the surrounding rural area. What causes higher temperatures in this urban area here in this given sketch? The correct response there is multiple reflections, which is indicated by those arrows that we can actually see. So the correct response there is Y for multiple reflections. Why Z is not correct is the buildings are not of the same height, and if you check the reflections indicated here, they are even higher than some of the buildings on the extreme side. So we cannot qualify height of buildings to be the correct answer for that one. All right, move on to the next question, which is question number 1.2.7. Right, the sketch below illustrates a pollution dome during the, is it day or night? Right, if we check on the shape of the pollution dome, and the concentration of pollutants differs between daytime and night time. Right, during the day, because of the higher temperatures within the city, they tends to develop a low pressure system within the city, which will attract incoming winds from the surrounding farmland or the surrounding countryside. So they tend to be a low pressure and rising air within the city because of the incoming air which is fed towards the low pressure within the city. So the pollution dome is elevated during the day, is raised up during the day because of the convection currents that are realized because of the high temperatures within the city that lead to a low pressure that attracts incoming air from the surrounding countryside. So this shape here is typical of the night situation. You can see that the pollutants are concentrated, and also the dome is having a unique dome shape and is just close to the tallest buildings in the city, which resembles that it's a night situation where we have a sinking air which will push the pollutants further down and closer to the buildings, and the concentration you tend to find that it's high at night than during the day. So that one, the correct response is the night pollution dome. It's a night situation. Right, we move on to the last question on that section, which is number 128. The type of pollution dome in question 127 is because of what causes that in relation to convection. Right, convection is low. There are no convections like what has been discussed earlier on. When you have convection, the pollution dome is raised and the pollutants are dispersed up into the upper atmosphere. But when there is low convection, it means the pollutants will become concentrated and the pollution dome will be lowered down. So it means there's low convection for that response. Right, that's the end of question number 1.2. We move on to the next question, which is question number 1.31. That is basically a synoptic, a satellite image on a mid-latitude cyclone, which is likely approaching South Africa. Right. The question is talking about point A here on the synoptic map. Right. You can see if we try to figure out this illustration of this satellite image, you tend to find that we have a cold front on this side here. If we check, there is a cold front which is on this side. Let me try to illustrate and show how these two are relating. Right, the cold front is coming from this side, and you can see getting to A. Then we have a warm front on this part. That is basically how this weather system is like. Right. So if you can see there, we can try to figure out using the way we read synoptic maps and try to relate it to the satellite images, because basically it's one in the same thing, but it's only that this one is a satellite image. But when we are using synoptic weather map, we use an aerial view where we draw the fronts, just like in symbol lines. So what is happening here is the area A, which is marked here. You can see that area A is falling at an area where the cold front has caught up with the warm front. In this instance, we might be having an occlusion at this particular part of the weather system. So the pressure system that develops here, where the cold front has caught up with the warm front, is a low pressure. That is the correct response for that question. That is a low pressure for that response. Right. Let's try to figure out the other responses which follow, the other questions which follow after this. Right. The next question is talking about the evidence from the satellite image of your answer to 131. Right, like what I've discussed here, why is it a low pressure cell on that part of the system? Right, you can see also that if we try to use the argument that we were using there of that drawing, you can see that's the point where the cold front has caught up with the warm front, or where there is an occlusion on that part of the weather system. And you can also see based using on the density of the cloud. The cloud there, you can see that there is a dense cloud around that particular area, right, which resembles that warm air has been uplifted from that particular section, causing high condensation level on that particular part. Warm air has been displaced from the ground surface. So basically, that's the evidence that we can use to support that it's a low pressure around point A. Then we move on to question number 3, 1.33. Describe the rainfall usually associated with the cloud type at warm front. At the warm front around here, what kind of clouds do we tend to find? Right. Maybe if we can try to illustrate this drawing using a cross-sectional view, we can tend to find that we have something that looks like on this part here we have the cold front, and maybe on this part we have the warm front going in that direction, and we are saying our weather system is moving in that direction. So we are looking at the clouds that develop along, we are saying this is our cold front indicated by this, and this is our warm front indicated by this. We want the type of clouds that develop around this area here, which is the area along the warm front. We know well that around this area we have incidences of towering cumulonimbus clouds, but that is not where our question is coming from. Our question is solely based on this part here. We want the type of rainfall that is a resultant effect of the clouds that form along the warm front. Right, in that instance, we have light to moderate rainfall over a wide area. The rainfall there will not be as heavy as the rainfall that we receive here under the cumulonimbus clouds. The rainfall here will be light to moderate rainfall, which will be extensive. It covers a wide area and often lasts for several days. The rainfall here will be prolonged rainfall. It's not very heavy, but it's moderate to average rainfall, but which lasts for quite a number of days. Why does it last? Is because this warm front moves gradually, and this cold front is the one that moves faster. So it means clouds will form gradually and will produce rainfall gradually as they are pushed by the coming cold front. And this area will keep on receiving moderate to light rainfall for prolonged periods until the coming of the cold front, which will completely displace the warm and moist air. So the correct response there, we should highlight that the rainfall is light to moderate and covers a wide area and is for a prolonged period. Right. We move on to number 134. Give a reason why the interior of South Africa experiences clear conditions. If we check on this map, the interior here is basically clear. Why is it clear in that instance? Right, we can relate to the coming of this weather system here. If we check this weather system, it's just very close to South Africa here, which means it's likely to impact on the western coast of South Africa. When does that happen? This happens during winter. We have the coming of cold fronts or the mid-latitude cyclone affecting South Africa during the winter season. And that is also where we have to find out that we have clear conditions over South Africa. The reason being that during winter, and we have the dominance of the Kalahari high pressure cell over the interior. We have the dominance of sinking air, which creates stable weather and clear skies over the interior during this particular time of the year, which is the winter season. So basically, the clear conditions are attributed to the Kalahari high pressure cell, which causes stable conditions over the interior and giving us a clear skies. Right. We move on to the next question, which is question number 135. Right. In a paragraph of approximately 8 lines, explain how approaching cold front changes cloud cover and winds experienced at area B. We should make sure that for this question, you address the two aspects in the question. Address the aspect of cloud cover and also address the aspect of winds. Right. With cloud cover, when the cold front is approaching, it will ultimately cause increasing cloudiness of the area. Area B is going to experience an increase in clouds. And as time moves on, the clouds will become thicker and more extensive as the cold front approaches. So it's increasing cloudiness at point B because of the cold front will be coming and pushing the warm and moist air to condensation. And as the cold front approaches, the clouds will thicken. They will become more thicker and they will become more extensive. You need to say they will cover a wider area. And we will have instances of towering cumulonimbus clouds developing over that area with the approaching of the cold front. That is basically the cloud changes. Then with the wind changes, we are looking at the wind speed is going to increase with the coming of the cold front, and also the winds will become stronger as the cold front approaches. And with the near approaching of the cold front, we will tend to have gust winds when the front is just coming, and that will have a potential of causing harm with the coming of the cold front. That's basically how the wind is also going to change over that particular point B. Right, that is our question number 1.3.5. We move on to the next question, which is a question on tropical cyclone ready. Right, this information provided here is an extract, and there is also an illustration of the path that was followed by that tropical cyclone. Right, we won't spend much time looking at the extract, assuming that the extract has been well understood. Right, let's go to the questions. Number 1.4.1, it talks about on which date did Tropical Cyclone Fred hit Madagascar. I think that is basically extraction. The answer is there in the extract where it says Tropical Cyclone Fred formed on 6 February in the Indian Ocean, northwest Right, Tropical Cyclone hit Madagascar on 21 February and Mozambique on 24 February. So basically our answer, we were worried about Madagascar. The answer is straightforward from the extract, which implies that the correct response is the 21st of February 2023. That is when it hits Madagascar. Right, number 1.42. Why was the impact of Tropical Cyclone Fred more severe or destructive in Mozambique than in Madagascar? Why did it cause more harm in Mozambique than in Madagascar? Right, the reason there is the tropical cyclone, if we check, Madagascar is here and Mozambique is there, which will mean that for this cyclone to come from Madagascar to get to Mozambique, it has to cross through the Mozambique channel here. From the 21st of February when it hit Madagascar, it crossed the Mozambique channel and reached Mozambique on the 22nd of February. So the reason why we are saying because the impact was more destructive in Mozambique is because the cyclone re-intensified, or it went through cyclogenesis over the Mozambique channel. It strengthened over the Mozambican channel, or it went through a cyclogenesis process, which means it gained more power as it was crossing the Mozambique channel. Right, let's go to the next question. Refer to the path of the tropical cyclone. Give 2 reasons why Tropical Cyclone Freddy changed from a tropical cyclone to a tropical depression from 21 February to 22 February. Right, you can also relate these 2 questions. They are almost related from the way the question are appearing, because you are looking at 21st February in Madagascar and 22nd February over Mozambique. Right, so the reasons why, because we have said it re-intensified over the Mozambique channel. What reasons can we give here? Because we know that a tropical depression is more destructive than a tropical cyclone, which means the wind speeds are different for a tropical cyclone and for a tropical depression. Why is it that the winds were more destructive? And what happened for it to transform from being a cyclone to become a depression? Right, the reasons that you can give there is because of the warm ocean water over the Mozambican channel. Remember, for tropical cyclones, they need warm oceans. So it went through cyclogenesis because of the warm ocean waters over the Mozambican channel, which provided it with energy to revive its power and to revive its circulation and become more stronger and cause more damage over Mozambique. And also we can talk of high humidity. Humidity fuels the cyclones. They strengthen using the power. When they release latent heat, they gain more power. So also because of the Mozambican channel being having warm waters, it also meant that it was fed with high humidity, and which also contributed towards the cyclone being more stronger as it went towards Mozambique. Right, we can move on to the next question, which is question number 1.44. Why is the northwesterly path taken by Tropical Cyclone Fred considered unusual? Right, before I answer this question, I would maybe want to clarify on the normal path that tropical cyclones form. Right, we know that tropical cyclones, in this instance in our hemisphere, the southern hemisphere, they move in a direction which is from east to west. And that is the ordinary and that is the general movement path of tropical cyclones under normal conditions. They move from east to the west. Right. And why do they move in that direction? It's because they are under the influence of the trade winds or the tropical easterlies. That is why they move in that direction. But if we check for this part here, for this tropical cyclone Freddy, we also tend to find that because of the combined effect of this movement of the tropical cyclones being driven by the trade winds. The trade winds also are influenced by a Coriolis effect, which will also cause them to deflect. And if we try to check or to refer back to our trade winds deflection in the southern hemisphere, we tend to find that our deflection is to the left, which will mean that the tropical cyclone, if it's being deflected with the movement of with the effect of Coriolis force and with the movement of the tropical easterlies, which are also under the influence of Coriolis force, we tend to find them twisting towards the south. But in this instance, it defied that. So why was it unusual? Why is it unusual? It is unusual because the northwesterly movement defies the typical clockwise rotation of tropical cyclones. We tend to find them having to twist slightly to the left or to the anti-clockwise as they get inland over Africa here because of the influence of Coriolis force. But in this instance, it's unusual because it's going against that circulation, that rotation. It's defying that rotation, which means it's an unusual movement of that tropical cyclone. Right, we move on to the next question. Number 1.4.6. Explain how the damage to infrastructure caused by tropical cyclone Freddy could have a negative impact on people in the affected areas. Right, the question here is specific, is referring to the damage to infrastructure and how does it pose negative impact on people. So we need to be very articulate when answering this question. We need to ensure that we indicate what damage to infrastructure has been realized by the tropical cyclone and how it impacts on people in the area. So I'll highlight just a few examples for this instance. We can talk of damage to roads being a form of infrastructure, the road network being damaged by the tropical cyclone. How does it impact on the people? We can talk of difficulty in transportation of goods or difficulty in access to services. People have difficulties in accessing their services that they want because they need to be transported via the road network, or they have difficulties to access goods that they want because the road system or the road network has been disrupted by the cyclone. Then you can also talk of the damage to houses. Tropical cyclone Freddy caused the damage to houses. How does it impact on the people? It results in homelessness. If people's homes have been destroyed, then it's a problem to the people, them becoming homeless. And damage to buildings, we can talk of damage to buildings like productive buildings like the factories and the industries. That will result in loss of jobs to the people, or that can result to unemployment. That is also a negative implication on infrastructure and resultant effect to people. And also we can talk of damage to communication networks. That can also, a communication infrastructure can be damaged by the cyclone. That will result in disruptions in communication or difficulties in people communicating. So basically we need to be articulate. We need to find the damage that has been done to infrastructure and its subsequent impact to people. Right, then we move on to question number 1.5, which is the last question on climate. All right. The question number 1.5, it says, refer to the sketch below which illustrates the development of line thunderstorms and during summer. Right, we should be able to interpret this diagram clearly before we try to answer the question. This is typical of traveling disturbances that happen during the summer season. Right, we understand that this is the interior of South Africa, and over the interior of South Africa, when it is summer, we tend to have the existence of the thermal law over the interior here because of intense heating. The ground is intensively heated, and it results in rising air, creating a low pressure over the interior. So we have the existence of the low pressure cell over the interior. And remember, we have our two high pressure cells over the Atlantic and over the Indian Ocean. And the resultant effect is that there will be pressure gradient between the South Atlantic high pressure cell and the interior, and also there will be a pressure gradient between the South Indian and the interior. So the resultant effect is that the anti-clockwise circulation of air out of the high pressure cell here will feed into the low pressure cell that has developed over the interior. And also the anti-clockwise circulation from the South Indian high pressure cell is also going to feed over the interior of South Africa, which will be having a thermal low. So those two air masses coming from different directions, apparently they will have to meet somewhere over the interior, and they will create this weather system which is indicated over this interior here. Right, let's not waste time by explaining. Let's go to the questions. Right, we have question number 1.51. Identify the front at A. This front here at A. This is a moisture front. It's a moisture front in that instance because of what happens at this front here. We have incidences of cloud formation and heavy rainfall forming along that front. So it's termed a moisture front. Right. Then we move on to the next question. Give the wind direction at B and C. Right, what wind direction is this one and what wind direction is this one? The wind which is fed from the South Indian here from B, let's start from at B here. The wind which comes from B, which is fed from B in this instance, is a northeasterly wind. This is coming from a slightly northern direction and from the east because it's coming from over the Indian Ocean. So it's a northeast, and this one coming from the Atlantic, this one becomes a southwesterly wind. So it's southwest from this side and northeast from this side here. Then state the moisture content of air masses B and C. Right, the moisture content we figure it out from the nature of the oceans from which these high pressure cells are located. This one is located over the Atlantic Ocean, and this one to the east is over the Indian Ocean. So the implication is over the Indian Ocean, remember it's a warm ocean, we tend to have a warm ocean current here, and the resultant effect is that the winds which come from this will be warm and moist. And here over the Atlantic, it means for the fact that it's a cold ocean, it means we have a cold ocean current, and the winds which blow from this high pressure cell will be cold and dry. So when you are comparing the moisture content here, we are saying the winds which are coming from B here, in this instance, the air mass B will be moist or will be humid, and this one coming from this side will be dry. So it's humid, moist from B, and it's dry from C. Right, explain the formation of line thunderstorms over the interior of South Africa. Right, we'll try just to summarize on that one there, how the moisture front forms. Right, the basic instance is that the high pressure cell over the eastern part, which is the South Indian, it feeds in warm and moist air. And the high pressure cell over the Atlantic Ocean, the South Atlantic, it also feeds in a warm, cold and dry air. Because of its anticyclonic circulation, it feeds in cold and dry air. From the South Indian, it feeds warm and moist air. And the existence of a low pressure cell over the interior attracts these two air masses because of pressure gradient, and they meet along the moisture front. As these two air masses meet, we know well that cold air is denser than warm air. So at the front here, the air coming from the Atlantic Ocean, it undercuts the air coming from the Indian Ocean, resulting in an upliftment of the warm and moist air and formation of clouds on the side of the warm and moist air. So the front forms by that fact that there is air which is fed from the South Indian high, which is warm and moist, and air which is fed from the South Atlantic, which is cold and dry. They meet because of the pressure gradient created by the thermal law over the interior, and as they meet, because of the differences in density and the differences in temperature, they cannot mix. This one is cold and dry from the side, and this one is warm and moist. This one, which is cold and dry, it undercuts or it wedges under the warm and moist. That is how the moisture front forms. And the line thunderstorms will develop as a result of the development of the clouds. As this warm and moist air is forced to rise, it's going to create cumulonimbus clouds that will result in thunderstorms happening along the moisture front in a line, which we call the line thunderstorms. Right, let's move on to the next question. What is the positive impact of heavy rainfall associated with line thunderstorms on the physical or natural environment? Right, the responses here are just simple. We are looking at the implication of having moisture being fed to the natural environment. How does it impact? We can talk of replenishing of water sources, which will benefit the aquatic life. We have different aquatic ecosystems and aquatic life. Those creatures and those animals and plants, they will benefit from the replenishment of water sources. And also it can argue that it adds soil moisture that promotes vegetation growth. That is good for the environment, for the natural environment, that we have the growth of vegetation because of the feeding in of moisture to the ground. Or we can argue that it provides water for the wildlife, which is also part of the benefits to the natural environment. So basically those are the expected responses from our first question on climate and weather. Right, we quickly move on to the second question, which is geomorphology. Right, geomorphology, we are doing fluvial geomorphology. In this instance, we are looking at the study of rivers. Right, I will go through the questions in as quick as is possible. Right, we look at question number 2.1.1. This is a column question. Right, dendritic stream pattern, is it Y or Z? Right, in this instance, we know well that the term dendritic is a derived term from the Greek term dendros, which means a tree and its branches. So when we are talking of a dendritic pattern, we are looking at a pattern which resembles a tree and its branches. So if we try to check on those two patterns, the one that reflects a tree and its branches, we tend to find that is Z in this instance. Our Z is the one which resembles a tree with its branches. This one is now a rectangular drainage pattern on Y. Right, we move on to the next part, which is item number 212, question number 212. The stream pattern develops on a dome. Stream pattern that develops on a dome, when you're talking of a dome here, we're giving an example of an elevated landscape. For example, a volcanic landscape, where we have a lake on top of a volcanic dome, or where we have that we call a caldera lake, which forms on top of a volcanic mountain. We tend to have streams radiating from a focal point. The streams, they will develop from one source and they will radiate into different directions. So the stream pattern that we tend to find on that instance is radial. Radial, the streams will be radiating from one focal point in different directions. The source being an elevated landscape, and they will be flowing towards low-lying areas in different directions in a radial form or radiating from a core focal point. Right, we go on to question number 213. Stream pattern characterized by short tributaries joining the main stream at right angles. Right, you are having a situation whereby the tributaries are shorter but the main stream is longer. It resembles an area which is mainly folded, where we have maybe a folded area or a faulted area where we have a rift valley or a graben and two nearby host or block mountains, or where we have folding, we have two fold mountains existing side by side and we have a valley in within. The system that we will develop there is that we will have a major river which will run through the valley, and we will have short tributaries emanating from the folds by the sides or emanating from the block mountains by the sides. So that system that we tend to have there is what we call the trellis drainage pattern. Right, we move on to the next question. 214. The underlying rock structure of the stream pattern below has what causes this? This type of pattern is typically a rectangular drainage pattern. What kind of rocks contribute towards the development of a rectangular pattern? Right, the correct response for that question there for number 214 is Y, where we have cracked and jointed rocks. This pattern is influenced by the cracks of the underlying rocks. The streams will follow the areas of weakness which have cracked, so they will follow those cracks. So the streams, they will be influenced by the underlying existing cracks along the rocks which are below that area. We move on to question number 215. It talks about drainage density of a river system flowing in areas of high permeability. Where we have high permeability, we are looking at a situation whereby the soil or the underlying rock material allows for infiltration and percolation. Rainwater is allowed to filter into groundwater storage. So it means, remember, for us to have high drainage, we need to have high surface runoff and limited infiltration. And if it is the opposite, we have less runoff and more infiltration, it means we will have less streams developing in that particular area. So in this instance, we are looking at a situation whereby drainage density of the river flowing in areas with high permeability, it means there is more infiltration compared to surface runoff. So we tend to have limited number of streams developing in that particular area. So the correct response for number 215 is low. We'll have a low density in that area. We have limited streams. Right, let's move on to question number 216. Question 216 is on stream ordering. Right, the stream order at X. Right, before we even answer that one, let's try to elaborate and try to simplify how we come out with the stream orders. Right, I will try to illustrate and show how we do the ordering of streams in the basin. Right, number 1 plus number 1 is stream number 2. Get number 2 plus number 1 is maintains number 2. We get number 2 plus number 2, it gives us number 3. Then if we have number 3 plus number 1 is number 3, and number 3 plus number 2 is means number 3, and if we have number 3 plus number 3, we get number 4, and so on, going in that order. That is how we do stream ordering. So I will try to label those streams. Right, a number 1 stream in a drainage basin is an independent stream without a tributary. So we tend to find that this is number 1, and this is number 1, this is number 1, number 1, number 1, number 1, number 1. Those are number 1 streams in that particular basin. And number 1 plus number 1 here means we have number 2 from this confluence here. And number 1 plus number 1, it means number 1 plus 1 here. From this confluence, it means we now have stream number 2. And number 1 plus number 1 in this instance from this confluence, it means this one is now number 2. And let's go back to this confluence here. This is number 2 plus number 1. The order does not change. It's still number 2. Then we are going on to number 2 plus number 2 in this instance. We are moving on to the next order, which means after this confluence, we have stream order number 3. Stream number 3 plus number 2, the order does not change. It remains 3 here after this confluence. So the correct response here is Z. That is the correct order for that particular point X in that drainage basin. Right, we move on to the next question. Characteristics of first order streams in a drainage basin. Is it straight and short or straight and long? Right, first order streams, they are not long. A high order stream is the one which is longer. Like for example, if we check here, stream order number 3 is starting from here going all this long. But stream order number 1 is just from here to here. Or if you check this one just from here to here, here to there, this becomes a shorter stream. It's straight and short, right? So the response here is Y, number 1, 2, 7, right? We can move on to the next question. which is number 2.2, quickly is on the concept of stream piracy or river capture. Right, it has river R to the extreme west and river Q to the extreme east. Then there's a watershed in between. Then all those processes happening there. Let's quickly go to the questions. We want to answer the questions as fast. Right, number 2.2.1, it says the sketcher illustrates A or N. Is it a longitudinal, plan, oblique, cross profile? Right, this one here, it qualifies to be a plan view. We cannot say it's a longitudinal because the longitudinal profile shows the gradient of the river from its source to its mouth. And in this instance, it's not one river. We're looking at the river R, river Q here, and river S, which later developed after the process of river capture. So this qualifies to be a plan view in that instance. Right. Then number 2.2.2, a river capture is taken place because tributary P flows on dash rock and over a dash gradient. Right, for river capture to take place, we need conditions where one river is flowing, is more energetic than the other river. And the energetic river advances through headward erosion towards the less energetic river across the watershed. It cuts through the watershed and approaches or intercepts the headward waters of the less energetic river on the other watershed, on the other drainage basin. And remember, the energetic river is usually the one which is on a lower ground, which is less elevated. It cuts through headward erosion until it cuts through the watershed until it intercepts the headward waters of the less energetic river on an elevated platform. So in this instance here, if we check our river tributary number P, if we try to figure out using that argument, we can say the nature of rocks. For this river to effectively erode headwardly, it needs to flow over softer rocks. So item number 1 qualifies, we disqualify harder. And what kind of gradient here? The gradient for this river to be energetic, it needs to flow over a steeper gradient. It approaches a river which is high-lying, so that it erodes headwardly across the watershed and be able to reach the other drainage basin. So item number 2 for harder and item number 4 for steeper gradient they are the responses which are relevant to that question, and the combination comes with letter option B, which is item 1 and item 4. Right, we move on to tributary, question number 2.2.3. Tributary P, as illustrated in the sketch, is a dash stream. Right, the labels for this water, let's just label all the aspects here. River R and river Q. Right, this tributary P is the one which intercepted the headward waters of river Q. So it means this one is the captor. Captor is the one that intercepts the water. Then this one is the captured. And where the stream piracy took place, this particular point here, the bend around here, this is what we call the elbow of capture. Then this river here, which continues after river capture, is what we call the beheaded stream. And then this part here, which marks a gap between the old river which was feeding into this one and the new river starting from here, is what we refer to as the wind gap. So basically, those are the concepts related to stream piracy. We have the captor, the captured, we have the elbow of capture, we have the wind gap, and we have the beheaded stream. Right, so if we're going back to our question, stream P, we have illustrated and we have labeled everything on that particular section of the river capture process. Tributary P qualifies to be the captor. It has captured headward waters of the stream on the other drainage basin. Then number 2.24, the process in which tributary P lengthened its channel by cutting through the watershed is known as, right, the process that aided tributary P to cut through. That, what kind of process is that one? That one is headward erosion. Right, remember we have three basic types of erosion that takes place within the river channel. Right, we have headward erosion. Headward erosion is responsible for lengthening the river channel, is the one that is responsible for making the river longer, which means it happens at the source of the river. The river source keeps on migrating towards the watershed. It migrates, meaning to say the length of the river will keep on increasing. That is headward erosion. Then we have vertical erosion. Vertical erosion is responsible for deepening the river channel. The channel becomes deeper through vertical erosion. Then lastly, we have what we call lateral erosion, which is sideway erosion. Sideway erosion is responsible for widening the river channel. So basically, those are the three types of erosion. So relevant to this question here, our type of process which is responsible for making river tributary P be able to cut through the watershed, it was aided by headward erosion. Right, we move on to the next question. Feature T is known as A or N. That is question number 2.25. We have already discussed that. That bend is called the elbow of capture. Right. We move on to question 2.26. River R will have a dash drainage basin and A or N velocity after river capture. Right. If we check on river R here in terms of its basin, river R used to have a basin which was this side of the watershed before the process of pirates. But now its basin is now extending going towards there, because this part of river Q is now part of its basin, because it's now being drained by this same river here. This is now a tributary of river R, so its drainage basin has been increased by the process of capture. So if we check on the responses here, it becomes larger. And the velocity, how does the velocity of the river, how is it influenced by the process of capture? If there is more water in the river channel, it means the river has more energy. It flows much faster when it has more water. So it's larger and an increase of velocity in that river. So it's the correct combination is item number 2 and item number 3. Item number 2 and item number 3, they come on number 2.26, item option number 6. That is the correct response. We move on to the next question. Refer to area U on the sketch where the river rejuvenation occurred. To answer question 227, 228. River rejuvenation occurred due to A or N and dash erosion that took place. Right, river rejuvenation. Some of the causes of river rejuvenation is isostatic uplift, which is indicated. Increase in volume of water, yes, is also a cause. We can also talk of other causes, like an increase in the rainfall received in the area is also a cause or a contributing factor of rejuvenation. But in this instance, our cause is direct. The rejuvenation or the revival of the river's erosive power is being contributed to by the increase in the volume of water. There has been stream piracy, and this stream piracy is contributing towards the increase in the discharge of that particular river, which will also imply that its erosive power is going to be revived. So it's increasing the volume of water, item A. We are cancelling item number 2. Then, what kind of erosion happens if a river is rejuvenated? When a river revives its erosive power, it regains energy to cause vertical erosion. It regains power to erode vertically and deepen its channel. That is why we tend to find that we have the development of landforms like valley in valleys after rejuvenation. The meanders, the entrenched meanders rather. The entrenched meanders, they are a result of incision by the river, which will mean that the river will be deepening its channel through vertical erosion. Or where we have the paired terraces, those terraces are realized because of the development of a channel in the old channel. So it will mean that the river will be regaining its capacity to cause vertical erosion. So the correct response is item number 1 and item number 4. Those two responses, they correlate at item increased volume of water and vertical erosion. Increased volume of water is item number 1, and vertical erosion is item number 3. 1 and 3, which means the correct response there should be item number A, response A. Right, we move on to the next question. The resultant landform most likely to form after rejuvenation in area U is A or N. Right, let's go to area U and try to analyze what landform is likely to form. This area marked U here, you can see this river. If you can check, the river is winding, is meandering around this area. So when there's rejuvenation, the river rejuvenates, and already the channel was meandering. What is the likely landform that is going to form in that particular part of the river? Definitely the correct response here, we are going to have the incised meanders are forming over that area. Right, that is question number 2.2. Let's quickly move on to the next question, which is question number 2.3. Question number 2.3 is based on the longitudinal profile of two rivers, river X and profile X and profile Y. Right. The first question is talking about what is longitudinal profile. Longitudinal profile, we can simply define it, though it can be defined differently according to your way of understanding, but we should address the basics. I can define a longitudinal profile of a river as the gradient of a river from its source to its mouth. How the river looks like along its course from where it starts until where it ends. That is the longitudinal profile. Right. Then we move on to the next question, number 2.3.2. A is known as this A here. What is it known as? That is a permanent base level. If you can see here, it's starting from the sea level, so that becomes a permanent. That river cannot erode below that point. If it gets that point, it attains a grade. It can never go below the level of the sea where it is feeding into. Right. And give an example of a natural temporal base level of erosion that could develop at the neck point. At the neck point, we can have a lake developing here. It can be a feature of a temporary base level. Right, we move on to the next question, number 2.3.4. Which profile X or Y is graded? When we talk of a graded profile, we are looking at a profile which resembles a smooth concave shape of the river's longitudinal profile from its source to its mouth. So if we try to check between these two, the one which is smooth concave is profile Y. Then we move on to the next question. Give a reason for your answer. I think I've already explained the answer. Why am I saying Y is a graded profile? Y resembles a smooth concave shape from the source of the river to its mouth. And then explain how the profile above the graded profile developed. Right. It is attained because of an equilibrium or a state of balance. For us to attain a grade, it is attained after the river attains an equilibrium. The rate of deposition, the rate of erosion is equated to the rate of deposition, which means whatever is eroded and whatever is deposited is the same, which means the river will maintain a smooth shape throughout its course from its source to its mouth. So basically, when I'm explaining the formation of a graded profile, it is a result of the balance between the rate of erosion and the rate of deposition. The material that is being eroded is equal to the material that is being deposited along the river channel, which will mean that the river will maintain a smooth concave throughout its profile. Then number 2.3.7, draw a rough cross profile of the river valley at B. Right, if you check point B here, we are very close to the source. We are still in the youthful stage of the river. If you are drawing the cross profile, you should ensure that your drawing should resemble, let me just simplify, a simple drawing which might be relevant. Right, we are saying the river will be having something like a profile like something like this. Right. What happens with this profile is the profile should have a narrow valley, and the valley should be deep. Those are the basics that should be addressed by that part, because the river is still in its youthful stage. It's still in the youthful stage where it is eroding vertically. It will mean that the river will have a deep valley. The valley will be deep and will be narrow. The river will still be in the young stage or in the youthful stage. So basically you can draw a profile which resembles something like that. A river which has got a narrow valley and which is deep. That is typical of a river. And also the discharge of the river will be very minimal. It will be having limited discharge because it's just in its youthful stage. Then give reason for the shape of the cross profile. I think I've explained before I answer before getting to the question. The reason why we have a narrow and a deeper valley is because the river is predominantly eroding vertically, and also the river is still in its youthful stage. That is why the river valley is still narrow. There is less discharge in that particular, and the type of erosion does not allow for the widening of the river channel, but rather it concentrates on the deepening of the channel. Right, we move on to the next question, which is question 2.4. Right. Number 2.4 is based on a sketch of a fluvial feature along the river channel. Right, before we look at this, let me try to explain the aspects of this diagram here, so that when you're answering the question, it becomes clear. This part of the river here, this fluvial landform, is what we call a meander. It's a bend along the river channel, which is in the river's lower course. I think you can see that the sea is illustrated here. The river is getting into the sea and it's winding its channel. The channel is winding. In that instance, it's bending. And along these bends, we have what we call the outer bend of the meander and the inner bend of the meander. Right, what we call the inner bend of the meander, for example, is this part here. This part A is what we refer to as the inner bend. And also this part here is the inner bend. And this part here, we labeled B, is the outer, and this is also the outer bend of the meander. So what happens is, as water is flowing past the bend, we tend to have that flow velocity of water here is much faster. The water flows faster. The water which goes via this outer bend will be much faster than the water which goes via this inner bend. The water here will be slower, will be having slower velocity, and the water here will be having a higher velocity. The same happens as the water is going again via past this bend here. There is fast velocity on this part. The water flows faster, and the water which comes via this side will be flowing gradually. That is what happens along the bend there. So this is what we call the outer bend, and which we call, this is the outer part of the bend, and which we call geographically the undercut. It's called the undercut of the meander, and this is called the slip off. It's called the slip off slope of the bend here. Right. These are the two parts of the meander that we are going to look at. And because of the limited velocity here, we tend to find that there is deposition taking place. Remember, whenever the energy to transport a load the force below the minimum required to transport that load, the river will deposit the load. If the energy required to transport, the minimum required to transport a load is not reached, the river starts to deposit material. So it means there is deposition which takes place here because of the limited velocity of the water, and here, because the water flows fast, it tends to erode this outer bank here. This bank is eroded and is undercut. That is why we are calling it undercut. It means it's being cut by erosional processes happening. And the material being taken here will be deposited on the inner bend where there is limited velocity. That is what happens along the river channel and along a bend in a river channel. So from that discussion, I think we are able to figure out the responses to the questions which will follow. Right, we'll quickly go through the questions and figure out the most probable responses. Right, number 2.4.1. The fluvial landform or feature illustrated in the sketch above. In the sketch is, we have already highlighted the correct response. That one is a meander, it's a bend along the river channel. Then we go to question number 2.4.2. Give a characteristic of a river in the lower course in which this fluvial feature named above develop. We are looking at features in the lower course. What are the features of a river which is now in its old age? Right. The river there will be having a wide channel in the lower course. It's one of the features. It has a wide channel. And also the discharge volume is high or is large. The river has got very large volume of discharge. And also there is slow velocity. The water is generally slow in terms of its velocity. And also, if you can check, the river is shallow. The river becomes shallower because of increased deposition. So basically, those are some of the features that you can figure out. The river is shallow, and there is slow velocity, and also the channel is wide, and there is a larger volume of discharge. Right, that is what happens in the lower course of the river. Then we can figure out question number 4.243. Explain how gradients influence the development of the fluvial landform in the sketch. How do meanders form in relation to the gradient? Right, what you should know that is the gradient of the landscape where the river is going towards its mouth in the lower course. The gradient is almost gentle. It's gentle to almost flat. The river will be flowing over a gently sloping landscape. What is the implication of a gently sloping landscape towards the formation of the meander? What will happen is the river will be flowing over a gently sloping landscape, which will also imply that the velocity will be lower in that particular landscape. As the velocity is lower, the river will start to deposit load. We will start to deposit sediments along its channel. And at the end, as the river deposits some material or some silt material and sediments, it starts to wind. It means the river will be blocking its own channel. And as it blocks its own channel, it has to wind to find its way, avoiding the deposits that it has made in its own channel. And as it winds, remember we are talking of what happens on a bend. Whenever the river creates its own bend, it will mean that water which goes to the outer part of the bend will be much faster than water which goes towards the inner part of the bend. And at the end, those processes are going to further and further, and the meander will migrate. The outer part of the meander will migrate, creating a pronounced meander or creating a pronounced bend. Cycles of erosion on the outer bend will continue, and the material that is eroded there will be deposited on the other side. And at the end, you tend to find that the river will create a pronounced bend because of that process. So it starts from the gradient of the landscape, it's gently sloping, leading to low velocity of the river. Because of low velocity, the river deposits material and deposits sediment. As it deposits sediment, it starts to wind, avoiding such sediments. And as it winds, remember there is undercutting that is going to take place as it tries to avoid the load which it has deposited in its own channel. So it means the outer part where it is trying to avoid the load is going to be undercut by erosional processes, and the material is going to be deposited on the inner side where it is avoiding. And that process repeats itself until the river has a winded channel or has a meandering channel which is bended. That is basically how we can figure out how the meanders develop from the gradient of the landscape in the lower course. Right. Refer to cross-section X and Y and the fluvial landform features above. Identify slopes A and B. We have already mentioned that. Slope A in that instance, that is a slip-off slope on the inner bend of the river where there is deposition. It's called a slip-off, and slope B is the undercut, which is a slope dominated by erosion on the outer bank of the river. Right. We move on to which cross-section X or Y represents the line between A and B. From A here, we tend to find that this is a gently sloping landscape. It's more of a convex slope from A going to the river channel, and here it's more of a concave which bends inwards. It's an undercut slope. So if you try to figure out from those two, you tend to find that the slope is gentle from beginning at A, it gets into the channel, and then it becomes steep as we go towards B. So the reflected cross-section of that channel is the one illustrated by Y. In that instance, is Y from A to B. Right. Which cross-section we've done that one? Explain the process involved in the formation of slopes A and B. I think we've explained that. We just have to clarify. Slope A, which is a depositional slope, which is the slip of water flows gradually on the inner bend and sediments are deposited on that river spot because of slow velocity. This is the side here. On A here, the water flows at a less velocity and sediments are deposited, meaning to say the slope will be having a gently sloping landscape going towards the stream, the river channel because of deposition. Then slope B. B here, water flows faster on the outer bend and it causes erosion of the outer bank here. This bank is eroded because of velocity of the water and it becomes an undercut. Material which is being taken here is deposited here. That is basically how those two slopes form. So we are looking at the process involved in the formation of A. There is erosion and deposition on one side and the other side, and deposition causes that slip off and erosion causes the undercut on the other side. Right, let's look at the last question on river management, river and catchment management. There's an extract there. The extract, I think, is clear and has been gone through. Right, in which province is Hammanskraal located? Right, this is map interpretation. You can see where Hammanskraal is and the province indicated here, and whatever you can use this infographic to figure out. Right, Hammanskraal is located in Gauteng. It's in Gauteng province. Right, we got question 2.5.2. What is meant by unplanned development as mentioned in the extract? The extract is talking of unplanned development. Right. We can safely relate this to a settlement. When you talk of unplanned development in settlement studies, what will we be referring to? Right. Let me try to figure out where the unplanned development part is falling under. Right. It says people have had a decade-long struggle with water and sanitation issues, serving as a clear example of what happens when unplanned development occurs. Right, basically when we're talking of unplanned development, we are looking at urban sprawl, the problem of urban sprawl, uncontrolled growth or formless growth of cities and towns. That is basically unplanned development. Or we are looking at the growth of informal settlements. Or we are looking at illegal invasions of land. That is unplanned development. So basically it has something to do with illegal settling of people or the sprawling of the urban settlement, the formless growth of urban areas and cities, or basically the growth of informal settlements. That is unplanned development. Then give two consequences of unplanned development according to the extract. Right, the extract talks about there are frequent leaks. There are frequent leaks in the water supply or in the sewerage systems. That is one consequence. Then the other consequence is disruption in water supply. Those ones are listed in the extract. It's just extraction. So it's frequent leaks and disruptions in water supply. Then we move on to the next one. How did Apis River become polluted? How did it get polluted? Right, it's also an extract question, which is from the extract given there. The number one cause of pollution is the dumping of raw wastewater into the river. There is the dumping of raw wastewater and also dumping of semi-treated wastewater into the river. Those are the two forms of pollution which are contributed to the Apis River. Then the last question, in a paragraph of approximately 8 lines, suggests strategies the local municipality can implement or put in place to reduce pollution of Apis River. What can the municipality do to avoid the incidences of pollution of that particular river? We are looking at a legislative perspective. We are looking at the local government. What can they do to try and curb the pollution of the Apis River? Right, we can talk of wastewater treatment improvement. Since we have noted that there's wastewater which is being dumped into the river, what can be done with the wastewater? How can we improve the wastewater treatment system? So we can upgrade existing systems, upgrade existing water treatment system, or we can do regular maintenance of the water treatment system so that we do not have disposal of untreated wastewater into the river or semi-treated wastewater into the river. That is number one. Then we can also enforce a legislation. We use the ruthless hand of the law to curb the problem. Enforcement of legislation by imposing penalties for violators. We can impose hefty penalties for those who cause pollution of the river. It's also an act which can be implemented. Or we can talk of intermunicipal cooperation. Municipalities can work together with other municipalities in the surrounding so that we manage the very same river which flows through the jurisdiction of the different municipalities, what we call the intermunicipal cooperation. Coordinated efforts of municipalities to try and curb the problem of pollution of rivers. Then we can also talk of private-public partnership. The municipality can partner with private businesses to find solutions to the problem of water pollution, of river pollution. Engaging with private entities, it can also help enhance resources in case the municipality or the local government is crippled in terms of its financial capacity to deal with the problem. It will imply that if they engage private partners, they might also chip in with financial assistance that will help us solve the problem of the pollution of the water sources. And also with knowledge, we might also tend to find that there might be private entities that will cooperate expertise towards the solving the problem of the pollution. And also we can promote public awareness. One of the major reasons why people pollute rivers is because of lack of knowledge on the implications of polluting rivers and the resultant effects of thereof when they pollute the rivers. So people need to be educated on the importance of river conservation and impacts of pollution. It's also a way that can be implemented to curb the problem. Then we can also talk of the protection of riparian zones. We can implement buffer zones around the rivers to limit development close to the rivers. We can fence the rivers so that we limit development close to the rivers, and also we limit unwanted activities happening close to the river. It's also an act that we can put in place along the rivers or along the wetlands. We can buffer.
Mixed bag, climatology and geomorphology once more, because this is where we find most challenges. All right, they say refer to figure 2.1 showing a high pressure and a low pressure cell in the southern hemisphere. Match the statements below with the high pressure cell or the low pressure cell. Write down your answer next to the question numbers 2.11 to 2.1.8 in the answer book. All right. 2.1.1 says, sorry, let us first look at the figure. Sorry about that. Let's look at the figure. So this is, let's call, let us refer to this one. Go to figure A, which is a high pressure cell. Figure B, a low pressure cell. All right. So they say associated with rising A. Is it going to be a high pressure cell or a low pressure cell? And for this case, that would be a low pressure cell. it is the one that is associated with rising air. Let's try to illustrate it here on our blank page. Okay. Because we know that in low pressure cells, air converges, then it's going to rise. This is in low pressure cells. All right. So which makes our option for 2.1.1 to be a low pressure cell. 2.1.2 says air diverges on the surface from this pressure cell. Air diverges. So we go back and we show air diverges on the surface. Okay. Now let us try to demonstrate here a high pressure cell first. In high pressure cell, air subsides or descends. After descending, then it's going to diverge. Because to diverge when air moves away. Okay. So air subsides, then diverges. This is the surface. Because in high pressure cells in the upper atmosphere, air converges. You see, it is converging here, and after converging, it is able to subside, or it is able to descend, forming a high pressure cell. Then eventually it diverges out on the surface. So which means if we go back to our options, 2.1.2, it will be a high pressure. 2.1.3, associated with clockwise movement of air. Don't forget, they said these pressure cells are situated in the southern hemisphere. All right. So which one between the low pressure cell and the high pressure cells move in a clockwise direction? Go back to our blank page to try to illustrate. If we have this globe here, which shows northern hemisphere and the southern hemisphere. So we know that in the northern hemisphere, low pressure cells, so in the southern hemisphere, low pressure cells rotates in a clockwise direction, and they rotate anti-clockwise in the northern hemisphere. This is typical of low pressure cells. And then high pressure cells, they rotate clockwise. These are high pressure cells. They rotate clockwise in the southern hemisphere and anti-clockwise in the southern hemisphere. So these are high pressure cells. But our question is saying associated with clockwise movement of air in the southern hemisphere. Clockwise movement in the southern hemisphere, which is this one here, is clockwise movement in the southern hemisphere, which is typical of a low pressure cell. At 2.1.4, unstable weather conditions over the interior. So remember, when they say unstable weather conditions, so they are referring to things, for example, rainfall, winds, overcast condition, etc. Right. We can as well talk about, let's say, thunderstorms. So all these are examples of unstable conditions. Now, how do these develop? We try to illustrate on our blank page. We know that rainfall develops as a result of air ascending. When air ascends, it condenses, forming clouds and as well rainfall, accompanied by thunderstorms. right? So does air rise in low pressure cells or in high pressure cells? And we did indicate up here that in low pressure cells, air rises. See, when it rises, there will be formation of overcast clouds and there will be rainfall. So which means that unstable conditions are associated in low pressure cells. In low pressure cells. 2.15 associated with ridging. What is ridging? This refers to the elongation or extension of isobars away from a high pressure. So the moment I say high pressure, definitely you know what our answer is, right? Because it says associated with ridging. So ridging is common in high pressure. So what they mean? Something like this is happening. You see isobars extending away. You see, so it means this is elongation. So this part here, you can see what refer to as ridging. Isobars are extending, you see, towards that other point. So that is ridging, which is common of high pressure cells. So we say high pressure. Okay. Associated with heavy rainfall and hail, this will of course be a low pressure, because we say that in low pressure cells we say that air rises. When it rises, it condenses, forming cloud that is accompanied by heavy rainfalls. That's why we say that to be a low pressure. 2.1.7 dominates the land in winter. That will be a high pressure cell. In the winter, the high pressure cell dominates the land. How do we show that? If we illustrate it down here, regarding a high pressure cell, this could be the map of South Africa, and normally they're going to show something of that sort or that nature, indicating a high pressure. When this happens, now this shows a high pressure cell dominating the land or the interior in winter. If it was summer, it was going to be like this, because in summer, a low pressure cell dominates the land. So this is winter and this is summer. Okay. So big wind conditions develop when it interacts with a coastal low. That will still be a high pressure. A high pressure cell. So if I can as well illustrate that on a diagram, it's going to be, because they say big wind conditions develop when it interacts with a coastal low. Okay. So it means if this is our high pressure cell, for example, it means we're going to have our coastal, in here we see L, meaning a coastal low here. So if we have a high pressure cell, now there will be a pressure gradient, indicating now winds are moving from a high pressure to the low pressure, and these winds are referred to as the big winds. Right. So they develop between the interaction of a high pressure cell over the land and the coastal over the coast. All right. So that is for question 2.1. 2.1. Okay, question 2.2. They say choose a concept from column B that matches this description in column A. Area drained by a river and its tributaries, that will be a drainage basin. So number D, number 2.2.2, a highlying area that separates two different drainage basins, that will be a watershed, which is F. 2.2.3, starting point of a river, that will be the source, which is G. 2.4, term that describes the main river and its tributaries, that will be E, which is the river system. Point where the river enters the sea, that will be the river mouth, which is H. Elevated land that separates streams in the same drainage basin, that will be an interflow, which is B. Point along the river where two or more streams meet, that will be C, which is the confluence. Okay. 2.3 figure shows the path of a tropical cyclone. So give a path of a tropical cyclone. So they're saying, give evidence that this tropical cyclone is in the southern hemisphere. How do we tell it is in the southern hemisphere? Firstly, can we indicate the clockwise rotation, clockwise symbol, and as well countries found in the southern hemisphere. Countries found in the southern hemisphere. What else can we look at? The date, which is April. So I think it is still summer. April. Yeah, I think that date. About the date. Which shows summer. In southern hemisphere, because April is still not yet winter. We're still experiencing high temperatures. What else can we look at? The Mozambique Channel, which is in the southern hemisphere, as well mentioned. The Mozambique Channel found in the southern hemisphere. All right. Now they say 2.3.2. Why is the Mozambique Channel usually ideal for the increase in temperature within the tropical cyclone? So consider Mozambique Channel experiences warm ocean currents which rises the ocean temperatures. Experiences warm ocean currents, which rises ocean temperatures. 2.3.3, explain how the intensity of the cyclone increased as it moved from area A to area B. Area A, area. So explain how the intensity of the tropical cyclone increased as it moved from area A to area B. So you can see area A to area B. This is the Mozambique channel. So don't have to explain how the intensity of the cyclone increased. Okay. So I'm set. That is what, which question is that? That is question 2.3.3. Question 2.3.3. So the intensity increased massively. The warm temperatures resulted into high rate of evaporation. There was high rate of condensation. Which resulted into high latent heat supply. As well say there was less friction. With the land to slow down the winds and intensity of the cyclone. As well say, and this area due to high temperatures, it resulted in further development of a low pressure. So that's how the intensity of the cyclone increased as it moved from area A to area B. All right. 2.3.4, discuss the conditions that could have caused the cyclone to weaken as it reached area C. So let's remove this one so that you can see clearly. Let's discuss the conditions that could have caused the cyclone to weaken as it reached area. So this is area C here. That's area C is almost close to the land. All right. Let's go back, discuss the conditions that could have caused the cyclone to weaken as it moved to area C. That is question 2.4.
2.3.4. This is 2.3.4. 2.3. So I could say friction with the land weakened cyclone, as well say cyclone moved into cooler areas, because we know that cyclones, they love warm conditions. So if they move towards cooler areas, this as well weakens them. Okay, as well say less supply, less evaporation, and condensation, meaning less supply of latent heat. So let's check again. At point C would have been the reason which caused the cyclone to weaken. Spoke about friction with the land, the supply of latent heat, moving into cooler areas, among others. So for now, I think we shall go with those factors. Let's proceed to question 2.3.5, which says evaluate the physical negative impact of the coast cyclones along the coast of Mozambique. The physical negative impact of the cyclone along the coast of Mozambique. It is 2.3.5. The negative, say, cause coastal flooding, destroying the coastal areas, results into flooding of farms, causing soil erosion, infrastructures, such as roads, buildings, destroys the natural habitats, disrupts the ecosystems, so I'll say due to heavy rains, it could cause landslides and landslides. So, among other
physical impacts. All right, so that is for question 2.3. So we're going to go to 2.5, which says, refer to figure 2.5, which shows a river capture or stream piracy. Define the concept, river capture, as shown in sketch B. So this is sketch B here. So before, you can see we have a watershed. There's this other stream flowing the other side, the other one flowing this other side. So there's a watershed in between them. So this is after capture. You can see this stream was able now to store the other river, and this one was left without the source. Okay, so define the concept, river capture, so this is what I say, energetic river stills headwaters of a weak river stills, or can as well say robs. Okay, stills or robs. Identify features 1 and 2 of river capture in sketch B. Features 1 and 2 of river capture. So feature 1, the elbow of capture. Feature 1, that's going to be the elbow of capture. What do you call it? The elbow of capture? As you can see, it forms an elbow. So this is an elbow, it's like there is a carving here. So notice the elbow of capture, it is the point where capturing took place. And feature 2, that would be the wind gap. The wind gap or a dry pen. So that is an area. Feature 2, this point here, that area which is now dry. There's no more water at that particular point. Okay. Then we look at question 2.5.3. What could have caused the capture stream to erode through the watershed? Remember, when they say capture stream, this is the same as the energetic stream, or the pirate, or the one which stall water. Right. So they say, what could have caused the capture stream to be able to erode through the watershed? We said the watershed, like you can see here, this is our watershed. Figure A high-lying area which separates two different rivers or different basins. So you can see that this river was able now to erode backward through this watershed and was able now to intercept the other river. That's why when you look at the other figure B, you can see nicely that the other river, it has been robbed of its source. Okay. Then the question is asking, what could have caused the capture stream, or the energetic stream, or the pirate, or the one which stole water to erode through the watershed? 2.5.3. So you could say it was flowing over steeper gradient. That's why it was able to erode faster. Steeper gradient able to erode watershed faster. or as well as say it was flowing over a less resistant rock. To erode faster. Check the question again. What could have made it to cut the catastrophe to erode through? As well as say it was more energetic. Making it able to erode through. Okay. 2.5.4 explain the process that resulted in the formation of the misfit stream. Which one is a misfit stream? You can see this is our misfit stream. This is our misfit stream here. Misfit stream. Now a misfit stream, that is for question. Misfit stream would say a stream that lost its source. That is a misfit stream. So we need to explain the process that resulted in the formation of a misfit stream. That is question 2.54. 2.54. So we could say energetic river erode through the watershed. Energetic river intercept and stills the headwaters of a weak stream. The lower part of the weak stream is left without a source. Forming a misfit. All right, that is for question 2.5.4. So we say an energetic river erode through the watershed, as you can see here. So this is our energetic river. She was able to do Edward erosion through the watershed. Was able now to intercept this stream and eventually stealing its source. That's why here, after capturing, you can see that now this stream no longer has its source. It has been now diverted, or it has been stolen, which means the misfit no longer has any water supply. That is how we could explain the formation of a misfit stream. All right. 2.5.5 says, describe the change in the flow characteristics of the capital stream. What will happen to the capital stream? We'll say its erosive power will increase, its velocity will increase as well. We're flowing so fast. It will erode. Vertically. Be rejuvenated to gain more water, to gain more volume of water. etc. All right. So question 2.6 says, figure 2.6 shows a river profile. All right. So 2.6.1 is the river profile in figure 2.6 graded or ungraded. So our answer for this case is going to be ungraded. Give evidence because we could say the profile is not rough or not smooth. Rough or not smooth. As well say it has temporary base levels of erosion, temporary base levels of erosion. It is the waterfalls and rapids. So you can see this profile is not smooth because you can see here there are waterfalls around this other point. You see, so the profile is not smooth throughout. That's why we say it is typical of ungraded profile. So 2.6.3, why will there be more erosion than deposition at A? Then we could say because the river velocity is high, gradient is steep. Let's go, I think we'll see this on our blank page 263. We said river velocity is high, the gradient is steep, allowing more erosion. Okay, so that's why we say that at A there will be more erosion than deposition. Look at the gradient. It is too steep. That's why there's a waterfall. Too steep. So where it is too steep, we don't expect materials to be deposited. Instead, the river will be eroding vertically, and as well, due to steep gradient, the velocity or the speed of the river is going to be high. Therefore, it will be eroding instead of depositing materials. 2.64, it says in a paragraph of 8 lines, explain the fluvial processes that a river undergoes to reach a graded profile. as we know, we say that this profile is ungraded as a result of temporary base levels of erosion like waterfalls, the rough surface, etc. So let's explain the fluvial processes that the river undergoes to reach a graded profile. So you could say the river erodes away the temporary base levels including rocks, rapids, waterfalls. The eroded materials, are transported downstream. The profile which was rough now it is smooth. This smooth therefore we shall have a new graded profile. Okay. So question 1.3 are based on climatology. The say figure 1.3 shows a mid-latitude cyclone on a synoptic weather map of southern Africa. Let's check figure 1.3. Figure 1.3 there. You can see we have there is the symbol of a cold front and home front. There is a symbol for high pressure cells. You can as well look at the isobars and sketch map of southern Africa. All right. So they say, give evidence from the diagram that suggests that the weather system A is a mid-latitude, a cyclone. So what evidence, yes, can we give to suggest that the weather system at A is a mid-latitude cyclone? For this question, we can see it has a cold front and a warm front. And you can say because of the cold front, the symbol for the cold front, the symbol for the warm front as well. Symbol for the warm front as well. Set the date. Talk about its location. Located in the western side. Located in the west. That's where the MLC or the mid-latitude cyclones do originate, among other factors. Why does this weather system originate at the polar front? Then we know at the polar front, that's where we have warm winds, meet cold winds. Okay. Because the polar front is a region where different air masses meet. That includes warm winds and the cold winds. So the mid-latitude cyclones do develop at the polar front. That is where the cold easterly winds meet with the warm westerly winds. Now give a reason for the direction of movement of this weather system. Now, its direction of movement, we know they move from west to east. But the question is asking that why do they move from west to east? Then we say they are driven by the westerly winds. So if you look at the diagram, usually mid-latitude cyclones, they move from the west going to the east. Reason? Because of the easterly winds. Okay. Then 1.3.4, why is the cold front associated with severe weather conditions? Then we say because it lowers down temperatures. It lowers down temperatures and as well results into overcast conditions and heavy rains. Okay. 135. Explain the formation of the stage of development shown in figure 1.3 of the mid-latitude cyclone. Explain the formation of stage of development in figure 1.3. Let's see the stage of development. I think this is going to be the occlusion stage because you can see the cold front and warm front are mixing up, which is the occlusion stage. Okay, so I'm going to explain 1.3.5 down here. But we said it is an occlusion stage. We say it forms. I said the cold front travels faster than the warm front. Okay. Cold front narrows the warm sector. Eventually, cold front eventually purchase the warm front. So what does that mean? If you look in the mature stage, for example, this could be our cold front. This is the warm front. But we know that the cold front is more dense, so it travels faster, so it keeps on narrowing the gap. Eventually, it will intercept the warm front, creating an occlusion. Right. For question 1.3.6, Why does the cold front of the mid-latitude cyclone have a positive impact on agricultural activities in the Western Cape? Then we could say it causes winter rainfall, which favors farming. It allows growth of crops which are suitable for cold conditions. Okay.
Please use the link below,
which is a tropical cyclone, and its effect on the South Africa's climate. Because remember, we are looking at the climatic phenomena that are affecting South Africa. Therefore, we observed the mid-latitude cyclone as one of them that is affecting in winter. And therefore, for now, we are going to look at the tropical cyclone, which is another aspect that is affecting South Africa, but this one is in summer. So with the tropical cyclone, we are going to look at the characteristics here, look at the stages, look at how we can manage the tropical cyclone. Therefore, how do we define a tropical cyclone? A tropical cyclone, we shall say that it's a low pressure system that occurs within the tropics, moving from east to west. I sometimes always want to add on that a tropical cyclone is a low pressure system that is basically associated with destructive weather conditions. Okay, it's associated with destructive weather conditions, but you must note with the tropical cyclone that just like a mid-latitude cyclone, tropical cyclone is a low pressure system. The difference is that this one is within the tropics, and for it, it is moving from east to west, unlike mid-latitude cyclone that is from west to east. Hope you get the difference, guys. So this one is a tropical cyclone, which we said it's from east to west. That is its movement, okay? But you must note that it is also a low pressure system. So be it a low pressure system, you remember that the low pressure systems associated with a clockwise movement in the southern hemisphere, pressure decreases towards the center. You understand? All those aspects, we also talked about it having unstable weather conditions, rising warm air, and so on and so forth. So that is the basics of a low pressure system. All right. So we need to also know that what are the characteristics? What can you look at to say that really this is a tropical cyclone? Okay. Number one, they develop in the late summer and the early autumn. Why do we say late summer? We know that tropical cyclone needs that high temperatures. So in the late summer, this is where it is becoming very, very hot, and the early autumn, it is still very hot. So these high temperatures will ensure or will help in the continuous evaporation, okay, which results to continuous condensation, and therefore this continuous evaporation will precipitate the occurrence of a tropical cyclone. So under the characteristic, we must know that late summer and also early autumn. Okay, another characteristic that they develop between 5 and 30 degrees north and south of the equator. What you must note that why do we say 5 and 30? We must know that this is 5 and 30. This is where we see the tropics. Okay, But also you must note that it does not occur between 0 and 5. Why? Because there is no Coriolis force. How is Coriolis force important? Coriolis force is important because it helps in the deflection of winds. Okay? Either to the left or to the right, depending on the hemisphere. So it occurs between 5 and 30. So when it goes beyond 30, remember 30 and above to 60 is mid-latitude cyclone. Therefore, there it is very cold and it needs high temperatures for it to occur. That's why it is between 5 and 30 degrees north and south of the equator. Another aspect we must note also that they are named alphabetically. What we refer to alphabetic naming, you know the alphabet. For example, we have A, B, C, D up to Z. It is named alphabetical according to that particular season. Take an example, Albia. That means with Albia, A is the first alphabet. Therefore, it's the first one within that summer season. B, Bostia. Because of B, it becomes the second one in that season, and so on and so forth. So it's named alphabetically, looking at the first letter. Okay. We also note that the center of a cyclone is also known as the eye. The eye is the center of the cyclone. But anyway, I'll explain more and we see how it occurs. So the center of the cyclone is the eye. The point at the center is the eye. Okay. Then the Coriolis force must be strong. Like I said, it does not occur between 0 and 5 because there is no Coriolis force, meaning that as you move away from the equator towards the polar region, the Coriolis force is becoming stronger and stronger. Therefore, the winds will be deflected to the east such that we can have its movement from east to west. It is also named, it has got different names in different areas. For instance, Africa, it is known as the tropical cyclone. In USA, that is the United States of America, it's known as hurricanes. In Asia, it's known as the typhoon. When I talk about Asia, I'm referring to Japan there. So those reasons of Japan, it's the typhoons. Australia, it's known as the willy wheel. Okay. So those are the names that are given to different type tropical cyclone in different areas. Go ahead and know the conditions that are basically necessary for its formation. The first one is that humidity must be high. What is humidity in the first place? Humidity is the amount of water vapor in the atmosphere. This water vapor, it must be high. Why? Because there is continuous evaporation of warm air from the surface of the sea. So when this warm air rises, it has got heat inside. So remember, warm air is moist. That means it has got a high humidity. So it needs that humidity for it to condense in the upper atmosphere so that these winds can deflect, can diverge to different positions. So there's that continuous rising of warm air, and therefore humidity is necessary. Another condition is that the unstable atmospheric winds. What do we refer to the unstable atmospheric winds? We know that when these winds converge in the low pressure, the moist winds rise. So that unstable atmospheric winds that rises in the upper atmosphere condenses to form clouds, the cumulonimbus clouds, that will form rainfall. But there is that instability in the upper atmosphere because of the continuous rising of warm air. Another one is the low surface friction. We know that friction stops the movement of tropical cyclone. Another aspect that you must understand is that this tropical cyclone travels at a very faster speed. And it is therefore on that note that friction stops the movement of tropical cyclone. Therefore, it must be very low in order for us to have it moving at a faster speed. Remember, we said that it is associated with destructive conditions. These destructive conditions come because of the speed of winds that are supposed to be moving very fast. Another aspect we must note that ocean temperature must be above 27 degrees Celsius. So in this case, that the temperature of the ocean must be very hot. So these hot temperatures or the high temperatures allows the continuous evaporation from the surface of the ocean. And remember, the water that is rising has got latent heat inside, which latent heat will be lost in the upper atmosphere at a condensation point or at a dew point level to form clouds. Therefore, we need temperatures to be above 27 degrees. This is hot temperatures. The Coriolis force must be strong. Of course, we named this one and we said Coriolis force, what is its value? It's for the diffraction of winds. Okay. We also must know that tropical cyclones basically occur on the eastern side of the continent. So this is the east. So we expect this to be the eastern side. Okay. And don't forget that we said it is moving from east to the west. You see that it is occurring here on the warm water body. Remember, the eastern side is warm. Why is it warm? Because we have got ocean current that is blowing from the tropic, from the equator to the poles. So here you have the ocean, which is warm, Mozambique warm ocean currents. So when these winds blow over these warm ocean currents, coupled to the season, which is summer, the temperatures now here on the water body is going to be 27 and above. This encourages the occurrence of a tropical cyclone. Okay. And another thing, you must know that because it is affecting this eastern side, the area that is mainly affected is this Mozambique side. Okay. Then you see that it occurs within the tropics, and this is the tropics we are referring to. Okay. And it is starting from somewhere here, not exactly at the equator, somewhere here, because that is 5 going down, it is 5 plus. Remember 5, 30, and so on and so forth, going down. So that is the tropics, and here is the ocean. We also see that it is moving from east to west. You can see, I'm trying to show you the movement. This is the movement away from the equator. In that direction, it is moving towards this side. Okay. We also see it moving, passing Madagascar. Okay. Then coming to Mozambique and then affecting some of these parts. So I want you to understand that sometimes the tropical cyclone has less effect onto South Africa, because South Africa, in one way or the other, is shielded by the Madagascar island. So as it is moving from here, within 5 years, it's the starting point. Therefore, the eye is not that visible, no strong winds, no rainfall, no clouds. But as it is continuing away from the equator, closing the ocean here, coming to the side, it affects these regions of Mozambique mainly. Okay, so, and then when it reaches this other side, it's now, remember, it is moving away from the equator, meaning that as you go down this way, the latitudes are changing. Eventually, when it reaches 30 degrees, it now changes direction and it moves, it turns eastwards at 30. Okay, turns east at 30. And therefore, that means it starts to die out. Why? Because as it is leaving this region, there will be no moisture, no warm air, and then friction will be too much. Okay, that is the characteristic. Then you look at the stages of development. Okay, and the stages of development, what do we start with? We have the first stage here. The first stage here is what we call the initial stage. What you must note with initial stage is that the pressure is still above 1000 hectopascal. What is pressure? Remember, I told you that pressure is the force that A exerts onto the Earth's surface. It is still above 1,000 hectopascal. Okay, remember this is southern hemisphere. What is the rotation? The rotation is clockwise. That's why you see these arrows are showing the clockwise rotation. Okay, this is clockwise rotation. And the pressure here is still above 1,000 hectopascal in the center. Okay, and in this case, you can see it above 1,000. Okay, we got the next stage in the southern hemisphere. Within the next stage, we can see, we call it the immature stage. Okay, and within this stage, the pressure is now starting to drop. You can see that the pressure is now below 1,000. That is 992 hectopascal. It is starting to drop. Therefore, the low pressure in the center is intensifying. But don't forget that the rotation is still anti-clockwise in the immature stage. We go to another stage, which is the third stage. And the third stage is what we call the mature stage. Within the mature stage is the pressure where the pressure is well below the 1,000 hectopascal. You can see 956. And that, therefore, it has dropped further. We also have the worst weather conditions being experienced within here. This is where we call it the left quadrant. But now I want you to look at this and understand. Someone can wonder, why do we have it here? Okay, and we don't have it maybe here in the north or here. Remember, this is southern hemisphere. In the southern hemisphere, the A is rotating in this clockwise direction. But we also know that this system is moving from east to west. East to west. Okay. And the rotation is clockwise. Hope you observe there, guys. The rotation is clockwise and the movement is east. So around this area here, we are going to find out that we have the rotation and the direction of winds coinciding. So because of the rotation and direction of wind coinciding within this area, that is why we are in position to have that's why we are in position to have the left-hand quadrant located here in the southern hemisphere. It is the opposite to the northern hemisphere, because the northern hemisphere will be located around there. Why? Because as in the northern hemisphere, the rotation is anti-clockwise, okay? But the movement is from east to west. Therefore, the coinciding point is going to be around here in the north. Okay, hope you guys understand. Now, in this case, we are looking at the southern hemisphere. Therefore, in the southern hemisphere, we have the left-hand quadrant located here. That is where we have the worst weather condition. In other words, very destructive winds, severe weather conditions, wind speed is very high, and so on and so forth. Then we have the stage number 4, and stage number 4 is what we refer to as the dispersion or the dissipating stage. We can call it the disappearing stage. And what happens here? That the pressure rises again. Yes, you can see that the pressure is now starting to rise again. Why? Because the wind, maybe the cyclone has reached the cold region. Okay, maybe it has now reached 30 degrees. So it is now starting to move eastward. Okay, it is now starting to move eastward. It was moving westward, but now it's starting to move eastward. Therefore, when it moves eastward, it is now being changed and it is now influenced by the westerly winds. Therefore, the pressure is rising again. It's now starting to be above 1,000. Remember, when it goes beyond 30 degrees, there it is reaching this the anticyclones or the subtropical region, whereby it is now air descending, making it cold. Therefore, it is the dissipating stage, or we can say that it is dying stage. All right. Then a tropical cyclone, will look at also its impact. Having seen the stages, the characteristics, and so on, we need to focus on its impact. Okay. But this impact should be categorized in the what you call human impact and environmental impact. So the ecosystem being damaged. And when you look at the ecosystem being damaged, we look at the fact that this system is associated with destructive winds, okay? Very strong winds, sometimes going above 120 kilometers per hour. Imagine it is the shear or the winds are traveling at that 120 kilometers per hour. Imagine a car that is traveling at 120 kilometers per hour. What will be the speed? So the destruction is going to be very much or very high. That means the ecosystem where animals, reptiles, and so on are living is going to be damaged. So in this case, you're going to find out that this is environmental impact. Then tourism. Sometimes I always want to put the ecotourism is going to be disturbed, like tourists who come to visit the area. This is human. People who are going to come and visit the area to see what is taking place or what is there are going to be disturbed because the winds are so strong. It becomes very difficult for them to travel or to move from one point to another. In the same area, it is going to be very heavy rainfall. So the tourism is going to be disturbed. Floods will occur. Why floods are going to occur? Floods are going to occur because it is going to have heavy rainfall. Heavy rainfall. So these heavy rains, okay, they are going to result into floods. Okay, so the floods are going to have its other effects like destruction of the farmland, affecting farmers in the long run. Okay, or sometimes we shall see bridges damaged. We can also find out that the farmland is also damaged and so on and so forth. In the same line, we see that floods can even wash away the topsoils. And when they wash away the topsoils, they are going to affect the fertility of the soil, which affect productivity of crops, as we shall see forward. Okay, winds that are very strong can uproot trees. That strong winds, it's not only blowing out away the houses, you're going to find out that even the trees are uprooted because the winds are very strong. Imagine they are blowing at 120 kilometers per hour and above. What do you expect? Nothing will survive on planet Earth or on land. Okay, that's why where it occurs, the damage is very, very, very much. Okay, so people are also injured or killed because of the strong winds, because of the floods. People will be killed, people will be injured, and that is another dangerous impact. Storm surge, okay, storm surge or abnormal rise in the sea level. You will find out storm surge will lead to abnormal rise in the sea level because there is going to be too much rain or water, and that will rise the sea level with its other effects. Okay, people are going to become homeless, loss of homes because of the strong winds that are going to be blowing, the floods and so on. Homes are going to be taken away. Communication links are going to be damaged. Take an example, bridges, roads are all going to be washed away by this heavy rainfall and winds. We'll also look at the waterborne diseases. Okay, why? Because when flooding takes place, all the materials or other things are going to be taken into water. Dams are going to be silted, and therefore the water is going to be damaged. And people are drinking that water, which eventually is going to cause waterborne diseases like cholera. Okay, it's going to be in place. You find out people are going to get diarrhea, etc. So coastal flooding, and this will damage structures. Boats will be damaged. Okay, and so on and so forth. So those are some of the impacts that are going to come up because of tropical cyclones. And in the same line, we also have the management strategies. How can we manage tropical cyclones? Excuse me. How can we manage tropical cyclones? Number one, the public must be informed. Please inform the public of what is going to take place. The government has to take the initiative after seeing or after monitoring how the tropical cyclone, the path the tropical cyclone is going to take, the intensity of the tropical cyclone that is likely to affect an area. People must be informed. We inform them using radio stations, we inform them using TV stations,
newspapers, magazines, and so on and so forth. So people must be aware, and therefore they prepare in advance in order to avoid the damage. We also go ahead and say that we need to monitor the path of a tropical cyclone. In other words, you can use satellites to monitor the path, to know when it's likely to occur and which path is it going to take, so that people can be evacuated, people can be informed, people are aware. If you get to know them, to monitor the path of a tropical cyclone, people can be told to relocate, leave those areas such that we can avoid the damage. Okay. Another aspect we have there, we can say that prepare evacuation plans. Like you can say that it's going to affect area A, so please leave that area. But you just don't need, people just don't need to just leave and then they stay homeless or they become homeless. These people need to be given an area where they are going to stay. And this becomes the responsibility of the government to assist people and get them where they are going to stay. So if you get them where they're going to stay, what do you need to do? You need to build them shelters. Come up with tents, temporary shelters where they can stay such that they are not much affected by the influence of a tropical cyclone, okay, or its occurrence. Then we also don't need to build in low-lying areas. Encourage people, tell them that the low-lying areas are susceptible to flooding. So because of the heavy rainfall, the flooding that will take place will affect such low-lying areas. Therefore, people must be told to avoid settling in such areas. Okay. We also see that in the same line, avoid crossing strongly flowing rivers. Okay. Remember, when it rains heavily, that water flows into the rivers so that it can be directed into the oceans or into other areas. So people must be told that such areas, when the rivers get full, they flow faster, they flood, and therefore they should stop crossing such rivers when they are flowing rapidly like that or strongly like that, in order to avoid losses of lives. Okay. Small boats and fishing crafts should return to ports, because in the same line, we have strong winds, we have the seas getting full, the rivers getting full. So such small boats can easily be turned upside down, or they can easily sink in the water. So they should avoid such areas using such small fishing crafts and boats. Okay. Now, we also need to look at the satellite images and how they are effectively tracking the tropical cyclones. Okay. For example, this is the influence of the satellite image. And somewhere here, we have the numbers that are showing stage 1, stage 2, or different phases, 1, 2, up to the different areas. Now, this becomes the path. Okay. This becomes the path of a tropical cyclone. Meaning that if maybe it's going to affect this area, people need to be informed that please, it's going to take that path. So people are aware of where it is going to pass and how it's going to take place. Therefore, data is received and it is real-time data. You must know that satellite images are very effective in tracking because there is real-time data that is acquired. It has acquired immediately and it is accurate. Okay, you don't need to first store it, interpret it. No, immediately it is acquired, you can easily interpret it. Okay, data can be easily monitored every hour so that you know what will happen the next hour, and then you will know what is what to do. It determines the intensity of a storm, it predicts the path, and therefore large accessible areas can be monitored. So people are going to be, or the government is going to be using this information to ensure that we control areas that are being affected by tropical cyclone and we reduce the damage. Okay. Now here we look at the different aspects. For example, somewhere here we have how to manage tropical cyclones. Okay. Here the satellite images or the satellite imagery that are acquiring data on the Earth's surface. Okay. You can also use the remote sensing to acquire data. And therefore, you have observed that this is where the eye is. Okay. And therefore, if you observe that, what do you need to do then? Okay. Prepare the emergency rescue services that are in the helicopters. So if this is the area that is going to be flooded with all this water, some people might remain in these areas. They need to be taken away from such areas using the emergency rescue system or emergency rescue people. So those people are going to come there, get them from those areas. You might find that they are still there lying, or their bodies are lying there if they have been affected before they are even get to see the damage. Okay. You also need to have housing, okay, on the stilts. Strong materials are going to be used to build such houses in case such areas are going to remain with people. Use very strong materials such that even when the strong winds come, those houses will remain intact. Okay. We also need to have what we call flood proofing. In other words, some areas can be flood prone, or some areas can be affected by floods. But if such areas have got proof to flooding, then you are going to avoid the damage. Good communication system. The satellites are there, the radars are there. You are going to communicate to people through using radios and so on and so forth, such that they can be aware of what is likely to happen when the tropical cyclone is about to occur. Besides that, you might have clear evacuation routes. You see, the routes are very clear, so that if this area is affected, you can easily rescue them, take them to different areas. Then have evacuation centers that you know that if I take those people from these areas that are maybe affected by tropical cyclone, I can put them in here where the effect is not going to be so much, or where they are not going to be affected. Okay. Then have extensive medical systems or paramedics to provide assistance. You can have hospitals. You can see here that if they are taken from there and they are damaged or they are affected by tropical cyclone, take them to the hospital. So such things are supposed to be in place. Okay. You can also have those storm warden patrols. People should, those ones are going to be patrolling these areas that are likely or that are affected by tropical cyclone, so that you will do damage control in such areas. So that is basically what we refer to as a tropical cyclone. So in this case, I'm trying to recap the whole topic of a tropical cyclone. What do we need to know? We said that it is named alphabetically. For example, Andrew, Bonnie, Carol, Deborah. In this case, the first letter of the alphabet is A. That means it's number 1 in that season. B is number 2. C is number 3. D is number 4, and so on and so forth. Then we must know that tropical cyclone originates from the ocean. Okay, not near or not between 0 and 5. It does not occur. Okay, but from 5 and above, it occurs. That is the tropical cyclone. What is its movement? It moves from east to west. Okay, away from the equator, it turns east when it reaches 30. What happens? Destruction. We look at the fact that they have got strong winds, very, very, very hard rainfall or heavy rainfall, and it's associated with flooding. Then you look at the conditions that are occurring in the eye. You must note, learners, that we have got two aspects. Number one, we have got the eye, okay? We have got the eye vertex. This is the eye wall. This is the eye wall, okay? And this is the eye. So what happens when warm air rises? It is rising here along the eye wall. Remember, it is warm air. It has got moisture embedded in and latent heat. So when it reaches the upper atmosphere, it condenses at a condensation level, okay? Condenses. And when it condenses, it forms clouds. So these are the cumulonimbus clouds. We shall name them as the CN, cumulonimbus clouds. So when clouds are formed, therefore there is loss of latent heat, and this results into heavy rainfall. We see heavy rainfall on the eye wall. Can you see that, learners? Heavy rainfall on the eye wall. But don't forget that when this warm air, when the warm air rose, it rises, it condenses to form cloud. That means it loses the heat that was embedded inside, the latent heat. So there is divergency in the upper atmosphere. Some cold air moves opposite direction, but some other air descends. As it cools, it becomes heavy, and therefore it descends within the eye of a tropical cyclone. So within the eye, what are the conditions you expect? There is descending air. Okay, remember, descending air hits adiabatically. Okay, and therefore when it hits, what will happen here? We shall have, as it is descending, cold air descending, we shall have clear skies. Okay, clear skies in the eye. We shall have clear skies. Okay, no rainfall. No rainfall in the eye, no rainfall or no rains. Remember, we said here it is heavy rainfall around the eye, but within the eye, no rainfall at all. Okay, no clouds or clear skies, no rainfall. Calm weather conditions are all here within the eye. Why? Because you have got cold air that is descending within the eye. So learners, I want you to note that the climatic conditions or the climatic conditions, the climatic or the weather conditions that are experienced within the eye are totally opposite or are totally different from what is experienced within the eye wall. So the eye wall has got unstable weather conditions. It has got heavy rainfall, very strong winds. Okay, that is the eye wall. But within the eye here of a tropical cyclone, what do you expect? We expect no winds or calm, clear conditions. That is within the eye. Clear skies or no clouds at all. No rainfall at all. Calm weather conditions. All these aspects in the eye, we say no. But when you're looking at the eye wall, we say yes. What shall we have? Eye wall, strong winds, cumulonimbus clouds, heavy rainfall. So we say yes. Okay? These are the weather conditions. Before the eye, we shall have during the eye and after the eye. So before the eye, during the eye, and after the eye, what do you expect? So within the eye, you expect this. Before the eye, that is the eye wall, you expect the opposite of what happens in the eye, and so on and so forth. So here we have the dissipating stage. So in the last stage, what do you expect? It reaches the land. When the tropical cyclone reaches the land, it dies out. Why? Because on the land, there is too much friction. Okay? No warm air rising. No moisture over the land. No moisture. Remember, it needs that moisture content for it to be formed. It needs warm air, and it is forming on the sea surface or on the sea area where there is continuous evaporation and less friction. But when it reaches the land, these are the conditions you expect. No moisture, no warm air, and friction is very, very much, and that determines it's starting to dissipate or dying out. We also have another aspect here, which we call the management of a tropical cyclone. The management of a tropical cyclone. We said you can use sandbags. What do sandbags do? Remember, if you're near the coastline or if you're near the sea and that sea rises because of the heavy rainfall, what will happen? That water will start flooding inland. Therefore, you can manage it by getting sandbags, put them, pile them, and therefore, when you are piling them, you are creating an embankment to stop the flooding into the inland. Then early warning systems. When you talk about early warning system, what do we refer to? Let the people know. Use radio stations, use newspapers, use magazines. You can use TV. Let the people know that this is likely to happen. And therefore, if you let them know, you are trying to control the damage, to reduce the damage that is likely to happen. You can also track the storm, know the path. When is it likely to happen? What is the intensity, the speed, so that you can know and people will be informed of what is likely to occur. We also have another one. We say in the same line, we must inform people, let them know, okay? Then provide services to them like medical services, food. There you are trying to manage the system or to assist the people who have been affected. And lastly, we have the evacuation plans. So within the evacuation plans, you must have where to put them. Okay. Now, learners, I want to see if really we can try to answer the questions that can be asked. Here, I have one of the examinable questions. And in this case, we said in USA, it is a hurricane. In Africa or along the eastern side of Africa, we have a tropical cyclone. Okay. I don't have Australia here, but we can see that Australia is somewhere there. So it's known as Willy Willy. Okay. Now, under this line, we have what we call the equator. Okay. And therefore, the equator, there is less Coriolis force, yet we said it needs Coriolis force. We have the warm water, okay, because the equator is very hot, therefore we have the warm water and moisture content is high. Tropical cyclone moves eastward. It moves from east to west. So it moves westward, not eastward, sorry. It moves westward. Okay, tropical cyclone is part of the easterly belt, therefore it moves from east to westward. Okay, then we also have the fact that there is land, like for example here, no warm water, and there is too much friction, which stops the occurrence of a tropical cyclone. Okay, then there, in this examinable question, I would like to see question number 1, give one similarity between a hurricane and tropical cyclone on the map. Okay, what is the similarity between a hurricane and a tropical cyclone? The similarity, the one similarity that we can see, that it occurs on the eastern side. Can you see? This is Africa, and therefore this is the east. This is Africa, and this is the east. Can you see that? I mean, this is USA, this is the east. This is Africa, this is the east. So this is east, this is east. The number one similarity, that it occurs on the eastern side. The second similarity, when you look at the arrows here, it moves, as it is moving away from the equator. Can you see? It is moving away from the equator on the eastern side. Okay. It is part of the tropical easterlies. Like you can see, it moves from east to west. Can you see that? From east to west. As it is moving away from the equator, is taking the east. It's part of the tropical easterlies, therefore it's from east to west. Okay. Another thing, that when it reaches the land, it dies out because there's no warm moisture, and so on and so forth. The influence of the Coriolis force is less near the equator. Those are the similarities, but they only want one. So anything you can give here is right, so long as it's a similarity. Okay. Number 2 is explain the point of origin of both hurricanes and tropical cyclone on the map. The point of origin, where does it start from? Okay, you can see it's starting from east to west. Okay, we can also say that as it is originating from east to west, it is moving away from the equator. All right, you are explaining the original point, the point of origin of both hurricanes and tropical cyclone on the map. So it is originating from east to west, as it is part of the tropical easterlies. Okay, number 3 is, why do these cyclones move from east to west? It moves from east to west because it is part of the tropical easterlies. Tropical easterlies, just like you hear it, tropical easterlies, originating from the tropics, and it is moving from east to west. That's why it is moving from east to west also, because learners, I want you to understand, if you are sitting in a bus that is traveling from west to east, you are also moving from west to east because you are sitting in that bus. In the same way, tropical cyclone occur within the tropics, but within the tropics, the winds are moving from east to west. Therefore, the system or tropical cyclone is also meant to move from east to west. That is why it is moving from east to west. Hope you understand, learners. Number 4, why do tropical cyclones weaken as it reaches the land, or when it reaches, or it as they move over Madagascar? Madagascar is land. Can you see that? So because Madagascar is land, what happens? There is no warm water. There is too much friction. There is less moisture. That's why it weakens when it reaches the land. You know friction. Friction stops or it reduces the speed, and tropical cyclone moves faster when there is no friction. Lastly is, why is the impact of a tropical cyclone more severe in developing countries? Now I want you to look at these, learners. We are looking at developing countries. Why is it severe in developing countries? When you look at developing countries, they lack a lot of aspects. In this case, we look at developing countries. You might find that someone deep in the village there, in a very rural, serious rural area, or we can call it a farm state, these people do not even have access to electricity. They don't even have TVs. They don't have radio stations. How do you expect to warn them of what is going to happen? Because it becomes very difficult for you to reach them. Yet we can let them know of the tropical cyclone, when it is going to occur, which path is taking, and so on and so forth. Therefore, developing countries are likely to be having this effect, or they are likely to be affected by severe conditions of a tropical cyclone, because number 1, they don't have access to the warning system, the warning systems like TVs, like radio stations, some rural areas. Number 2, that some rural areas have got very poor infrastructure. Because of this poor infrastructure, if the damage has occurred, it becomes very difficult for them to be informed of for them to be evacuated or to be assisted, because they do not have the areas and inaccessible. They can't be reached. Okay, so that's why it's going to be severe. Another thing that is in developing world, we don't have that better technology of tracking the tropical cyclone. Therefore, you don't know where it's going to pass. They don't know where it's going to affect the people. And under that line, the effect is going to be very, very, very severe in the developing world. Okay, hope you understand, guys. When you explain any of those aspects, it will help us to understand tropical cyclone. Okay, so I expect learners for you to be knowing these aspects now. You can answer questions that come like this. So the advice I can give you here, that find more questions related to tropical shared with you. And therefore, I looked at a lot of things last time, but still I want to look at more. And this will help us to understand the concepts in mapwork, to understand everything in mapwork, that when you're writing, it won't be stressing you. Okay, so in this session, I want us to focus on basically map calculations. Last time, our focus was on map interpretations, how to identify features, how to know the man-made and the physical features. In other words, we did the map orientation and map interpretation. Okay, I remember very well what we explained regarding the scale, the physical features, the man-made features, and so on and so forth, map codes and everything. So we did that last time. So today, I want our focus to be on basically calculations. Okay. So dear learners, girls and boys, what you see on your screen is talking about what you need to know regarding calculations. When you're doing calculations, it is important to follow all the steps in order to get all the marks. In most cases, I see learners jumping steps, and when I'm marking, I don't mark the answer because I don't know where the answer is coming from. So in this case, I would like you to know that when you are doing these calculations, you make sure that you follow each and every step while doing your calculations. That's number one. Number two, that on those calculations, on the calculations you're doing, you make sure that you put all the units necessary for you to proceed with your calculations. For example, if you have measured on a ruler, and now you have measured this line here, and you have used the centimeters, okay? It's not a problem when you're writing your units. Let me say you have measured 2 centimeters, therefore you write 2 centimeters. There's no problem. If you have measured 1, you write 1 to show the units of measurements. It even becomes easier for you when you are doing conversions because you know which units you are changing from to which units. Okay, so it is very important for us to know the units in which we are doing the measurements on the map. That's one thing. The second thing is that when you're doing your calculations, you also need to be sure of the kind of map you are using. Take an example. When you read the question and the question says the topographic map, please straight run to the topographic map. If the question says orthophoto map, quickly run to the orthophoto map. Because what you must understand, learners, that these maps have got different scales. And these different scales help us to understand the units in which we are converting the aspects into. Therefore, we need to make sure that we know the units of measurements and the kind of map you're using. Okay. The second thing is that the relevancy of the different calculations. This makes understanding of the calculations easier. For example, gradients. If you're dealing with gradient, what do you need to know? When you're dealing with gradient, you must know that a gradient simply means how steep or how gentle the slope appears. So under that case, you know that when you're calculating the gradient, you need to understand that I need to know how steep or how gentle the gradient is. Remember, when you're dealing with the gradient, we know that the smaller the number, the steeper the gradient. The bigger the number, the gentler the gradient. So by you understanding all those concepts, knowing the value, knowing why you are calculating, then it becomes easier for you to be on track. You will not lose track at all. Okay. Now, scales of different maps and the conversion. I think this is what I've just talked about in the previous bullet. I said that you must know the different maps, and each map has its own scale. Take an example. You're dealing with the topographic map. What is the scale? The scale is 1 to 50,000. And if it's 1 to 50,000, you must understand that if I'm changing from centimeters to kilometer, I use 0.5. Why 0.5? Because the map is a topographic map. And the topographic map, 1 centimeter on the map represents 50,000 centimeters on the ground. So in terms of kilometers, it's going to be 0.5. So under that line, you get to understand that regarding the aspects of a topographic map and the orthophoto map, we need to understand which scale is being used. Okay. All right. So, if you look at the orthophoto map has got 1 to 10,000, which is the scale. So if it's 1 to 10,000 as the scale, that means 1 centimeter on the map represents 0.1 kilometer on the ground. That is in terms of kilometers. Okay. But the same way, 1 centimeter on the map represents 100 meters on the ground in actual reality. Okay. So meaning to say that the moment you familiar yourself with which kind of map am I using, how important is this map, or what is the scale of this map, it makes it easier for you to understand what you are now dealing with. Okay. Maps are always smaller than the area of the ground they represent. This is obvious, because if the map was at the actual, was having the actual length, or the actual length, the way it is in the ground, it simply means you are not going to be in a position to represent it on the map, on the paper. So it is very important to understand that a scale is used to ensure that the maps can fit on the paper. It is from that background that you know that if there is no scale, or if we are not having scales, it was going to be very difficult for us to represent the distance on the ground and to show the relationship with it on the paper. Okay, sorry. Now, there are 3 ways we're using these scales, or there are different types of scales. I think I mentioned about this last time. Representative scale, fractional, or ratio scale. Actually, when we talk about fraction, you know that the ratio is existing in a fraction format. And then when you talk about the ratio scale, it simply means it's a ratio format. For example, 1 to 50,000 is ratio. That means 1 centimeter on the map, excuse me, 1 centimeter on the map represents 50,000 centimeters on the ground. What you must note with the ratio scale, ratio scales normally will have, in most cases, they represent the same units. For example, centimeter on the map, centimeter on the ground. But it's not a must. We can also say 1 centimeter on the map representing 0.1 kilometer or 0.5 kilometer on the ground. Therefore, that is the ratio. But you know very well that we can convert the ratio to fraction mathematically. When you are converting the ratio to fraction, it simply means if it is 1 centimeter, if it is 1 centimeter representing 50,000, how will we represent this in a fraction? You just have to have 1 over 50,000. It's the same scale, but this is ratio. This one is fraction. Okay. So you must be in position to know that. Okay. So another thing is that when you look at the representative scale, we say that 1 centimeter on the map represents 50,000 centimeters on the ground. When you say it like that, it's a representative scale. Okay, so representative fractional scale or representative racial scale are basically the same. Literally, they are the same, but they're different in writing because they have the same values, the same digits we are using. But when you're writing, it's a fraction, it must be a fraction, a ratio, it must be a ratio. Okay, now, what you must note that when you look at this here, this number here is in reality is bigger than this. Okay, when you look at it mathematically, 50,000 is bigger than 10,000. But in terms of the ratio representation, this one represents an enlarged section, and this one represents a smaller section. However, this one will have more details than this. Let's check. The larger the denominator, the smaller the scale, and the lesser the details it can have. Meaning that this one has got less details compared to what this one has. What is going to happen that this one is larger, it's exaggerated, it's enlarged. And I think you have observed that normally when you get a section from a topographic map, and they put it on the orthophoto map. At times, you might not be in position to see the street names or the streets on the topographic map. But because that small section has been enlarged, you will see the street names in most cases on the orthophoto map because it has been enlarged, and therefore you can be positioned to see exactly. So the larger the scale, so the more details it can have. I mean, the smaller the denominator, the larger the scale, and so more details can be shown on that map. And also a larger the scale is used, large scale is used if the map shows a smaller area. For example, 1 to 100, a lot of details can be seen on such a map. This is what I said, like 100, when you look at it mathematically, is smaller than 10,000. But in terms of details, it will have more details that you will see on that area because it will be larger, it will be enlarged. In other words, it's like it is zoomed out. So you'll have a lot of things to see there. Okay, that was the first scale. The second scale that you're going to look at is what we call the linear scale or line scale. Linear scale is coming from the word line. Okay, so when you look at this word here, a line, this one is a line, just like you can see a line. I think you can see this here. Sorry, you can see this line here. Okay. When you look at this line, it has got two sections. Can you see that, learners? Look at it. This line has got this section here, this one here, and it has got from 0 to 9, this section here. When you look at here, here it is indicated meters. Here it is indicated kilometers. What you must understand that from 0 going this way is kilometers. From 0 going this other side is meters. So this linear scale has got two sections. It has got the meter scale or the meter section and the kilometer section. What do we need to note? We need to note that when you look at this from 0 to 100 to 1,000 meters, it's the same as 1 kilometer. But this box here, 0 to 1,000 meters, this meter section, it has got 10 small sections. What does that mean? If it has got 10, the whole box has got 1,000. So when you divide 1,000, when you divide 1,000 by 10, you will find out that you will be having 100, meaning that each box here represents 100. In other words, that means the answer you can get when you're doing calculations with the calculator, you will have to be in position to get the same answer when you put it on a linear scale. I think I will do that in the later stage to show you how we can use a linear scale in order for us to get the answer. Okay. So we know that this horizontal line drawn on a map, which is divided into a number of equal parts. A line scale is accurate and no calculations are used. A line scale is divided into parts. This is what I said. It has the kilometer and it has the what? The meters. Okay. So hope you understand that, learners. But as we proceed, I'll teach you how we use this line scale in order to get the answers. It's very accurate, very, very accurate. Actually, it's accurate more than the calculations that you use with the calculator. All right, but we shall see how we get how the accuracy is acquired. The word scale is another type of scale. A word scale is words, and this means that they are said verbally. Okay, it's a verbal statement. Just like the ratio scale is 1, 2 when you're using those dots. Now here you say it verbally. That 1 centimeter, 1 centimeter on the map represents. I want you to look at this word. The word says represents. It doesn't say it's equal to. Some of you learners make a mistake and you write this scale in terms of equal to. That is very wrong. For example, if you say 1 centimeter represents, okay, sorry for the ratio, represents 50 or 500 meters. This is very right, because 1 centimeter on the map is just representing. It is not equivalent to. So some of you write it like 1 centimeter equal to 500 meters. This is very wrong. Please avoid it. It will never be equal to 500 meters. It can't be, but it represents 500 meters on the ground. So understand, learners, that this one is very wrong. It must represent 2. So the right word to use is either represents or ratio. Okay. All right. So here, the scale is given in words. In other words, just like you see the word, this one, to say a word scale, because of this word, it simply shows us that the scale is in form of words. Because of the word ratio, the scale is in the form of ratio. Those are the 2 dots. Because of the word, what did we say, a line, the ratio is in form of a line. So from there, you get the details of how you're supposed to use those different aspects in different areas. Okay, so I expect learners not to keep on making such mistakes in map work, because it's costly. You end up losing a lot of marks because of making such slight mistakes, and you can avoid it. Okay, let's proceed. All right, how do we calculate distance? Remember, I told you that our main focus today's topic is distance. Is calculations. And while calculating, you must know that calculations cover a lot of aspects. For example, under calculations, we cover, let's see here, under calculations, we cover, number 1, we cover distance. Okay, we cover gradient, we cover area, we cover vertical exaggeration, we cover distance, area, gradient. Under calculations, we also cover magnetic declination and magnetic bearing. Okay, then under calculations, we also cover what else? Okay, if you look at all these aspects and you put them in your head, then there's no calculation you will find that will give you trouble. Okay, maybe we shall add on others as we proceed, but I want you to understand that these aspects are very important. So in case you as a child, you're going to write your paper, please make sure that you don't go to a paper minus putting all these aspects in your head before you write. Okay, gradient, area, vertical exaggeration, magnetic declination, magnetic bearing, true bearing, all those aspects need to be put in your head before you go to write your examination or any form of assessment. Now, calculating distance is the first aspect that I want us to look at. So while calculating distance, I want you to know that there are 2 distance calculations that we can look at. Take an example. We have a straight line distance, and we also have a curved distance or a winding distance. So when you talk about a straight line distance, it must be straight. Like you just put a ruler there, you get the distance in centimeters, you do your conversions, and you get your marks quickly. Now, if we talk about the winding distance, you have to use something that is not stretching, but it can be bent to cover all the widening areas, okay, or the curved areas. For example, you can use paper edge, you can use a thread, you can use anything to make sure that the distance is covered. I want us to look at this, learners. Here we have this line here, this black line here, that is coming from here to the end there. And now the question comes that calculate the distance covered by a black line covering, maybe let me say block 1A, A1, A2, and B1 and B2. So if this is a line, it's a straight line distance, what do we do? Please, learners, let's look at the procedure. The first procedure is measure This measurement is sometimes referred to as the profiles, or you have to measure the distance, the straight line distance, and then the distance you measure, you convert it. Look at this. The first thing is with a line as in above. Okay, let me say measure the distance between these two, between one spot height 1268 and 1282. Now, what do? We first of all measure the distance. Whatever you use is fine, but measure the what? The distance. After measuring the distance, what's next? Let me say you have measured the distance from where, on this map, from here to here. And after laying your ruler along this line here, you have come up with 3.8 centimeters. I think you must be knowing position. You must be in position now. You must be in position to use a ruler. When you're using a ruler has got two sides, or it has got different units. Some of you are measuring, the measurements you're using here is millimeters, because I know some rulers have got millimeters, some rulers have got centimeters, some rulers have got inches. So if you use a centimeter ruler, I normally advise my learners not to use any other units, because it disturbs a lot, because some learners don't know how to convert. So I preferably ask my learners to use centimeters, because when you're using centimeters, it becomes easier for you to know what to convert to. So when you look at this kind of map we're using, it is meant to be, or it is a topographic map. When you know that, when you understand that it's a topographic map, what comes in your head? What you get in your head is that a topographic map has got a scale of 1 to 50,000. Okay, so what does it mean? If you measure from this point here to this point here, and after putting your ruler along with this point, the units you are getting is 3.8 centimeters. So that is your measured distance. So what shall we say? We shall say that measure the distance, or map distance, times the map scale. What will you get? You will get the answer there. So what have we measured along with this line? We have measured that along with this line, it is 3.8 centimeters. I want you to see you're putting units. Why? Because you measured it in centimeters. If when you measured it in millimeters, you can put in millimeters, but you must be in position to do what? To convert. If you can't convert, it's going to give you a hard time to understand. So it's 3.8 centimeters times the map scale. Since this is a topographic map, what is the scale of a topographic map? Just pause for a second, think about it. Okay, I'm just pausing for 1-2 seconds. What is the scale on the topographic map? Okay. Yeah, I can see learners are thinking about the scale. So the scale is 1 to 50,000. Okay. And if this is the scale we have, and what shall we do here? We shall multiply by 50,000. Okay. And after multiplying by 50,000, remember, what does this scale mean? 1 centimeter on the map represents 50,000 centimeters on the ground, meaning that this 3.8 centimeters is what you measured on the map, on the piece of paper. So if this is what is on the paper, you must convert this distance to reality distance. What will it be if I go where this map is coming from? But you know that each unit on the map is representing 50,000. So what will I have? And what will it be? What will be the units? So what shall we do? So we multiply. Okay. So after multiplying, what will you get? After multiplying, what will you get? The multiplication is going to be that 3.8 times 50,000. What are you getting? You are going to get 175,000. 175,000. But this is what? Centimeters. You see that? Meaning that The map distance that you have is 3.8 centimeters. The ground distance or the reality distance is 175,000 centimeters. So that is the ground distance. But according to the question, in this case, the question is saying that the distance, the answer, let me say the answer, the examiner wants the answer in kilometers. Okay. The examiner wants the answer in what? In kilometers. What shall we do? We shall say that this answer you got here, divide it by 100,000. And what will you get? You'll get the answer to be 1.75 kilometers. Meaning that this distance you are seeing from here to here, it is the paper or the map distance. But in kilometers, in where this map is coming from, it is 1.7 kilometers. That is one way of getting the answer. But don't forget that if you go this way, you still get the same answer. If you cannot go this way, what do? You come here. I want you to see here. When it is a topographic map, 1 centimeter represents 50,000 centimeters. Also, 1 centimeter can represent 500 meters. The same way 1 centimeter is representing 0.5 kilometers if it's a topographic map. If it's an orthophoto map, the same way, because the scale here is 1 to 10,000. So in terms of meters, we're going to use 100. In terms of kilometers, we're going to use 0.1. So we come back here. And we say, this map we are using here is a topographic map. So when you check here, topographic map, if I want the answer in kilometers, what am I multiplying with? 0.5 kilometers. So I come here, I would say that 3.8 centimeters times 0.5 kilometers. What will I get? The answer you're going to get is going to be 1.75 kilometers. Do you see that it is the same answer, guys? It's the same answer. But now you must understand that here you must have this in your head. That if it's a topographic map, I use 0.5 if they want the answer in kilometers. If it's an orthophoto map, I use 0.1 if they want the answer in kilometers. If they want the answer in meters and you are dealing with the topographic map, please learners, don't forget, we use 500 for the topographic map. We use 100 for the orthophoto map. Hope learners, you won't make any mistake anyway, okay? Because those mistakes cost you a lot. Imagine this section or this part here is saying 4 marks, and then you lose all the 4 marks because of that, or 2 marks, and you lose all the 2 marks because of that. And that mistake can be avoided. So you have 2 ways. You can either go this way or you can go this other side. Whatever is easier for you, you can use it such that you can get everything right. Hope that is okay, learners. That is for the straight line distance. In scenarios, I want you to look at it in the same scenario here. Can you see? Then check which scale is it using, multiply, and you see that you get the answers here in centimeters. Then you convert the centimeters to meters. Then you convert the meters to kilometers. It depends on how you want to go about it. Okay, it depends on how you want to go about it. But all in all, that is how we do the calculations. Okay, so if it is orthophoto map, I expect learners to be knowing that. Let me take an example here. When you look at this area here, it's coming from the topographic. Imagine, please just imagine. I'm not saying this is the orthophoto map. Just imagine. This is orthophoto map. Okay. And this distance that this line that you are having here is drawn on the orthophoto map. And after measuring this distance here on the orthophoto map, it is giving you 3.8 3.8 centimeters, what will it be? So I think you know what to do. There, you just get the 3.8, okay? And you say 3.8 in terms of centimeters. Sorry, it will be 3.8 centimeters times 0.1. Okay, that is if you go from, if you use this method here. Okay, if you use this method that I put here, it's going to be 3.8 centimeters times 10,000. So the answer you're going to get, you're going to divide it by 100,000. So when you divide the answer here by 100,000, the answer you're going to get is going to be that very answer. Okay, so what you'll get will simply means that will be the distance in kilometers. In other words, 0.38, okay, times 0.1, I think you'll have to get 0.38. Okay, and this is going to be kilometers. Okay, so in this case, if this was orthophoto map, this is what I expect to see. If it is a topographic map, please use the previous one that we used. Hope we understand each other, learners. Okay, so boys and girls, having seen the distance which is straight, we must understand that we use the different approach if we are dealing with something that is not straight. Take an example, the distance for this road here from the beginning to the end. You can see that this road here is not straight, it is winding. Can you see that? So what do? Get a piece of paper or a thread, lay it along the feature you are measuring. Let me say in this scenario, it's this road here, from here to here. So you lay it along this road here nicely. Don't stretch it, because when you stretch it, let me say you are using a thread that is stretching, or anything that is stretching, it simply means it's going to give you wrong measurements. So what do? You don't stretch it, you lay it along that line. Then afterwards, you take this distance to the ruler, measure the distance in centimeters, and then you follow the same procedure to convert. Okay, if this let me say this distance here, after laying a thread along this, you see when you lay thread here, you put it from here. If it winds, you also wind the thread. If it changes direction, you also change along this line. So afterwards, you're going to hold a thread that is straight. So that thread, you lay it along on the ruler, and you get an answer in centimeters. If not, you use a divider. I think, learners, you know a divider in your mathematical set. A divider has got two sharp points. So when you lay a divider along that thread, you just put it along the thread and you get the distance. You transfer the divider to the ruler and you get the centimeters. So those centimeters are the ones you convert using the same procedure. If it's a topographic map and they want the answer in kilometers, 0.5. If they want the answer in meters, 500. If it's an orthophoto map, they want the answer in meters, 100. They want the answer in kilometers, 0.1. Like that. So you won't find any challenges at all. Okay, so that is distance, learners. I hope we understand each other. We are at par and everything is okay regarding distance calculations. So if you still have any problem regarding distance calculation, feel free to contact me via Thundereduc platform, or to ask questions via the Thundereduc platform. I'll be in position to reply to you and answer your questions. But learners, I want you to know that map work is very easy. Map work is the easiest section to pass. And I want you to understand that in any case you understand map work, it's free marks. If you really understand it, it becomes free marks. So I don't expect my learners that are now going through this lesson to still fail map work. Okay, most especially these simple things. So, okay, we are done with the distance, or actual distance, or straight line distance, or curved distance. So that is exactly what can be asked. Let's proceed and look at area calculation. Let's proceed and look at area calculation. Area calculation, in other words, the area is calculated to determine the actual size of the ground on the ground. And in this case, we'll look at a feature or a demarcated area that you're going to look at. Under this line, we are looking at the area that is put down here. And when I look at it the way it is, what comes in my head is that this is a topographic map. And the moment I see a topographic map, I'm thinking of the scale that is now meant to be used on the topographic map. Okay. So what we can do here, or what can we do here? We go back here and say that while looking at the area can also be calculated in kilometers, and also it can be calculated in meters. So learners, I want to electrify something here. When you look at the formula that is now being used here, it is area, which is, it's area which is equal to L times S in 2 brackets times B times S into brackets. This formula normally in your exams is not what is given. In your exams, they normally say area is equal to L times S. This is what normally comes in your exams. Now, when you see such a formula in your exams, learners, please don't hesitate to expand it. You can have the formula like this in your exam, but just know that area is equal to L times S times into brackets times S, B times S. Sorry, this is L times B. Okay. Now, if it's like this, that simply means you will not forget what to do. You will not forget that I have to multiply everything by the scale. Otherwise, if you go with this here, in most cases, you forget to multiply everything by the scale. Yet, the area we are looking for the area on the ground, actual distance. And therefore, to get the actual distance, you must make sure that you consider the scale that is used and which map is being used. Take an instance that when you come here, when you come here, oh, I want to create space, sorry for that. When you come here on this area that the part that is given, look at this. By looking at the way it is even indicated area covered by the orthophoto map. But this must be on the topographic map. The way you see it's in color, you can see the features with symbols. Remember, a topographic map basically uses more of symbols and so graphs and so on and so forth. So these contour lines and the way it appears in color, it simply tells us that it's a topographic map. What are we measuring? We said that according to the formula, we need to measure the L and the B. You come here. When you look at this part here is 7.4 centimeters. This part here is 9.8 centimeters. By you looking at the units or the answer that you got after measuring, it clearly tells you which one is the length. Okay, normally the length is longer than the breadth. So you will find out that the L must be bigger than the B. In most cases, even if this part here is turned upside down and this part is here, this part is up here, you must note that even if it is turned upside down, This line that is longer should be the length. Though I know after calculating, you will get the same answer, but you have swapped the concept. The concept is that length is the longest part than the B. So if you just put this under the length instead of under the B instead of putting it under the L, you will lose marks. Sometimes you will be penalized for that. So please let us try to avoid some such minor mistakes. So when you're given this formula, which is L times B, normally I tell my learners to expand it, write it in an extended formatting. The moment you write it like this, it is going to come into your brains that what is A? A is the what? Is the area, which is equal to L. What is the value for L? L, you have just measured it that it is 9,8. So you will come here and you say 9,8 centimeters times the scale. What is the scale? Which map am I using? I'm using a topographic what? A topographic map. Oh, I'm using a topographic map. What is the topographic map scale? The topographic map scale is 50,000. Put it in brackets. Remember, this is also what? Centimeters. Okay, put in bracket times. What is B? The value for B is 7,4. I come here, I say 7,4 centimeters times. What is the scale? Obviously, it's a topographic map. Okay, oh, the topographic map, what is the scale? Is 1 to 50,000. So you say times 50,000 centimeters. You cross the brackets. Why am I putting this? Why am I multiplying by 50,000? To convert the centimeter distance, the actual distance in centimeters on the ground. So when you multiply that, what will you get? You will find out that it's going to be 9,8 times 50,000, which gives you 9,8 times 50,000, which gives you 5. Okay, 50,000, 9,8. This is centimeters. Okay, then you go, sorry, it is multiplication. It is 9,8 times 50,000. It gives you 4. It gives you 4,9,0,0. Okay, 490,000. Okay, this is centimeters. Then you come here, 7,4 times 50,000, and you get that is 370,000 centimeters. Okay, so I have this. It's all centimeters. Okay, it simply means that the paper has got 9,7, but in reality, where the map is coming from, it is 490,000 centimeters in reality. Just the same way the B has got 7,4 centimeters, in reality, it is 370,000 centimeters. Now, these are centimeters, okay? But according to this, the question wants the answer in kilometers, okay? So because the question wants the answer in kilometers, here, can you see it in kilometers? So what do? I come here, I change the centimeters to what? To kilometers, okay? So that means this divided by 10,000, divide by 10,000, sorry, not 10,000, 100,000, and you also divide by 100,000. such that is 4, go with this 4, and therefore I'm remaining with how many? 1 place. I move it here, it becomes 3.7 kilometers. That means this one has changed from kilometers, from centimeters to kilometers. Okay, now I come here, so this is this one, 1, 2, 3, 4, 1, 2, 3, 4. How many places am I moving? It's 1, which becomes 4.9 kilometers. So the answer is going to be kilometer times kilometer. What are you getting? You get kilometer squared. Now 3.7 times 4.9, what do you get? 3.7 times 4.9, what are you getting? You get 18.13. So this answer you get is in kilometer. This is the area if you are using kilometer. So in scenarios whereby you were supposed to use meters, what will you do? It simply means that after multiplication is here, you don't multiply by 10,000, you don't divide by 10,000, you divide by 100. Even here, you divide by 100. Someone can ask me, but sir, where do we get this? Why do we multiply by 10,000? What do we multiply? What do we divide by 100,000? And why do we divide by 100,000? I want you to remember these, learners. Remember this so that you don't forget. Okay. King Henry does not mind drinking cold milk. I just want to deal with what I'm dealing mainly with, kilometers and what? And meters. So this is kilometers, this is centimeters, this is millimeters, and this one is meters. Most important. So if kilometers, how many spaces shall I have? Those are the spaces. This one, 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 those are the spaces. And here, those are the spaces. Meaning to say, if I'm moving from here to here, okay, I will divide by what? The spaces, the numbers are here. You see? It's 100,000. That's why here I divide by 100,000 to change the centimeters to what? To kilometer. The same way here, if I'm using meters to kilometer, I will come here and I will use this number here. You see that? So that means I will divide by 100 here, which gives us the answer that is very, very okay. Okay, so if you're changing from centimeters to meters, that means you are going to be here, still using 100. So while looking at those aspects, it is going to be very easy for you to remember. That's why I encourage learners, if you're given L times B, extend it so that on the extension of this area of this formula, it will be very easy for you to remember what S stands for and what B stands for. Under the same line, if I put this one away, I want to see if really, because I don't want you to say, but sir, that we are forgetting, or that site is too long, we can't remember. That's why I'm giving another option. Okay. The other option here is that, what shall we have? We shall say that area, still you expand it, area is equal to L times S into this B times S. What is the value for L? The value for L is 9.8 centimeters times 0.5. And here the value for B is 7.4 centimeters times 0.5. You know that this 0.5 is the scale. But why are we multiplying? We are multiplying so that we can convert the paper distance or the distance on the paper to the reality distance, the ground distance. So that when you multiply this by this, it still gives you, okay, 4,9 kilometers times 3,7 kilometers. So the final answer you're going to get is going to be 18,13 kilometers squared. I want you to understand that the moment you put kilometers here and you put kilometers here, I will know where the kilometer squared is coming from. But if you don't put kilometer squared and you end here and you put kilometer squared, the question is whether this kilometer squared comes from. It's coming from kilometer times kilometer, kilometer squared. 4.9 times 3.7 gives you this one. That's when you get the final answer. So there will be no way you'll be penalized for that. So please ensure that you put units. And like I told you at the beginning, that while doing calculations, you follow all the steps. Okay, you follow all the steps. So everything you do, you make sure that the steps are catered for. Every step you do, it has a meaning. So if you don't respect the steps you are doing, it simply means that you're going to be affected, and eventually you will jump other steps, which will result in loss of marks. And remember, we are doing this to maximize marks. So I don't expect my geography student to fail to maximize calculations, GIS, and interpretation. Those 30 marks, they look to be for free. Okay, but you can apply your geographical skills, and then, yeah, we proceed. Now, I think you have seen this, 4,9, 3,7, and the answer is there, which means the final answer is this. And how do you get this? I have taught you how to get that. Okay, remember, I'm reminding you that don't forget to put units. That's why you see here there's kilometer square, there is kilometer here, there's kilometer square here. So that here at the end, this times this I get kilometer square, this times this I get this. If you don't do that, you're missing a point somewhere. Okay. Now that is area. So this question is basically asking area in kilometers. What about if they ask area in meters? Area in meters, you just need to take away this other. It's the same, you follow the same procedure here, you follow the same procedure here. But now when it reaches here, you convert this to what? To meters. So you divide by 100, you divide by 100. Then at the end of it all, you will reach your final answer in meters. Okay. Now, the next aspect that I want us to look at is the aspect of true bearing. True bearing is the same as direction. However, true bearing appears in you measure degrees. In other words, you use degrees, you use angles. We follow the same procedure, but we use what? We use angles. In other words, at times they ask true bearing and direction, which one is very accurate?